Good morning. We should get started. It's my pleasure to introduce Massimo Gaspari, who is at Princeton, and he's going to talk about self-regulated AGN feedback loop.
Yeah. So thank you very much. And good morning, everyone. And thank you in particular for having me. And in particular, thank you to Paul and Carol also for the help and time put on this. So I just moved to Princeton a couple of weeks ago from MPA, where I was a postdoctoral fellow. And so I will just discuss and review a little bit my topics of research, in particular focusing on the self-regulated AGN feedback. So I will focus more actually on the feeding part and a little bit in the end on the feedback part. So in the feeding part, I will discuss mainly how the supermassive black hole accretes the gas. Is it in sort of cold or versus hot mode? We want to link these 50 or more kiloparsec scales down to the subparsec scales. And in particular, we want to understand the nonlinear interplay of key physics. For example, turbulence, cooling, heating, and rotation. And we are now actually starting to understand that such nonlinear interplay drives new accretion mechanisms. One of those is chaotic accretion, or CCA. In the feedback part, of course, we are mainly concerned with the amount of energy released by the supermassive black hole, where this energy is deposited, is it in mechanical, thermal, or radiative form, and which are the key imprints of the feedback mechanism. So my main tool of investigation is mainly 3D simulations using flashcode. So for the feeding simulations, so these are very high resolution simulations, so of the order of several million CPU hours. So we go basically from 10 kiloparsec and zooming in the very central region with very high resolution down to 10's gravitational radii. While in the feedback simulations, of course, we want to resolve the several giga revolution up to basically the megaparsec. So we need essentially coarser resolution to do that. And both parts are linked through this feedback loop. Now, I like to kind of divide the models broadly in two modes, the hot mode and the cold mode. So here I just showed some examples. So we are in a massive early-type galaxy as NGC 5044. So this is the central only cross-section of mass-weighted temperature within the central 1 kiloparsec. So we have this hot halo, 1 keV, more or less, so X-ray emitting hot halo, supermassive black hole of 3 × 10⁹ solar masses. And here I just showed two examples. One, the hot halo is essentially dominated by turbulence. So turbulence sears your gas in a chaotic way, while of course with the rotation we have coherent motions. But the key point here is essentially that in hot mode accretion, we always have some kind of vorticity in the center, either chaotic or coherent. So in the end, if we plot the accretion rate as a function of time, we always end up with some kind of suppression of the accretion rate, so stifling the accretion. And typically for subsonic turbulence, this is of the order of 3, 4, compared with this pure bondy, spherically symmetric hot mode accretion, which I guess all of you know. Of course, with supersonic turbulence, this decrease will be much, much more orders of magnitude. So hot halos are not only, of course, turbulent, but we know they are emitting a lot in X-ray, but not only, and all the residual cooling can be seen throughout all the wavelengths, so down to UV, H-alpha emission, of course, radio and molecular. Here I just shown some beautiful images from Perseus, but I just want to remember that in basically many massive early-type galaxies, we see these beautiful filaments, and Rebecca has talked a little bit about that, and Grant, I guess, will do more in his talk, especially for galaxy clusters. So in cold accretion modes, and where we don't have basically any kind of rotation or turbulence, of course, we form this kind of pure cooling flow. So massive condensation of a cold cloud down to here 10⁴ Kelvin. And of course, this cloud keeps increasing in size through time. And of course, the accretion rate is basically equal more or less to the cooling rate. Instead, if we have some amount of rotation, of course, we condense onto the central plane, and we form cold thin disk. Again, a centrifugal barrier will suppress your accretion by here 2 orders of magnitude, still a bit higher than in the hot mode. But so hot halos are not only cooling, turbulent, rotating. Of course, they are driven and linked to the heating and mainly AGN feedback, and this has been shown by XMM, Chandra observations. Christine has done a great job in her review to show all these beautiful features, such as bubbles, shocks, and so on. And you can see here is just very quickly, we will see a quick movie later on of these AGN outflows self-regulating the halo. And this is basically the internal average energy increase averaged over 1 gigayear. And you can see that even though the AGN outflows are kind of anisotropic, over the long term, basically we have sort of isotropic heating. And both from observations and simulations, we can say that basically the heating rate on average balances the cooling rate. So there is this sort of quasi-thermal equilibrium on large scales, both in space, in a sense in radial shells, and time. So this kind of very perturbed halos, again, heating, cooling, and turbulence are all interacting non-linearly. It comes out that the accretion is very different from classic studies, and one of these is chaotical accretion, or in brief, CCA. And so in simple terms, really CCA is very familiar to our everyday experience of weather and rain. So very simply, you have condensation of these cold clouds and filaments out of the hot phase, and these filaments and clouds just rain onto the supermassive black hole. Now, and this is really the key concept behind CCA. So then we can talk about linear thermal instabilities and so on and so forth. But really, this is really the core physical concepts. Now, these cold clouds and filaments start to rain onto the supermassive black hole. And so in the very center, about hundreds parsecs or so, of course, they start to inelastically collide in chaotic way. And if you plot the angular momentum distribution, so condensation basically broadens every time your angular momentum distribution of your cold gas. And also turbulence keeps basically broadening your angular momentum distribution. However, your chaotic collisions in the very center, especially major collisions, start to basically promote angular momentum mixing or partial cancellation. So this means that if we plot the accretion rate as a function of time, we see this kind of boosted accretion. Here for elliptical galaxies, basically mega-year variability. And the accretion rate can be boosted up to 100 times the Bondi rate, which is more or less comparable to the cooling rate. And of course, we have several collisions, cloud-cloud collisions, filament cloud collision, cloud clumpy torus in the very center collision. But in the end, again, this mechanism can boost accretion up to a large value. So if when turbulence decay, so this, well, in dimensionless number, this means turbulent halo number becomes basically greater than 1. So you can see that the chaotic evolution disappears, and we are approaching this kind of more quiescent disk evolution. Of course, as the disk is consumed, we are only left with this hot mode accretion, so kind of suppressed Bondi accretion. Okay, so there are several observational ways to test CCA. So one of those is X-ray temperature profiles. And so CCA predicts inner flat X-ray temperature profiles, which is very different from basically all hot models, which predict a very cuspy X-ray temperature profile in the center. So interesting enough, so very recently we have seen, for example, in AIM-87, in NGC 3115, such kind of flat X-ray temperature profile and associated with multi-phase structures. While, of course, we have also other examples of more quiescent galaxies, as NGC 4649, where we see this kind of hot mode, only one phase and cuspy temperature profiles. Now, another interesting test is H-alpha emission. So as I said, the cold gas condenses out of the hot phase, and basically the first stable phase is around 10 to the 4 Kelvin. And so here H-alpha is very interesting probe. Here again, I plotted SOAR data of H-alpha emission. And you can see that in, for example, NGC 5044 is a beautiful example of such chaotic system, also perturbed by AGN feedback quite a lot. You can see that in this CCA mode, we have essentially these filaments and clouds up to here 4 kiloparsec. So, and these kind of extended filaments follow more or less a criterion, which is essentially the cooling time is divided by the free fall time less than 10. So you have this kind of condensation region. Again, this threshold 10 is not a line in descent. There is a lot of scatter, so between 5, 20. So it's not perfect marker, but we can see that in massive galaxies, we have this condensation region around 5 kiloparsec up to galaxy clusters up to even 20 or even more kiloparsec. So of course, instead, when we are left with only less turbulent system, more quiescent system, we see H-alpha also disk here in NGC 68, for example. Now, so there are several implications, as I said, of CCA, and I like to call it, as again, raining onto black holes. I won't discuss much this. So, of course, this kind of cold clouds and filaments may form broader region, narrower region. Of course, we see often this clumpy and turbulent torus. We know how important it is for AGN unification theories. But I like to stress actually at this point so that there is this very tight symbiosis between the tiny black hole and basically the whole galaxy. So the black hole mass is essentially linearly linked to the cold mass of the host halo. We know that later on we will form stars, so observers tend to see more kind of Pythagorean relation. But so the key point is this very fast communication time between the host and the tiny, very, very tiny black hole. And of course, these accretion rates are boosted up to the cooling rate, which is really key for the AGN feedback cycle, which we will see in a moment. Okay, so this is a quick movie. So this is density cut through the midplane is 20 kiloparsec of a cluster core, and just focus on the top panel. So essentially, as cooling dominates over heating and cooling time, free fall time falls below a factor of 10, so thermal instabilities become nonlinear. Cold clumps here in red, so these cross sections, start to condense out of the hot phase. They rain onto the black hole, and they feed the, of course, the black hole, boosting the AGN outflow power. And of course, the outflows thermalize in the core, 10 kiloparsec or so, through shocks and bubbles. I will show some examples. And of course, thermalizing in the core means reducing your TI, reducing your cold gas, so your accretion rate goes down, the power goes down, and later on, of course, your halo is allowed to cool again. And of course, in the end, we are left with a multi-phase structure, so with a hot halo and a more warm and cold phase. So this is another key example of self-regulated AGN feedback with CCA. So there are consistency with observations, here mainly X-ray observations. So-called solving the cooling flow problem means actually two things. Well, a third one I will talk in the last slide. So quenching the pure cooling rates by at least 20-fold, and this can be achieved. You can see the cooling rate as a function of time is decreased by basically more than an order of magnitude, but this can be easily done by kind of any heating mode, thermal, mechanical, or radiative, and so on and so forth. Of course, what it's very difficult is essentially to preserve the cool core structure for several gigayears, so avoiding here overcooling, but we need also to avoid severe overheating, otherwise we would see only non-cool core objects, and we know that there are several. So the universe is populated by cool cores, low redshift, high redshift, and weak cool cores, strong cool cores, and so on. And for example, here is the X-ray, so projected X-ray temperature. And you can see that there is, of course, variability, but essentially the positive temperature gradient is not destroyed by the self-regulated feedback. Here you can see the jet power, the jet velocity as a function of time, 7 gigayear. And of course, here maybe you see more these peaks up to several 10 to the 44 erg per second. So this is what observers tend to see. With deeper observation, we will see more and more of this. But you can see that basically on the lower level, the duty cycle is almost always on, right? So say on the low-level activity. So there is quasi-continuous cycle, and it is a relatively gentle cycle. Although we kind of are a little bit biased by, bigger events such as bubbles, cavities, and shocks for example, in massive systems. So, and to remark this, so there are several key imprints of feedback. I just briefly review here. So first of all, X-ray bubbles of the order of with radius 10, 15 kiloparsec or more in clusters. We see these weak shocks, cocoon shocks, and turbulence self-driven by the AGN outflows. We also can basically track the AGN feedback with, for example, the metal uplift or cold gas entrainment. And we see these bubbles, shocks, entrainment basically throughout all the systems from massive clusters, as I said, but if you look deep enough in groups and massive galaxies. So I put here some groups, but again, Christine has done a great job in showing many beautiful X-ray data. And so the last slide here, actually, as I said, so quenching the pure cooling flow doesn't actually mean to reduce the total cooling rate, which is relatively easy. What it's relatively difficult to do is actually to quench in detail the X-ray spectrum. So the problem is how to quench from so this one is more or less the hot phase around 3-4 kV down to 0.3, 0.4 kV. And so we want actually to suppress quite a lot in the soft X-ray. And so here in red are the X-ray constraints. There is a lot of literature in the last 15 years. And so essentially we see very steep suppression in the soft X-ray regime. And so actually if you put some AGN feedback, so AGN feedback is very simple, inside-out feedback. So this means that so if the thermalization is done properly, so you deposit relatively more heat in the inner region, which is essentially the cooler phase, right? So you actually tend to achieve, you get this quite naturally from self-regulated AGN feedback. If the feedback is not too strong, of course, or if the feedback is not overcooling. If we add a little bit of turbulence, of course, this increases the spread in your distribution. And remember that turbulence, for example, becomes transonic in the cooler and cooler phase. So we have kind of relatively stronger diffusion and mixing due to turbulence. So this is my conclusion. And just to recap this self-regulated AGN feedback loop. So very simple, you have this chaotic cold accretion mode where you form extended non-thermal instability out of basically the hot phase, inducing these cold clouds and filaments, rain onto the supermassive black hole. The feedback, again, is boosted up to 100 times the Bondi rate or the cooling rate. So you quench later on the cooling flow and star formation through bubbles, shocks, entrainment. Of course, later on, as turbulence decays, we are left with a kind of cold disk, so which is basically the residual effect of partial angular momentum cancellation. And the accretion goes down, the power goes down, again, the disk is consumed, and we are left only at the end with some hot mode. So hot mode means highly suppressed accretion rates, much below the Bondi rate. So, and later on, we are allowed to cool again and form TI over and over again. Thank you.
Questions for Massimo?
So in your phase diagram, I saw that there was a very sharp cutoff.
Yeah,
Temperature of like 10 to the 3.
10 to the, yeah,
Is that
4.
the floor temperature?
Yeah, in that simulation, exactly. So it's a floor in that simulation, but yeah. But you can go down.
Your run where you didn't include the floor?
Sorry?
I'm wondering what your lowest temperature that you would get is.
Yeah.
Do you run where you don't include like a floor in temperature?
Yeah. Well, numerically, you always need some floor at some point, because otherwise you crash the simulation. Sorry?
Why 10 to the 3?
So 10 to the 3, 10 to the 4 is the first stable phase. So there are, I mean, we can do more detailed simulation of that. But so in the cooling curve, you have essentially the first. It's very, sharp. So the logarithm of dln lambda dln t basically is very steep. So you are very stable around 10 to the 4 Kelvin. So that's the reasoning around that. But of course, we need to go down. Yes, of course, exactly. But in that simulation. So yeah, exactly. Good point.
Yeah. The simulations that you discussed, they presumably didn't include accretion flow at the very center in the black hole, right?
Yeah, there is no GR basically.
The accretion flow itself brings two issues. One is the propagation time through the accretion flow, which is quite long.
Yes.
For a thin accretion disk, it could be even comparable with the Hubble effect. The second is how much mass actually makes it to the black hole, because the accretion flow can make the gas flow out and actually it flows on the way.
Sure.
What's your point of view on these two issues?
Well, as I said, so we did these very high resolution simulations, so down to basically 20 gravitational radii. So, and we still see a boosted accretion. Of course, I would like to go down deeper, but I mean the time step becomes very, very, very small. So I agree with you. I mean, in this kind of chaotical accretion, you tend to, in the very central region, you tend to basically chaotically collide many times, and you basically funnel, you see the funneling of these cold clouds in the very, very center. So there is actually no thin disk in the CCA evolution. Of course, when we form the disk, then it's, again, suppressed accretion even more in the very center. So, yeah. But this will get better with time, right? So as we can improve resolution and hopefully go down deeper.
We have time for just one more. But, of course, there's coffee and lunch to talk further. Nick?
In your plot where you showed the distribution of angular momentum, it looked very centered on 0. Is that right?
It was, yeah, well, yeah, exactly.
So if you have these clumps of cold gas coming in on sort of random inclinations, I wonder if you can constrain the prevalence of this chaotic cold mode by looking at how many radio loads, for example, maintain a constant orientation, or, for example, looking at iron K alpha measurements of black hole spin, since if you're sending in gas on random inclinations, the net effect is to spin the black hole down.
Yeah, exactly. That was one. Yeah.
Okay.
Yeah, exactly. I mean, changing the black hole spin is definitely one interesting topic. I haven't done calculation on that, but yeah, that's a great point. Yes, could be studied, and it's one implication on exactly that. You tend to kind of realign or change or decrease the black hole spin with chaotic accretion. Yes.
Okay, let's thank Massimo again. Next up will be Anna Pantos, who's here at SAO, and she's going to talk about revealing the drawline region in AGN using the reverberation method.
Sound good? Okay. All right, hello everyone. So today I'm going to talk about measuring the masses of supermassive black holes in AGN, and one of the main problems that we have in trying to do this, and how we can overcome this problem by trying to constrain the properties of gas close to the black hole in the broadline region. This is work I've been doing with Brendan Brewer and Tommaso Treu and the LAMP 2008 collaboration. And really it's motivated by the fact that we'd really like to understand the evolution of the supermassive black hole population, its accretion rate, and how it's related and interacts with its host galaxy through possible feedback mechanisms. But in order to do this, we really need to be able to measure supermassive black hole masses outside of the local universe, which means having a method to do this that does not depend upon spatially resolving the motions of gas or stars around the black hole. And thankfully, we can do this using supermassive black holes that are actively accreting in AGN, where we can actually get down deep into the sphere of influence of the black hole by transferring, instead of worrying about spatial resolution, by sort of using resolution in the time domain instead. And so for this work, we're going to focus on gas in the broadline region, which is outside of the accretion disk and supermassive black hole, but inside this dusty obscuring torus, which shields the broadline region from certain lines of sight. And gas in the broadline region is moving so quickly around the black hole that the emission lines from that gas are broadened, which gives us a direct handle on the kinematics of this gas. Of course, if we're trying to measure a black hole mass, then the other piece of information we really need is to know how far away this gas is from the black hole. And in order to get this, we use a technique known as reverberation mapping. And this really relies upon the stochastic variability of ionizing photons from the accretion disk. And in practice, we look at the optical photons typically, since this is easier to observe. But we can see these. And the ionizing photons also propagate out to the broadline region gas and are basically reprocessed into line flux. And so you can imagine that if there's some amount of variability in the accretion disk flux, you'll see these same variability features in light from the broadline region, but with a time delay that depends upon this light travel time here. So if you monitor an AGN over a couple months, you'll see some variability features, hopefully, if you're lucky, and you can sort of map this time lag between the continuum light curve and the broadline flux and measure tau, which gives you some sense for the size of the broadline region. So combining the size of the broadline region with the velocity of the gas in the broadline region from the width of the broad emission line, you can get at a black hole mass, where c is the speed of light, and this transfers your time lag into a distance. G is a gravitational constant. And the last piece is f. And this is a normalization constant of order unity, dimensionless. And it sort of encapsulates all of the unknown geometry, dynamics, and orientation of the broadline region. And unfortunately, this is the biggest problem in reverberation mapped measurements, because we don't actually know what f should be because we can't spatially resolve the broadline region. So typically, the way we get around this is by measuring an average value of the f factor. And this is done using the correlation between black hole mass and stellar velocity dispersion of the host galaxy bulge, the m-sigma relation. And we take the m-sigma relation for local galaxies where we have black hole mass measurements from dynamics of gas or stars, and we basically overplot the reverberation map sample so that it is aligned with it. And we figure out what average value of f this gives us. Unfortunately, this introduces the largest source of uncertainty in reverberation map masses, as big as 0.4 dex, because the individual black hole mass measurements could have substantially different f factors from this relationship. So in an effort to improve the situation and hopefully measure AGM black hole mass measurements more precisely, I've been working on a different technique, which goes at trying to model reverberation mapping data sets directly using a geometric and dynamical model for the broadline region. And this gives us sort of three things that we'd really like. The first is some sort of quantitative constraints on what's actually going on in the broadline region. What are its geometry and dynamics, and how is it oriented with respect to us? This gives us, in a sense, the value of f in individual AGN instead of having to rely upon this average value. And these two things together should allow us to measure the black hole mass to less than 0.4 dex uncertainty, because we no longer have to carry around this average value of f and its uncertainty. So the way that we've gone about doing this is working within a Bayesian framework in which we develop some model for the broadline region, and we use it to predict some sort of model broadline light curve that we can then compare to data. And by simply testing different models, we can try to figure out which one best fits the data. So in an effort to make as few assumptions as possible at the beginning, when we don't have a lot of prior information about what's going on, we've developed a simply parametrized phenomenological model for the broadline region, where we're just really interested in trying to constrain the distribution of broadline emission. We might also be interested in the distribution of the gas, but in order to connect that to the emission, we would have to make additional assumptions. So in this model, the distribution of emission is given by the distribution of many point particles. And each point particle is just going to act like a mirror, reflecting the continuum light from the accretion disk at the origin to the observer with some time lag that depends upon its position, and with a wavelength shift for the line flux that depends upon the point particle's velocity. And so you can imagine that if you have some distribution of point particles and you filter through it some AGN continuum light curve, you could predict any sort of line light curve or emission line profile from the broadline region. So in order to do this, we really need two parts. We need to both know the continuum flux, AGN continuum flux at all times, and we also need to have some way of determining where these point particles should be spatially and in velocity space as well. So for the AGN continuum model, we use Gaussian processes, which has been found to be a good model for AGN variability on the time scales that we're interested in. And it also allows us to include the errors from interpolation between the data points, which is very important on having robust measurements of broadline region and black hole mass parameters. So these are 5 examples of what this looks like in practice. The black points are the data. And so you can see in regions where we have a lot of data, the continuum model is very well constrained. But in regions where we don't have a lot of data, there's quite a bit of uncertainty in the continuum model. The second part of this is the broadline region model itself. And for this, we use a radial distribution of broadline emission that's given by a gamma distribution. This is fairly flexible. It can range from a narrow Gaussian to an exponential profile or steeper. And once we have this radial distribution of gas, we can apply some opening angles. So we can go from a sphere to a disk, as well as an inclination angle. And we finally allow for some additional asymmetry, such as a transparent to opaque midplane, more emission from the far side or the near side of the disk, and something more like a cone instead of a disk. And for the dynamics, we choose something that's fairly simple at this point. We only consider the gravity of the black hole, and we consider only 3 different kinds of orbits: near circular, inflowing, and outflowing. So this is a fairly simple model to start, but we've begun to apply this to real data. So I'm going to show you results for the LIC AGN Monitoring Project 2008 data set, but we are currently working on analyzing a whole slew of data. There's actually quite a bit of high-quality reverberation mapping data that's been taken in the last 5 years especially. So there's a lot of room to continue this approach. So this data set was built upon 64 nights of spectroscopy at the Shane Telescope at Lick Observatory, as well as ground-based photometry from a number of telescopes. And we monitored 12 AGN, and only 9 had measured time lags. This is just what happens when you're dependent upon stochastic variability. And 5 of those had data good enough for this broadline region modeling approach. So this is what I'm going to show you now. Here I'm showing you one posterior sample of the inferred geometry for the H-beta emitting broadline region. So each row is for an AGN, and this left-hand column is the edge-on view of the broadline region that we infer. So the observer is looking from the right-hand side in this direction, and then this right-hand panel is the face-on view of the broadline region. The size of the points corresponds to how much emission you're getting from each point. And what you can sort of see at first is that the geometry that we infer is basically a thick disk for all of these systems. Of course, their inclination angles vary, but they're generally face-on, as you would assume from sort of the AGN orientation picture. Another thing you can notice is that there seems to be a preference for more emission from the far side of the broadline region, as you can see here in these 3 objects for which that is actually constrained. For the dynamics, we generally find a combination of something like near circular or inflowing orbits. We don't find any of these objects with outflows. This isn't too surprising because these are very sort of low luminosity, low accretion rate objects. So when you put all of this together, what we're able to do is measure the black hole mass to 0.15 to 0.3 dex uncertainty, which is a substantial improvement over the 0.4 dex uncertainty that we would otherwise have to be dragging around if we use this average value of F. So that's good news. Just to give you sort of a little more detail for the highest quality object in this sample, ARC-151. So for this object, we were able to measure the black hole mass to 0.15 dex uncertainty. You can see the posterior PDF for black hole mass here, and it's definitely correlated with certain other parameters of the model, such as inclination angle and opening angle. But this is one of the powerful parts of using a Bayesian approach, so we can look into all of these things. Even though we're using a fairly simple model for the broadline region, it does a pretty good job of actually matching the overall variability that we observe in the data. So here is the integrated H-beta light curve here. The blue points are the data, and the red and gray are the model. So it matches the overall variability, and it also matches the overall line profile shape. So here are 2 H-beta emission line profiles. The data is in blue and green, and the model fit is in red. So again, we're doing pretty well. Of course, one of the problems with this approach is that it does require fairly high-quality reverberation mapping data. So not just any reverberation mapping data. And reverberation mapping already takes, multiple months of observations to get a black hole mass. Thankfully, even though we've only done that for about 60 AGN, the reverberation map sample has allowed us to measure AGN black hole masses in much larger samples of objects, as you're probably all aware, through something called the radius-luminosity relationship. This relationship between the size of the broadline region and the luminosity of the AGN. And this correlation is quite tight, and it basically allows us to take a single spectrum and get a black hole mass measurement. Unfortunately, because it's based on the reverberation map sample, it carries around the same uncertainties and errors that you get from the reverberation mapped AGN masses, and this means that the dominant source of uncertainty is still the fact that we don't know what the broadline region is doing in these different objects. And it's even worse in the sense that the reverberation map sample is all sort of at low redshift, fairly low luminosity AGNs, and yet we're applying these single epoch recipes to larger samples of AGN at all redshifts and all luminosities. And so it would be really nice to know that we're not making some seriously bad assumptions when we do this. And so one of the things that we can do with the broadline region modeling approach is try to get reverberation mapping data for higher luminosity AGN and test and see whether the broadline region in these objects are different. And so we're currently working on acquiring this data in the next couple of years. We can also do a couple of other things in the meantime, and that is try to reduce the uncertainty in the average value of the F factor. And one way we can do this is just by putting together all of our independent measurements of F into one average value. And so, of course, we've only done this for 5 objects so far, but we have enough data to increase the sample by a factor of 4 or 5. So within the next year or two, we should be able to increase this substantially. The other thing we can look at is to see whether F is correlated with any other properties of the AGN or the broadline region that we may be able to measure. And unfortunately, at least for the 5 objects that I'm showing here, the only correlations we've found are between F and inclination angle and opening angle, both of which are very hard to measure. But we're looking into different correlations and what we can do about this in the future. So hopefully this method will not just be useful for specifically reverberation mapped AGNs, but also for the full AGN mass sample. So in conclusion, broadline region modeling allows us to do a couple cool things. It allows us to measure black hole masses more precisely. It gives us the first measurements of F for individual AGN, and it also allows us to constrain quantitatively the details of the broadline region structure. So we're working on analyzing a bunch more objects, and in the future we'll also be able to test different models for the broadline region because a lot of them exist in the literature, and we'd like to be able to figure out which ones are actually true. So that's it. Thank you.
Questions? Dan?
Can your Bayesian approach also be used to test whether the assumption that the initial change comes from the center of the black hole versus, say, somewhere out along the jet?
The initial change? That's a great, you mean the continuum flux?
Yeah, the driving.
That's a great question, and we're actually running into that limit in some new data that we've just acquired. So in this data that I've shown you, I've assumed that the continuum is just coming from a point at the center. But what we've actually found in a really high quality reverberation mapping campaign using HST for NGC 5548 is that the optical accretion disk, which is what we're using as a proxy for the ionizing photon flux, is actually sort of coincident with the inner parts of the broadline region. So this may end up being a problem depending on which line we use. Right now, we're really only able to see with a resolution of about 1 day. So anything that's smaller than that in these data, we can't really resolve. So depending on the data quality, we may be able to start look at more complicated continuum models.
So Misty Bentz, in her papers, they looked at other lines besides H-beta. One thing I heard that helium-2 is supposed to be a little bit puffier than hydrogen in general. It's coming from a puffier part of the disk. That's the standard lore. Do you have any sense that the different lines have different structures?
So I've only modeled H-beta so far, but there's no reason you couldn't model other lines. In fact, we're working on that right now. So hopefully within another year or two, I should have a much better answer for you.
Anna, those models where you had those clouds of points, they all had this white region in the middle, no clouds. Is that something you're putting in by hand, or the data is demanding a real empty region in the center?
It's actually demanding a real empty region in the center. Our radial model, I didn't go into too much detail. So it's a gamma distribution, but it has some offset, or is allowed to have some offset, as well as sort of an outer maximum radius. So it chooses to do that. It doesn't have to.
Does your inclination measurements match any other inclination from, say, a jet or the energy measured from Einstein or something like that?
That's a great question. So there is only one jet inclination angle measurement that I'm aware of in an AGN that we have actually or are in the process of modeling. And so far it looks like the agreement is very good. But I would love to have more objects like that because, one of the issues with this approach is that we're assuming some sort of model, and it would be really nice to know that it agrees with other data. Unfortunately, or fortunately, depending on how you look at it, a lot of the stuff we're getting out of this modeling is new. And so I've been looking for a lot of these examples of places where we can tie it to other work.
Why is it this approach needs better data than the standard approach?
The standard reverberation mapping approach.
That's one part of the standard.
So basically, what we're trying to do is resolve variations in the emission line profile as a function of time. Okay, that's where all of the power in this approach is coming from. And in traditional reverberation mapping, all you're doing is integrating the total line flux and making a line light curve and doing cross-correlation analysis between that and the continuum. So you're basically just using two light curves to get your time lag. And so instead, we're sort of doing the velocity resolved version of that.
Other questions? I got one.
Yeah.
So there's a lot of people who are curious about, inclinations of AGN and what other effects they have. It looks like you already have a small data set where that shows that you can use F for that. So has anybody correlated F against X-ray parameters like alpha OX or the spectral slope for these objects?
We have not yet, but we could. And sort of doing a better approach to that is one of the things I'd like to look at. So we've actually are in the final stages of analyzing 4 other objects which also lie on that relation. So we now actually have 9 points that lie on that correlation that I showed you. So I think at this point it's a good time to start looking at other correlations such as that.
Yeah, because you could also imagine that you might be able to use a spectral energy distribution to approximate F for objects where you can't do this.
Right, and that is one of the main goals of doing that sort of comparison. Yeah.
Okay, let's thank Anna again. Our further enlightenment will come from Maria Petropoulou, and she's going to talk to us about blazars as the astrophysical counterparts of the ice cube neutrinos.
Hello. First of all, I would like to say that I'm really glad to be here for the second year, and I'm going to share with you what I have been mostly working the past year as an Einstein Fellow. So this is the outline of my talk. So first of all, I would like to give a very short introduction and just to define what we are going to call high energy versus very high energy neutrinos. And I'm going to show you a very short overview of the current IceCube results regarding the very high energy neutrinos. And I would like just to say a few words about the production mechanisms of very high energy neutrinos. And then I'm going to, in the second part of my talk, focus on my research and especially try to show you or to convince you that there might be some connection between blazars, a class of radio loud active galactic nuclei, with the observed IceCube neutrinos. And Okay. Just to put things in context, so I just borrowed this plot that shows the neutrino flux, which is either measured or expected from different models as a function of the energy. And here you see a very wide energy range of neutrinos. Actually, we have measurements only for solar neutrinos, neutrinos from supernova, and here I'm going to show you later on the observations by IceCube. So what we call high-energy neutrinos is actually neutrinos with energies above 1 MeV up to a few TeV, and above that, the neutrinos are defined as very high-energy neutrinos. So solar neutrinos fall in the low-energy regime, and they are not interesting, at least for high-energy astrophysics. Okay, depending now on their energy, there are actually two types of detectors for detecting neutrinos. And for the very high energy neutrinos at least, there are the underwater or under ice Cherenkov light detectors. So in this kind of regime, there are actually currently two detectors. The Antares detector that has been constructed in the Mediterranean Sea, and the IceCube detector that is located at the South Pole. So IceCube detector is actually built within the ice, and it has 80 strings, and 86 strings actually, and these 86 strings have optical detectors for detecting the Cherenkov light radiation. So IceCube has announced the discovery of very high energy neutrinos of astrophysical origin in 2013. And for that reason, they have used the 3-year data of IceCube. So right now, they have at hand the 4-year data, and they presented some preliminary results of this 4-year data in the recent International Cosmic Ray Conference in the Netherlands this summer. So in this slide, I would like just to summarize the current status. And in the first plot here, you can see the number of events that IceCube has detected in the 4 years, which is now 54 events above 30 TeV, more or less, as a function of the energy of the neutrino that is actually deposited on the detector. This is not an actual measurement of the neutrino energy, but is a good equivalent. It's a minimum energy, a minimum value. So you can see here the events which are binned in energy bins, and with color you can see the histogram of the atmospheric neutrinos. And when we are talking about astrophysical neutrinos, these neutrinos here are considered to be a background. So again, we are not interested into that part, but we are interested in the neutrinos detected at higher energies that peak above the predictions that we have for the atmospheric neutrino fluxes. So what has changed since the first announcement of the discovery of very high energy neutrinos from IceCube is actually only the spectral slope of the neutrino spectrum, which is a little bit softer than it was announced a few years ago. And besides that, everything else remained the same. Here is again the galactic sky map in galactic coordinates of the detected events, which are shown here. And after doing a statistical analysis, IceCube has found no significant clustering. So what they have detected so far is consistent with an isotropic astrophysical flux of very high energy neutrinos. So let's go one step further, and let's consider let's talk about the possible mechanisms of producing very high energy neutrinos. And these are actually two. So you can produce neutrinos either with photohadronic interactions where you have relativistic protons interacting with photon fields, or you can have inelastic proton-proton collisions, and through the production again of pions that they decay into muons, then you can end up with muon and electron neutrinos. Depending now on the environment on the astrophysical sources that we are interested in, one process is more favorable than the other. So in environments like active galactic nuclei in the jets and in GRB jets, where the photon fields are more dense, this process tends to be more important than the proton-proton collisions. whereas proton-proton collisions may be important in star-forming galaxies or in galaxy groups and clusters, or when we talk about individual sources, when we have interaction-powered supernova or supernova remnants interacting with molecular clouds. These are very nice environments for proton-proton collisions to take place and produce neutrinos. So in the first year of my fellowship, actually I focused on the neutrino production from gamma ray bursts, and then I moved in the neutrino production from blazars, which are a subclass of active galactic nuclei. So let's go and focus on blazars. And actually you can imagine two ways of producing neutrinos in blazars. You can produce neutrinos internally within the relativistic jet of a blazar, under the assumption that this jet can actually accelerate both electrons and protons to very high energies. And the second way of producing neutrinos from blazars is from protons that can escape from the blazar jet or from the active galactic nucleus, and as it travels and it propagates in the intergalactic medium, it interacts with ambient photon fields, like the cosmic microwave background and the other photon fields. So these neutrinos that are produced during the propagation are usually called cosmogenic neutrinos. And this is not part of what I have been doing, so I'm going to talk mostly about the internally produced neutrino fluxes from blazars. Until so far, there have been no firm association of the detected ice cube neutrinos with some astrophysical source or some class of sources. And so people have been trying to find possible astrophysical counterparts of these neutrinos. One recent work was by Padovani and Resconi in 2014, where they took the 3-year data of IceCube, which consists of 35 events, and they have tried to correlate these 35 events with gamma ray astrophysical sources. And for that reason, they used all-sky gamma ray catalogs in the GeV and TeV gamma rays, like you can see them here. And they focused only in neutrino events that had a median angular error less than 20 degrees, which in terms of astronomy and astrophysics is huge, but in terms of neutrino astronomy, it's quite reasonable. So here is, for example, a sky map again, and you can see some of the neutrino events and the median angular error size. Moreover, instead of doing just a correlation in positions, they added another energetic constraint into their sample. And this can be understood by looking in this figure. This is a nu-f-nu plot, so luminosity versus energy. And here is the flux of the detected neutrino event. What you can see with the points are actually the photon fluxes, the GeV and TeV photon fluxes of the 3 of probable counterparts of that neutrino event. So the authors actually said that if the extrapolated gamma ray neutrino flux, let's see the blue points here, lies much below the 1 sigma error bar of the neutrino event, this is not considered as a probable counterpart, so is discarded. After doing this energetic constraint, after applying this energetic constraint, from the 35 events, they moved down to only these events and having the most probable astrophysical counterparts, these. So as you can see, most of them are BLX, so blazars with no or very weak optical lines, and a few, and actually only 2 pulsar wind nebulae. So as you can imagine, this work is observationally driven and it is model independent. So what I wanted to do next is to take these astrophysical counterparts, which are probable astrophysical counterparts, and see and test what is a model prediction about the neutrino fluxes. So in order to do that, I have applied a leptohadronic model to model the emission, the multi-wavelength emission of these blazars, and calculate the neutrino fluxes, and compare, of course, with the neutrino fluxes of the observed events. So here are two examples of a multi-wavelength spectrum of Markarian 421 and for another blazar, which is located at a much larger redshift than Markarian. And in order to model the multi-wavelength SED, I tried to use mostly simultaneous data because it's really important to have a multi-wavelength coverage using almost or quasi-simultaneous data. As you can see in both cases, the leptohadronic model can explain pretty good the SEDs, as you can see here. And here you can see with different types of lines the various components of emission. I don't want to go to the details, so let's focus now in the neutrino emission that is predicted. In the case of Markarian 421, you can see this red dotted line, which is the all-flavor neutrino flux predicted by the model. And you can see that it's pretty close to the 1 sigma error bar of the neutrino event number 9. However, if you go to the other blazar that we modeled, the neutrino flux is much below the 1 sigma error bar at the specific energy beam. So what is also interesting to see is that in that case, the peak neutrino flux and the observed gamma ray flux are more or less at the same level, whereas in this case, the peak neutrino flux is much lower than the observed gamma ray flux. So this ratio of neutrino versus observed gamma ray flux is really interesting from for what I'm going to say in the next slide. And just to say a few words more, in that case where the peak neutrino flux is much lower than the gamma ray flux, this gives us an indirect way of saying that the gamma rays actually seen from that blazar have a leptonic origin. So they are the result of synchrotron self-Compton, and so any hadronic component or contribution to the gamma ray flux is suppressed. Whereas in this case, the gamma ray emission is mostly explained by hadronic processes. So moving from individual BLX sources, what was the following step to do is to model the neutrino flux from the whole population of BLX. And in order to do so, we need two actually things. First of all, what we did is that we went and from the individual sources that we modeled, we tried to encode the information into only very two simple equations for the neutrino spectrum. So what we did is that we modeled the neutrino spectrum, trying to include only observable quantities like the observed gamma ray flux above density V, and the peak neutrino energy of this spectrum, which depends on the redshift of the source, the Doppler factor, which is going to be a model parameter, and the observed synchrotron, peak synchrotron frequency. And you can see here that the only tunable parameter is this ratio y that I showed you before. So we let this y parameter to be the only free parameter of the model. So what we need next in order to calculate the neutrino emission from the whole class of BLX is we need a model for their evolution with respect to redshift. So we need to know their gamma ray luminosity with respect to redshift and so on. Instead of using a prescription for that, we use the Monte Carlo simulation that simulates the blazar evolution. And it has been recently proposed by Giomi and Padovani, and it is based on the radioluminosity function of blazars and not on the X-ray luminosity functions of blazars. So this is the important thing. So what we did is that in every source in the simulation that has a specific redshift, a specific gamma ray luminosity, and so on, we attributed a neutrino spectrum given by these two equations. Then we summed up the neutrino emission from all the simulated BLX, and we came up with this curve. So this is the new plot. Again, luminosity, neutrino luminosity versus energy in PeV units. These are the IceCube data, the 1 sigma and 3 sigma upper limits, and this is what we get from the neutrino emission from the whole population of BLX. And you can see that it can explain the 1 and 2 PeV neutrino events, but it cannot explain at all the sub-PeV events. So BLX may be responsible for this neutrino emission, And this is something to be actually falsified or not in the next few years. If IceCube doesn't detect anything, so in the next few years, these upper limits are going to go down. So this is going to constrain the Y parameters, the only tunable parameter that we had in the model. So a smaller Y parameter is going to bring this curve down and consistent with a possible no detection. And this will mean that the hadronic contribution in blazars is not as important as we thought to be. And here just to make a comment, because we talked about neutrino emission from individual BLX and neutrino emission from the whole population, so the diffuse emission from BLX. It was not clear to me at first how both are combined. I mean, if you have the neutrino emission, if you have a diffuse emission from a source, from a population of sources, how would the signal from a point source look into the same plot? So here is an example where we show again the same nu plot, and instead of showing you the average of the Monte Carlo simulations, I show you individual simulation runs. So you can see a bunch of lines here. It doesn't matter, you cannot distinguish between them. But you can see that in some simulations you see a bump, and then you can follow the other emission. So this kind of bump in the neutrino flux is produced artificially by an outlier source in the Monte Carlo simulation. And outlier meaning in the sense that it has it is a single source with a relatively high gamma ray flux and therefore neutrino flux. The point is that although this is it is an artifact of the Monte Carlo simulation, it actually mimics the neutrino signal from a point source. So this would look like a point source emitting in this energy range plus the diffuse emission from the BLX. And interestingly, here is the neutrino event that was the counterpart of Marcaria 421, the blazer. And I'm just going to close with this slide and just to see the big picture right now, because we are actually at the period where we talk about the neutrino background as well. So up to now, we were familiar with extragalactic backgrounds in the radio, the X-rays, and the gamma ray regime. And here are the measurements of the Fermi telescope in the gamma ray regime. So now we can complete this picture by putting into the same plot, into the same units, the IceCube data. And you can see that there's a very nice power law here connecting the gamma ray background and the neutrino background. So from the simulation, we are able to predict the neutrino emission from BLX, which are shown with these two curves for two different values of the Y parameter that I was talking before. And we can actually compute what is the gamma ray neutrino emission, the gamma ray emission from the blazars in the simulation. And you can see that the blazars above 100 GeV, they can explain mostly the extragalactic gamma ray background measured by Fermi. There is a lag here at lower energies, and at the same time, there is a lag here at sub-PV neutrinos. So I would like just to close by saying that maybe blazars can be maybe a probable let's say, source class for explaining the very high energy neutrino events as well as the high energy gamma ray background, but we need something else in order to complete this picture here. So I will leave my summary here, and I would like to thank you.
Question from Maria.
Matching the individual sources, it seemed that the point was systematically on the left with respect to the peak of your predicted bump. You have wiggle room there, or is this a problem? But the data point for the individual source was always maybe factor 5, lower energies with respect to the position of the predicted peak.
Yeah. So you're talking about...
No, all the way back. The individual sources, Marcaria 421.
Yeah, so here in the top panel. Yeah, it's the same.
Yeah, maybe it's the same thing.
It's the same thing.
Okay. Yeah.
So here. Yeah, the fact that the model predicts a peak neutrino flux at higher energies, it is, I mean, you cannot fine-tune it because it actually depends on the peak frequency of the low energy band. But the fact is that even this is a neutrino event which is measured by IceCube, but you must have in mind that the neutrino energy is just the lower limit because these neutrinos are very high energies, so they have a lower energy. This is a lower limit on their energy. Yeah.
So there should be an arrow on the energy instead of an error bar?
Yeah, in principle, yes.
Other questions?
You said Y was the only tunable parameter, but isn't the evolution of the DLX must be very uncertain at larger redshifts?
Yeah, so the thing is that by using this kind of Monte Carlo simulation for the evolution, actually what the simulation does is that it takes different kind of sources, following only the radioluminosity function and evolution, which is better constrained for blazars. And following that, they wanted to satisfy various gamma ray constraints and X-ray constraints. So the simulation may follow blazars up to a redshift of 1.5. So after that.
Any other questions?
But at least, but at least in this series of papers, they have made a series of comparisons of the Monte Carlo simulation results regarding the X-ray luminosity function and the gamma ray luminosity measurements from the simulation to the data. And they found a good comparison. So, yeah.
Other questions? So let's thank Maria then. The next talk is Oleg Sadovsky will talk about simulations of stars eaten up by supermassive black holes.
Thank you. I'm Oleg Sadovsky, and I will talk about tidal disruption events. So I ask for two things: understanding, because it's a new field for me, and constructive comments, please. Okay. So this is the outline. The outline is very simple. I start from introduction, and the introduction is justified because this is the first out of a couple talks about tidal disruption events. So I'm allowed to say very basic things about tidal disruption events. So whenever a star gets too close to a supermassive black hole, its own gravitational field is overcome by the gravitational field of the black hole, and it is disrupted. And whenever the star gets too close to the supermassive black hole, then very close to the supermassive black hole, then the relativistic precession can be very important, and the stream of debris coming back to the black hole can actually self-interact with itself. In the most likely case of a parabolic approach to the black hole, roughly half of the debris returns to the black hole and the rest is ejected into the interstellar medium. And we do observe actually such events. We observe them mostly in optical or UV. There are also a couple of events which were observed in X-rays, which are associated with the jet emission. And the observed luminosities can be quite high. So the disruption events are quite exciting, and it is exciting also to study them. This is the standard picture of what happens with the star after it gets disrupted. Now we no longer talk about the star, we talk about the debris of the star. Half of it is bound, half of the debris is unbound, and the bound debris comes back to the black hole with this canonical, is expected to come back towards the black hole with this canonical time dependence. However, the return rate of the debris towards the supermassive black hole is not actually the accretion rate, because this debris is still accretion rate through the black hole horizon. This is because the debris still has some angular momentum and it does not directly hit the horizon. One has to get rid of this angular momentum to make the black hole accrete. And it is possible that this debris returning back to the black hole forms an accretion disk, and only in this accretion disk we get magnetically induced turbulence, which provides effective viscosity, which allows for the extraction of angular momentum and the accretion finally takes place. However, if we look just at the numbers and we look at at what rate the debris comes back to the black hole, then we get that at the initial stage, this accretion rate is quite likely to exceed the Eddington number. And there are a couple of puzzles in the field of tidal disruption events. One, which I have just described, is how the gas makes to the black hole. The other one is the question of the tidal disruption energetics. So the typical mass of a disrupted star is more or less a solar mass. Half of it makes its way on the black hole. If we assume that that mass is accreted through a thin, radiatively efficient standard accretion disk, then we expect that 10% of the rest mass energy of that accreted mass will go into the radiation. So we can estimate that the predicted emitted energy by such an object is of the order of 10 to 52 ergs. However, if we integrate the observed fluxes, if we calculate the total luminosity of the observed events, we get a number which is 1 or 2 orders of magnitude lower. So the open question is why tidal disruption events are actually not radiatively efficient. What makes them so dim? So I approached these problems by combining SPH method with the GR radiative MHD approach. The SPH part was performed by my collaborator Emilio Tejeda, who comes from Stockholm, where he worked with Stefan Rosvog. And this part is, I was in charge of that part, and I will give you a couple of details. I don't know too much details of the SPH part, so I just cite what people say about it. So this is based on the Stefan's Rosvog code, and recently updated by including the relativistic potential of Tejeda and Rosvog, which allows to more precisely study the relativistic precession, which is an important factor in close encounters. I can give you more details about the part I'm in charge of, which is this general relativistic radiation magnetohydrodynamics. The code which I developed is called Coral, and it couples magnetohydrodynamics with a simplified radiation transfer under the M1 closure. It is written in general relativity in a fixed spacetime of a black hole, and it can perform global simulations of gas in the vicinity of the black hole. And because it is written in GR, it can actually, the inner edge can be actually inside the black hole, and we can precisely trace the rate at which gas crosses the black hole horizon. And this is an example of what I did before. So I come from the field where I study accretion flows, irregular accretion flows. And this is an example of a simulation of accreting gas with mildly super Eddington accretion rate on a black hole. The left-hand side shows what happens with gas density. This is the poloidal plane. This is sliced through the equatorial plane. The right-hand side shows what happens with the radiation. Radiation, because this is optically thick, radiation more or less follows the gas. However, some significant fraction is extracted as well. So it seems natural that we can apply similar methods to tidal disruption events, because they are expected to produce, at least initially, super critical accretion flows. And this is what I did. However, there are some limitations that we should be aware of before we simply jump into this field. So the simulations, GR MHD simulations which I perform, have some limits. First of all, we do want to resolve the black hole horizon, which makes the innermost cells quite small, which makes the time steps very short, which limits the total duration of a simulation that we can afford. Another thing is that the resolution is finite, and we don't want to go into too high resolution because it will again limit the time step. So we can't resolve arbitrarily thin streams of debris. One has to study rather disruptions which are not so thin. So this kind of suggests that to get a good, well-behaved disruption, which we can evolve into this in the framework of general relativistic MHD, one would rather simulate elliptical orbit, which will be like confined to relatively limited range of radii. And also the impact parameter should be large, which means that the star actually penetrates very close the space-time and gets close to the black hole, which means that it self-interacts efficiently and the debris will not fly away to large radii. And also, we want relatively small mass ratio between the black hole and the star, so that the star is actually not so thin as it could be in more relativistic scenarios. Okay, and this is the simulation setup which we performed. So we chose the black hole mass of 10 to 5 solar masses, stellar mass of, we chose a red dwarf of 10% solar masses. The black hole is non-rotating, and we chose an elliptical orbit with eccentricity 0.97. The impact parameter is 10, which corresponds to the pericentral radius, just 7 gravitational radii from the black hole. And this is the output of the SPH simulation we performed. The star approaches as a star on that orbit, but then it is disrupted and this kind of pancake forms. Because it was an elliptical orbit, actually the debris is bound, totally bound. Even the outermost section of the debris is bound and will ultimately come back to the black hole. And then we take the stage just before the debris starts to approach the black hole and translate it onto the fixed grid of the Coral code. And this is what it exactly looks like. So this is the last stage of the SPH simulation, and we translate one-to-one this gas to the Coral fixed grid. And you see the velocity vectors, even although this points out this gas, as I just pointed out, is bound and will ultimately come back. And then what we do, we run the simulation, right? And we perform two simulations, one with pure hydrodynamics with no magnetic field, and another one with the star kind of arbitrarily magnetized at very low level to see how the magnetic field will evolve with time. Initially, we had the idea of performing a radiative simulation as well. The code is capable of that. However, this setup will result in such high accretion rates, which correspond to so optically thick gas that actually the whole domain of the simulation would be optically thick, and the radiation actually would not tell us, the radiation part would tell us little, because to really find the luminosity of a source, we need to resolve the photosphere, and that was not designed properly for that. Here are the parameters of the simulations. Inner edge is inside the black hole horizon, outer edge is at 1000 gravitational radii, relatively modest resolution, and quite long duration of the simulation, 100,000 gravitational times. Okay, so this is the output of the hydro simulation. Here we are looking at the slice of at the equatorial plane. This is the slice of the in the poloidal plane across this dashed line. The plot shows the accretion rate over time, and the accretion rate actually reaches 10,000, not 100,000, 10,000 times Eddington accretion rate, which is reasonable because this is a regular star, but it actually accretes in a very short time, because this mass is accreted in a very short time because of the fact that the counter is very close, so that almost 1% of the solar mass is accreted in the time of 10 hours. Okay, so this is what happens. You initially saw that the star was disrupted, some gas was ejected along radial direction, then the gas started to circularize, and we end up with this quasi-steady state with a disk which is turbulent, turbulent because it is affected by most likely Papaloisa-Pringle instability, which is very thick, and actually we do see some significant accretion. Where do this accretion come from? This is the plot showing the accretion rate over time, and as you see, you can already anticipate that there will be a little difference between, hardly any difference between the hydro run and the magneto-hydrodynamical run, and I will explain this later. However, you see that the accretion rate is quite large, can exceed thousands of Eddington accretion rate. This plot shows the amount of gas which is contained in the domain and the amount of gas accreted by the black hole, which is the integral of this curve. So there are two things to take out of it. In the late stage, you see that the derivative of the slope of one equals minus the slope of the other, which means that the gas is lost only on the black hole. However, in the initial stage, the amount of mass in the domain is actually lost quicker than the gas is accreted on the black hole, which means that gas must be escaping through the outer boundary and is lost from the simulation. How is this possible that the gas is lost in such an amount? We will come to that in the next slide. Before we look at the self-crossing, the innermost section, the innermost part of the flow where the gas is self-crossing itself. So because of this relativistic precession, the gas is not following this orbit that it would like to have in the Newtonian potential, but actually it is bent towards itself and self-crosses strongly, causing a self-crossing shock, which results in high temperature and increased entropy. And there is hardly any actually shock seen in this nozzle part. And the reason for that is that nozzle is actually quite thick, and it is thick because the encounter that this disruption is very close, which means that actually the velocity vectors of the gas are spread over spatial dimensions. They are not actually exactly pointing towards this pericenter where one would expect very thin pancake shaped nozzle. So not much happens here, but quite a lot happens in this region. The gas is shocked up, and some part of it is heated up so much that it actually escapes from the domain. These are the plots showing the Bernoulli number. So the red colors correspond to the gas which is unbound. The blue colors correspond to the gas which is bound, which will stay there, which will never escape to infinity. This is the relatively early stage of the simulation. This is a later stage, and finally this is this quasi-steady disk-like stage of the simulation. So you see that initially plenty of gas is ejected from the system. It becomes unbound when it is shocked and heated in this innermost region, and this is the gas which leaves the domain. Later on, actually this ejection process is no longer so efficient, and we start seeing more and more bound gas in the simulation domain, and we end up with an accretion disk which is totally bound, or accreting, or actually equilibrium structure which is bound. And when you compare the binding energy of the more or less initial star with the binding energy of the torus that we end up with, you see that it became more bound, which is actually the reason why we were able to eject so much mass in the early stages. Okay, and this is another plot showing what happens with the accretion. So we take a slice over at radius 100, and we measure accretion rate through the sphere with radius 100. We initially see that the cloud itself, the star itself, crosses the surface. This is this peak of inflow. Later on, this gas comes back. Not all of it escapes. The other part forms the quasi-steady structure, and only a relatively small fraction of that mass crossing the sphere is actually accreted on the black hole. And where is it accreted from? So this is initially it's reasonable to expect that this gas crossing the black hole horizon will come from angular momentum cancellation. There is plenty of interaction, plenty of self-crossing. Some gas simply makes it to the black hole. However, later on, we have this quasi-steady structure. And this is the average structure. This is the average structure of the density, and we see that this torus is quite thick, and the vectors show the velocity. The thickness of the velocity shows the velocity, reflect the velocity magnitude, and we actually see that there is hardly any, on average, velocity in the bulk of the torus. Actually, gas is falling down along the edge of the torus and in the poloidal plane, near the axis. When we plot the accretion rate, we see that actually, once again, there is little accretion deep in the disk. The gas is actually falling down along the edge of the disk, and this is where the accretion comes from. What is this gas? This is the gas which was ejected out of the plane initially in the early stage of the simulation, but which was bound, so it was not able to escape to infinity. It is gradually falling down on the black hole, and it provides most of the accretion in the late stage. So what does this equilibrium structure look like? It is actually almost zero Bernoulli number equilibrium torus when compared to standard accretion disks. This is what recently has been proposed and called zebras, zero Bernoulli accretion. And also angular momentum of the torus which is formed is very, very, very low. So it is definitely not a standard accreting structure, and this explains why there's hardly an accretion dip in the structure, in the disk. When we look at the magnetic field, in the case of the other simulation, where the magnetic field was included and initiated as a very weak magnetic field of the initial star, we see that over time the magnetic field builds up in the disk. This is the magnetic pressure to gas pressure ratio as a function of radius. We see that because of differential rotation, magnetic field lines are stretched, they increase in magnitude. But what we see is that actually they saturate at quite low level, because it is a completely different structure than a regular standard accretion disk, where you would expect this quantity to go to high numbers. Actually, we see that it saturates at the level of 10 to minus 3 and does not want to go up with time. And this explains why we do not see in the second simulation significant magnetically induced turbulence. This magnetic field never gets strong enough for the magnetorotational instability to be resolved under the resolution that we have. However, even if the resolution was infinite, we would not expect very strong very strong effective viscosity, because the level at which the magnetic field saturates is quite lower than in the standard disk cases. This is the summary slide. We have simulated a red dwarf disrupted by a black hole in a very close encounter. Strong relativistic precession makes the self-intersection violent. The self-intersection results in plenty of unbound gas released in the initial phase. However, later on the gas settles down in this quasi-disk with low angular momentum and marginally bound. Well, bound, but very close to zero Bernoulli number. There is hardly any accretion in the torus. The accretion rate in the late stage comes actually from the debris falling down on the black hole. And the magnetized star brings magnetic field, which builds up over time, but in the setup that we studied, this magnetic field did not grow to sufficiently high numbers to resolve MRI. However, still one can propose that even if it was, the effective viscosity would not be huge. And finally, what's the luminosity of this system? The luminosity of this system would be really low, although this is like thousands of Eddington accretion rate. All the stuff that we see here is optically thick. It's so optically thick that it will not let the photons leave the system. All the photons which would be contained in the simulation would be advected on the black hole. Only far away, there would be the photosphere where the photons can actually leave the system and go to the observer. So this would be very radiatively inefficient, and in some sense it may address this question of TD, of tidal disruption events energetics. There's an open question, probably what luminosity would correspond to this initial violent stage of ejection of unbound gas, but this has to be carefully investigated and probably in a separate project. Thank you. I'm done.
Questions for Oleg? Yeah.
I have two questions. You talked about this problem with the observed energy not equaling the gravitational energy you've got available, but your calculations showed that you've got large outflows.
Yes.
And then don't you then have an analogy with galactic microquasars like SS433, where we know an enormous amount of the energy is put into the kinetic energy of the ejected at relativistic speeds material. And isn't that exactly what you're showing here? So that will help resolve that problem.
You're absolutely right. You're absolutely right. So I did not measure that, but this initial outflow probably will carry significant amount of kinetic energy. And that energy will definitely decrease the amount of energy that we expect in radiation.
Right.
So in some sense, yes, it also helps to explain this puzzle.
My second one was, can you produce predicted light curves out of your simulations to compare?
Unfortunately not. The reason for that is that this particular simulation is so optically thick that the photosphere is at the boundary of the computational domain. And really to get the light, we need to resolve the photosphere. So I will think hard, hopefully with the help of others, how to set a tidal disruption event in such a way that it still can be evolved in such a way, but it will result in more optically thin system which will give the photosphere.
But at the very least, can you compare your timescales of what you're doing with observed actual?
Well, so the timescales are very short because this is a very close encounter. It's like an unlike encounter, which is convenient for numerical reasons. But it's not a good example for the disruption events that we are actually observing, which are most likely more parabolic and which take longer, which take weeks or months. This took only half a day.
So how large a photosphere are we talking?
That's a good and difficult question. Well, I would guess tens of thousands of radiation or radii. This is, but don't take me for granted. What I'm saying for granted.
Yeah, but very impressive stuff. What's the total mass that is ejected from the shocks at the self-intersection point? Is it a majority of the star's mass, a smaller fraction?
Okay, so at the end we accrete 20% by the black hole, but we end up only with 50%, so 30% was ejected out of the movie.
Thanks.
Other questions? Okay, I just wanted to make two small announcements before we have coffee. One is that if there are people that want to collaborate on taxis to the airport, you might want to just meet over here right now, just to see if there are other people at a similar time. And also, we generally post the presentations on the website for the community, and so hopefully everybody's willing to do that. You don't have to, but it would be great if we could do that. And so we have a bunch of your presentations. If you feel like this version shouldn't go on the web, then you can provide us with another version. So I'll be pestering you about that after the symposium. Okay, let's thank Oleg and all our speakers.
Good morning. On to the next session. On to the next session. I'm Nancy Evans, and I just commented to Paul. It's a delight to come and enjoy the science and not worry about the typos in the program. I used to be the fellowship coordinator, and needless to say, it's a fantastic experience to hear the people that are going to carry the field forward in the next few years. These are always impressive. I mostly work on CEPIs, and particularly their binary particles, and I've had a number of interesting conversations with the second speaker in the program, who will be upcoming. So the first speaker for this session is Yanfen Zhang, who did his graduate work at Princeton and is now at SAO.
Yes.
And the title is How Do Massive Stars Get Their Super Eddington Luminosity?
Thank you.
Flash some warnings to you.
Okay. So I'm the third year here, and the last year I decided to talk about something totally different compared to what I studied before. So I think this is a way to thank the Einstein. I think because of the Einstein, I have this option to do something that I want. So the topic is how do massive stars get their super Eddington luminosity. I think it sounds like a very old topic because like star structures, we have studied that for many years. For example, we have studied the sun to death basically. And the star basically just a tool that we use in the astronomy community. For example, we just heard the accident tour that we just throw stars to the black holes and see what happens. But it turned out that once I started the project, I realized that so many things we don't know about stars, particularly the massive stars. And I will show you what are the issues. So this is the work I did with Mattel and Lars in Santa Barbara and Elliot in Berkeley and also Oma in University California in Santa Barbara. So this is just a very brief introduction of why the massive stars are interesting. As I said, that because interesting, that is very useful for many different things. But massive star, this is just one picture that what massive star can do. For example, they can explode and drive very powerful outflows, and people just use the radiation from the massive stars. That is the radiation for feedback, like to study the gas structures and the evolutions. And also in the early universe, the radiation from the massive stars is also an important thought for the reorganization of the universe. Of course, when the massive stars die, they are basically the progenitors for like compact objects like the neutron stars and the black holes. Of course, right now the hot topic is that the binary evolution, most of massive stars also observed in binaries, and binary evolution also play an important role for the evolution of massive stars. But I just feel the people jump too much, because even for single massive stars, we still do not understand what are the structures and how they evolve. And the simple and why, particularly the massive stars, have a lot of puzzles, particularly because they are a very strong luminosity. This is basically when people study the evolution of the stars. This is basically you plot the luminosity of the stars and the mass. This is the case for the stars at the main sequence. This is the case for stars that evolved after the main sequence. And this is basically all the study people done for basically 1D stellar evolution studies. And they basically show that if you look at the total luminosity coming out of stars and in a function of mass, you'll see that if you just consider the Einstein limit, this Einstein limit is basically defined in terms of electron scattering. And you will see that particularly for the evolved stars, you'll see that the luminosity coming out of the stars is pretty close to the Einstein limit in terms of electron scattering. Like for the evolved stars can get to like 75% of the electron scattering. And this is even worse if you consider the real opacity that can exist in the envelope of massive stars. So the massive stars do not just have a hydrogen, there are more metals. So this is the opacity table as a function of temperature for different fixed density. So this level is basically electron scattering, like 0.32 or 0.34 for solar metallicity. And what you see that, by the way, this table is basically people get from experiment actually. What you see that there is the one opacity bump around like 2 times 25K, which is caused by ions actually. And then there are more opacity bump like by heliums and the hydrogen minors when you go to low temperatures. And you can see that the opacity caused by ions is a factor of few larger than the value of the electron scattering opacity. And of course, this depends on the metallicity. If you have larger metallicity, the opacity bump will be larger. So then the serious question happens, right? If we just take the same luminosity coming from the massive stars as calculated by the 1D stellar evolution structures, and the radiation force is basically flux times the opacity. If you enhance the opacity, that is by a factor of few, and we know that even for electron scattering, the luminosity is already pretty close to the end limit. And when you consider the opacity caused by the metals, the massive stars, the radiation force will be much larger than the gravitational force. And then how the massive stars can hold their structures without blowing away the photons. So that is basically the puzzles people study the structure of the massive stars. So more specifically, so this is basically an example from MESA. So MESA is basically a 1D stellar evolution code. And you can see a beautiful structure evolution check on the HR diagrams for like 15 solar massive stars up to like 70 massive stars. But I will say that if I first see this, it looks very beautiful. It seems that the evolution of massive star problem is solved. But if you look into the details, like how they do this, there are really a lot of questions that you should, when you see this picture, you should put a lot of question mark basically in the plot. The simple explanation is that if you all those 1D stellar evolution structures, you construct basically a hydrostatic 1D spherical symmetric solutions. And if the radiation that coming out of the region where the ion opacity is located is larger than the gravitational force, and you try to construct hydrostatic structures, what you will find is that you need basically the radiation force is larger than the gravity force, so you need additional gas pressure to hold the mass. And that's how they construct 1D structures. And that is expressed in these hydrostatic equations. What that means that your gas pressure will actually increase with the radius at the location where the ion opacity is located. And because the temperature always decreases with the height based on the diffusion equation, that means that the density will actually increase with the distance. That is basically the long puzzle for like density inversion if your luminosity is the superantenna at the ion opacity regions. But we know that from the study of the sun that the radiation, not just diffusion radiation, there's the convection. The simple criterion is that if you calculate the entropy when the density inversion happens, this actually satisfies the convection criterions. So this really comes to the specific question that how convection works in the radiation dominant regimes. So that is really the fundamental puzzle that if you have this superabundant, strongly radiation pressure dominant case around the ion opacity regions, how much convection you can get. Because like, for example, when you study the structural suns, the amount of convection flux basically determines the structures of the stars. And this is a similar issue as in massive stars. And as you know that although we have studied the convection for like maybe 60 years or more, the best theory we have is basically missing length theory. And the missing length theory is really, there's really a free parameter, basically it's also called alpha. And that's how, by the way, that's how they can calculate this stellar evolution check, because they just use the missing length theory and they use alpha as the free parameter. They tune the parameters as much as they want so they can evolve the stellar structures in the HR diagrams. So the question is that can we really understand the convection in the radiation dome regimes from first principle so that the mixing length theory is no longer a free parameter, or whether it works in the radiation dome regimes. The second picture that people proposed for a long time to pass the superabundant luminosity, the so-called Pelosi effect. So this is the basic picture that is not, that may be what 1D stellar evolution structure assume that it's spherical symmetric. So all the gas in some radius, for example, will fill the same amount of flux. But maybe the 3D, the star is inhomogeneous. Maybe in the envelope we have a very large density fluctuations, such that most of the photons will actually go through low density regions. So what that means that if you calculate the density weighted radiation acceleration, that means if you take the opacity times the flux at each location times the density and divide by the average density, that will be much smaller than what you will naively think by just calculating the average opacity times the flux. So this is a way that you can reduce the total radiation acceleration on the mass, but at the same time that you can get all the photons out. Of course, this is just idea, so we want to calculate and see how much effect that can exist and on what condition that can happen. So this is basically the parameters that we take. We take the one MESA stellar evolution studies for two different massive stars, one for 40 solar massive stars after the main sequence, and two additional simulations for 80 solar massive stars, one at the main sequence and one after the main sequence. And then what we do is that we put the typical conditions for the structural stars in this local box. So what we do is that we apply the flux, which is taken from the MESA calculations. That is the flux that you will expect from the center of the star. And then you put the gravity here. And initially, we put also the opacity table. And initially, the radiation acceleration is larger, is the superabundant near the ion opacity regions. So you get the density inversion. And then you run the simulations. So these simulations we run in the radiation hydro simulations. So we solve the radiation transfer equation self-consistently without any ad hoc assumptions. So that means we use the so-called variable and tensor method. That turned out to be critical to study the Pelosi effect. For example, that how much the photons will go through the inhomogeneity of the envelope. So these are just two examples. So the critical numbers that it turns out is that there's one parameter, which is the ratio between the speed of light and isothermal sound speed at the ion opacity regions. And another important parameter is the optical depth per pressure scale height at the ion opacity regions. So I have two examples. One example is that the actual optical depth at the ion opacity region is much larger than the critical number. And the other case is that the actual optical depth is much smaller than the critical number. Because the ion opacity is basically roughly always around 2 times 10 to 5K. So this ratio is roughly the same. But as you can see, the evolution is quite different. First of all, what you see is that the initial density inversion, as you will expect from the 1D structure, is basically unstable. It's broken away basically because of the convection. And you can see that in this regime, that the actual optical depth is very large. You basically get a very slow subsonic convection. While in the right case, when the optical depth is small, you get very turbulent large density fluctuations, and the whole envelope undergo vertical oscillations. I will skip this. So as I said, that the best theory we have for convection is the so-called missing length theory. So what we do that in the case when you see the efficient convection, and then we can calculate the amount of convective flux from our simulations directly, and then we can compare with the mixing length theory. And because this is a calculation from simulations, so this is a way we can actually calibrate the free alpha parameters in the mixing length theory. And first of all, in the efficient convection case, it seems that the mixing length theory actually can describe the amount of convection I think relatively good. But with the mixing parameter, it's only like 0.5, which is actually smaller than what people usually assume. And for the inefficient convection case, which is the case that the low optical depth per pressure scale height at the envelope is much smaller than the critical numbers, what you see here is that this is the vertical velocity of the envelope and the history. What you see that you undergo very large amplitude oscillations of the whole envelope with a period like a few hours, which is actually pretty close to some periodical variability for massive stars. And what you see, the left panel, just snapshot, you see that the envelope with very large density fluctuations. This is just a movie to show what the oscillation of the envelope look like. I will skip that. And the convection flux is very small in this case. So I want to jump to this very important point that when the convection is inefficient, the optical depth is more than the critical numbers. You get these large density fluctuations. And the left panel is just a horizontal snapshot of density. And the bottom is the horizontal snapshot of the radiation flux. And what you see, you do see that most of the flux are coming from the low density regions, while the amount of flux coming from the high density region is smaller. And this is exactly the so-called the porosity effect. And the effect of this is that if you calculate the density weighted radiation acceleration, as I said, it is smaller than the volume average radiation acceleration as we would expect based on the 1D static structures. But it's not enough. The radiation acceleration, even with this density fluctuation, is still a little bit larger than the gravitational acceleration. That's why you can see the vertical oscillations of the envelope. So skip that. So I just put a summary here. I think based on the radiation hydro self-consistent simulations, we're the first time that we can calibrate actually convection in the radiation dome regimes. We can tell you what alpha you can use. And also we can have a basically very simple criterion that if the optical depth per pressure scale height and also the critical numbers, if that is smaller, you can get inefficient convection, and your envelope can undergo very large amplitude oscillations. And also, this also have a very important implication that the inefficient convection regimes, your turbulence caused by convection is basically supersonic compared with the isotomal sound speed. And that also have a lot of implications when people study, for example, the rotation of massive stars, and also people study, for example, the size of massive stars and the evolution of the massive stars. That will be the study in the future. Okay, thank you.
Questions?
These large amplitude oscillations, what would be the typical size of this oscillating features? Should one not rather expect that when integrated over the stellar surface, they will cancel out and there will be no strong effect?
Yeah, so basically that is basically a question of what is the correlation length of the typical structures. That is basically determined by the local pressure scale height. And all the simulation box is basically is already resolved the local pressure scale height. So you can imagine if you do a full star structures, each video will basically do very similar things if you have the same amount of flux coming out, as long as you resolve the correlation length. In each other part, if you have multiple locations that are not causally connected, they may not just do the similar thing instead of canceling out.
Very
Okay.
interesting topic.
Thank you.
Thank you. And the next speaker is Maxwell Moe, who did his graduate work here at Harvard and is now moved to the University of Arizona. And his title is How I Learned to Stop Worrying and Love Eclipse Fire.
Which one?
Forward, backwards, and then laser.
Great. Okay, we've all seen Dr. Strangelove, right? Raise your hand. Oh, that's a little poor showing here. So as Nancy said, I defended my thesis here in July, so I'm just going to be sharing a hodgepodge of various results from my thesis. I want to thank Roseanne DeStefano right here, my thesis advisor. But there are a couple of new results I wanted to share. The first of which is the birth of our son, Malachi Regulus Moe. He's just turned 6 weeks old. And his middle name, Regulus, is from Alpha Leonis, the heart of the lion. It was one of the bright stars that maritime navigators used to navigate their ships, hence the nautical-themed clothes. But Regulus itself is a very interesting system. It's a rapidly rotating B-type main sequence star, the verge of breakup. It's a single-line spectroscopic binary, so we know it has a companion, but we don't know what it is. It could be a K-dwarf companion, where the rapid rotation of the B-type star is just a natural development of massive stars. The more plausible scenario, in my opinion, is that it's a white dwarf companion that originally was a more massive, donated its material to the B-type star, spun it up, and leaving behind a white dwarf remnant. This is a nice example of a mystery in our galactic backyard. But there are many other mysteries in the context of binary star evolution. A significant fraction of B-type and O-type stars will interact with a closely orbiting companion, and they can evolve to produce a plethora of astrophysical phenomena, including type 1a supernovae, X-ray binaries, millisecond pulsars, mergers of neutron stars, which we may be able to detect as gravitational waves here soon, and short GRBs. And so to fully understand and characterize these systems, I think it's imperative that we have some insight into their progenitors and their evolution. However, as of 2012, these were the best statistics we had on the close binary companions to O-type and B-type stars. They all come from double-line spectroscopic binaries. And first off, they're all in our Milky Way, so they have roughly solar metallicity. We can only measure mass ratios for SB2s, where the companion is luminous enough so we can see it in the combined spectrum. Low mass companions may appear as SB1s, but just like Regulus, they could be contaminated with white dwarfs. We don't know if the companion is a low mass star or white dwarf. And finally, they become incomplete at these longer orbital periods, and you really suffer from small sample statistics. So how do we probe lower metallicities, extreme mass ratios, and intermediate orbital periods? The fact that we have poor or no sample statistics in these regimes should incite immediate fear, concern, and worry. Fortunately, we recently celebrated the 50th anniversary of Dr. Strangelove, and Peter Sellers here helped me to learn to stop worrying and love eclipsing binaries. Namely, I've really fallen in love with the Ogle data set, which stared at the Magellanic Clouds for 7 years. It got 500 plus photometric measurements on 50 plus million stars, and identified 30,000 eclipsing binaries, thousands of which are these early type eclipsing binaries with B-type main sequence primaries. Now, there's some really wonderful advantages of this Ogle data set. First off, the Magellanic Clouds probe these lower metallicities. And so by comparing the eclipsing binary properties in the LMC, SMC, or Milky Way, we find that the properties of massive binaries are really not sensitive to metallicity. Secondly, the Ogle observations are sensitive to shallow eclipses, which means we can detect these small, low-mass companions that eclipse their B-type main sequence primaries. There's also, as I mentioned, we have thousands of these eclipsing binaries, so despite the inclination and geometrical selection effects, we can still get decent sample statistics at these longer orbital periods. And this is the coolest aspect. The fact that we know the distance to the LMC, Magellanic Clouds, and the stellar evolutionary tracks are decently calibrated. We can measure the physical properties of eclipsing binaries, the mass ratio, age, and eccentricity, based solely on the light curves. No need for spectroscopy. And we can do this for thousands of systems. And this is just a proof of concept for one system here, showing that the solutions for the physical parameters are unique. Granted, some of the solutions are correlated. But we can measure the ages to 30% accuracy and masses to about 15% accuracy for these eclipsing binaries in the Magellanic Clouds. And so we do this for thousands of systems. And first, I just want to show the 130 eclipsing binaries in this narrow strip of orbital period space, 20 to 50 days. And you notice this correlation between eccentricity and age. First off, we see that the young systems are all born with these large eccentricities, which suggests these massive binaries formed through some kind of dynamical interactions. That can be tidal or disk capture, or three-body exchanges, or secular evolution in some kind of triple star system. And the trend is simply caused by tidal evolution. And so by measuring the slope here, we directly constrain the tidal damping constant and these massive main sequence stars with radiative envelopes. So after pouring through thousands of these eclipsing binaries, as Christine Jones said yesterday, just look at the data, and we found about 22 of these systems that showed these unusual features. In addition to the eclipses here and here, there's a sinusoidal variation between eclipses. And we realize this is caused by radiation over the B-type main sequence star and onto the companion, and we get this reflection effect. To get this heating and reflection effect, you have to have short periods, which they are, and we measured that the radii are comparable, but the companion is significantly cooler than the primary. And so these systems are main sequence plus pre-main sequence eclipsing binaries. The companion is a low mass star that's still collapsing, contracting into its normal phase of evolution along the pre-main sequence phase. And so these are extreme mass ratios with very young ages, young enough so that the primary is a main sequence star and the low mass secondary is still in the pre-main sequence. As a further testament to their youth, we find that the majority of these main sequence plus pre-main sequence eclipsing binaries are in H2 regions. So here's a picture of the Magellanic Cloud. You can see all the pink H2 regions. The thousands of B-type main sequence eclipsing binaries are dominated in the bar of the LMC. But if we just show the 22 pre-main sequence eclipsing binaries with pre-main sequence companions, we can see that they're predominantly in H2 regions. In particular, the type of eclipsing binary is correlated with the type of H2 region in which it resides. One of our youngest systems here that we dated at 0.6 million years has a very deep eclipse, is in the bright Tarantula Nebula. You have another young system here that we dated at 0.9 million years. Can everybody see the little pink right there of that H2 region right there in the middle of the dot? But older eclipsing binaries are in these larger diffuse H2 regions. And so this is a direct probe of the kinematics of the H2 regions, which we hope to eventually use to measure the feedback in these H2 regions in these stellar nurseries. So my mom always told me to mind your P's and Q's. I'm sure what she meant by that is that to never assume that the distribution of orbital period P is independent of the distribution of mass ratio Q. You really have to think of the full two-dimensional phase space. And as 2012, all we really had was the double-line spectroscopic binaries at short periods and the visual binaries, the visually resolved companions at these long orbital periods. And so since then, we've been filling in the phase space. Intermediate periods, we have long baseline interferometry. We also have Cepheids done by Nancy here, using Cepheids to probe these intermediate periods. And then our work on eclipsing binaries shows that these extreme mass ratio companions do exist, and we can measure them out to roughly 100 days or so, an orbital period. And so by combining all these statistics, what emerges is a self-consistent paradigm for binary star formation. On the top panel here, I'm plotting the power law component gamma of the mass ratio distribution. So gamma of 0 is a uniform mass ratio distribution. Gamma of minus 2.35 is what you'd get from assuming random pairings from a salt-pure IMF, so a distribution that's weighted towards extreme mass ratios. On the bottom panel, I'm showing the excess fraction of twins with mass ratios very close to unity. And you can see that for both low mass and high mass primaries, close companions have this close to uniform mass ratio distribution with an excess fraction of twins. However, as we go to longer orbital periods, these massive binaries become weighted towards extreme mass ratios. And that's indicating that the components evolved more or less independently instead of correlated evolution as they would have been if they were closer. And we see this trend in both massive stars and solar type stars. But for solar type binaries, we see correlated components across a large range of orbital periods. And that's just because these solar type binaries have these long-lived primordial disks. These massive stars, they collapse in a few free fall times and photoevaporate their disks within 0.2 million years. Perfect. And so we get these low mass companions at these slightly wider orbital periods. So the main point is we have more of these extreme mass ratio companions at these slightly wider orbital periods than what we over here and what we measure at close periods. You cannot use the statistics of these close systems, which has been done, which is what typically is done, and extrapolate it to these longer orbital periods. And so the differences here have some very important consequences for evolution of massive binaries. I just want to take the last 4 minutes or so to talk about two of them. So we know, well, the best model for forming galactic low-mass X-ray binaries and millisecond pulsars is from extreme mass ratio binaries. You need at least a 10 solar mass star to undergo a supernova, maybe 9 solar masses, maybe even 8 solar masses. And the secondary has to be a low-mass star, less than 1.5 solar masses, so that it has a radiative core and convective envelope, and so that during this phase of evolution here, magnetic braking, coupling with tides, will cause them to come together to get this Roche-Lobe overflow and produce a low-mass X-ray binary. Assuming the canonical input assumptions in binary population synthesis, the predicted rate of low-mass X-ray binaries and millisecond pulsars is 1 to 2 orders of magnitude what we infer from observations. Now, what has been done before is to resolve this discrepancy is to invoke unrealistic, in my opinion, prescriptions for binary evolution. Like, for example, making the efficiency of common envelope evolution here, nearly 100%, or hoping that the velocity of the supernova kick here is so smaller than the orbital velocity so that you don't disrupt the binary. But by implementing these updated initial conditions, again, we're finding many more of these extreme mass ratio binaries at these intermediate orbital periods. We naturally expect about 30 times more than what was predicted, assuming a uniform mass ratio distribution. And so that naturally explains the discrepancy in the earlier calculations without having to invoke changes in the binary evolution parameters. Finally, what motivated my thesis was the type 1a supernova progenitor problem. And here I'm showing in green the observed delay time distribution. We see type 1a supernovae go off in spiral galaxies, but also after star formation has long ceased, and we see type 1a's go off in ellipticals. And we get this nice t to the minus 1 power law distribution for the delay time distribution. And so there's very different predictions for type 1a supernovae, whether they come from double degenerate or a single degenerate. You can see that both predictions fall below what's observed. However, the double degenerate prediction has the same functional form, whereas the single degenerate prediction has this kink at late times. And so this kink at late times that's different than what's observed was one of the main arguments for the double degenerate scenario. However, again, all these population synthesis studies assume a uniform mass ratio distribution, the canonical input assumptions. And we're finding that there's, again, many more of these extreme mass ratio binaries which produce more symbiotic systems that lead to these late time single degenerate type 1a supernovae. And so we're predicting a factor of 20 increase right here just due to implementing these new initial conditions. So I'm not saying that type 1a supernovae come from single degenerates. I'm just saying that Considering the uncertainties and the predictions, and taking into account the updated initial conditions, you cannot use the delay time distribution to discriminate between progenitor models. So just to conclude, in the end, I think about 1/3 of these SB1s contain these compact remnant companions, just like Regulus, be white dwarfs, neutron stars, black holes. We were able to use the OGLE data set to probe these early type binaries in portions of the parameter space unavailable to spectroscopy, namely low metallicities, extreme mass ratios, and intermediate orbital periods. In the process, we serendipitously discovered this new class of pre-main sequence plus main sequence eclipsing binaries. And by using these eclipsing binaries with known distances, we can use them as age indicators to understand the evolution of H2 regions and the eccentricities due to tidal evolutions. And we're finding that you have to mind your P's and Q's. You got to consider that the mass ratios and orbital periods are interrelated, and that has important consequences for the evolution towards these kinds of systems. Thank you. Right.
Why would that affect the other bins in the generation?
Let's see, go back, here we go. The late bin comes from symbiotics, which dominate the late time component. These early bins in the single degenerate scenario come from main sequence donors, which come from a different parameter space of M1, Q, and P. And so the parameter space where those systems are doesn't change that much, what we're finding in the initial conditions.
A couple of items. On this curve, you might make the argument, which I think is probably the reality, which is that both modes contribute. By some, your 2 points, I get closer to the observations than either one gets individually. Both the single and double degenerate are contributing to what we see.
I totally agree that both of these are going to occur in nature. We don't know if it's 10%, 50% of each, how each one contributes, whether they look differently. There are various subtypes of 1As, whether one occurs more predominantly in different environments. But yes, I definitely agree with the statement that both are definitely going to occur in nature.
Then on the summer chart,
yeah.
The compact remnant companions, if they're white dwarfs that are in a fairly close system, shouldn't they have an X-ray signal due to accretion under the white dwarf that would provide a different signal from a non-compact remnant? If so, have we looked at some of these with Chandra? We've done a lot of observations of the LMC. Have you looked into that at all?
I have not personally done that. I know no one is yet looking at the white dwarf problem, just because I think with the white dwarf, most companions are going to be the primaries are going to be main sequence stars, and so you're not going to expect too much wind accretion onto the white dwarf, for example, until the primary evolves. For the more massive systems, for the O-type stars, that are SB1s, we are finding that a lot of these SB1s do show some narrow emission features in their spectra that were previously overlooked. This is done by Josh Grimley is investigating that for the more massive SB1s.
From the light curves that you had, were you able to also measure the rotation or the tidal deformations of the stars, some very close binary stars? Like, could you resolve some things about the shape and so forth, more detail?
Right. So my main focus was on the wider orbits, because that's where we had poor statistics. But as we go into the closer orbits, yes, we can actually see a lot of these systems are not, they're not spherical stars. And the modeling takes that into account. That near, if you're close to Roche Lobophilia, you're going to have your, teardrop-shaped kind of stars. So I didn't, look into what that implicates for the those kinds of systems. So.
Okay, let's thank
Yep.
Max again.
Yep, thank you.
All right. Thank you for the nice introduction. I just started my Einstein Fellowship at Columbia University a couple of months ago, and it's a real pleasure to be here at my first Einstein Symposium. So I'll be talking about some recent theoretical work I have with Brian Metzger on the expected event rates for tidal disruption flares and how we can compare that to the growing observational sample of tidal disruption flares that we have. This is currently in press. So Oleg gave a great introduction to tidal disruption events. I won't belabor the basic physics of this very much. What I want to get right into is this problem that Brian and I have identified, sort of a missing flare problem, which is that when you compute a theoretical event rate based on a sort of empirically motivated set of galaxies, you find a large discrepancy between that theoretical expectation for the event rate and the event rates that are observationally inferred from our current sample of TDEs. In particular, the theoretical event rates are at least one, maybe more, orders of magnitude greater than the commonly quoted observationally inferred rates. So I'm going to walk through the details of our theoretical calculation and then discuss some possible resolutions to this rates discrepancy. These include observational selection effects, exotic stellar dynamics, and maybe just a lack of understanding about what produces the observed emission in tidal disruption flares. But before I get into the details of these rate calculations, I want to highlight one other bit of uncertainty in current tidal disruption physics, which I think could be relevant for resolving this rates discrepancy, and that's the issue of debris circularization. So Oleg showed a very exciting simulation earlier in which circularization happened rapidly because of self-intersections between debris streams that were forced by relativistic apsidal precession. And I think this is unavoidable when you have relatively relativistic pericenters of order 10 gravitational radii. But in many tidal disruption events, you can have much larger pericenters. So here I'm showing an SPH simulation with a post-Newtonian potential where the tidal disruption radius is 50 gravitational radii. And as you'll see in a second, the self-intersection radius of this debris stream is quite a ways far out at about 400 gravitational radii. So self-intersections at these radii may be less efficient at quickly circularizing debris and forming a luminous accretion disk. And I just want to highlight this early on because even though the exact dynamics of circularization are still very much an open problem, this may turn out to be crucial in resolving the rates issue. So getting to the subject of tidal disruption event rates, the classical way to think about this is in terms of a loss cone in the six-dimensional phase space that stars inhabit around supermassive black holes. So in this cartoon picture right here, we have a supermassive black hole sitting in the center of a star cluster in a galactic nucleus, and it has a tidal disruption radius around it. Stars which penetrate within this tidal radius are torn apart on a dynamical time and quickly accrete onto the black hole. So if you think about a distribution of stars orbiting the black hole, for any given star, at any point along its orbit, there's a conical structure in velocity space, the so-called loss cone, and if the star's orbital velocity falls within this cone, its orbital pericenter falls within the tidal disruption radius. You can think about this loss cone in spherically symmetric galactic nuclei purely in terms of specific orbital angular momentum J. So there's a loss cone value for J, and if perturbations reduce a star's orbital angular momentum below this loss cone value, then the star is torn apart when it completes its orbit. So that near the black hole, you expect this loss cone phase space to be empty, and the rate of tidal disruption is set by the rate at which relaxational processes repopulate it. So there are different kinds of relaxational processes you can think of, different ways in which stellar orbits evolve over time, but sort of the simplest and most ubiquitous one is just two-body relaxation, collisional scattering of stars off of each other. Now, in my paper and in this talk, I'm going to neglect alternative relaxational mechanisms, more exotic things like non-collisional processes and non-spherical potentials, because the qualitative effect of all of these is to increase the tidal disruption event rate. And as I mentioned at the beginning, the primary motivation for this work is to see whether this apparent tension between theory and observation can be alleviated in any way from the theoretical side. So whenever possible in this paper, what I did was to take the more conservative choice of assumptions. If there was an ambiguous assumption to make, I always tried to err on the side of the more conservative assumption to see if there was anything that could be done to beat down this theoretical event rate into agreement with observations. And I want to just emphasize that a second goal of all of this is to see whether or not tidal disruption flares, and specifically statistical samples of them, can serve as a probe of the bottom end of the supermassive black hole mass function. It's been thought for a long time that the intrinsic rate of tidal disruption events will be dominated by the smallest supermassive black holes in the universe. I'll quantify this in a slide or two, and at the end of the talk discuss how promising I think this is. So, what are the actual mechanics? What are the steps that you take to calculate the rate of tidal disruptions in a given galactic nucleus? Well, if you start off with some sort of surface brightness profile for your galactic nucleus, the surface brightness is a function of a projected radial coordinate r, you can apply this semi-analytic formalism developed by David Merritt and his collaborators in 2004 that lets you take a number of steps to translate this into a rate of stellar tidal disruptions. So the first step is to deproject the surface brightness profile into a three-dimensional density profile rho. In this process, we use a simple Abel inversion. This assumes spherical symmetry. As I said a moment ago, this is a purely conservative assumption, assuming axisymmetric or triaxial geometries will only increase the rate of TDEs. You can then, from this 3D density profile, compute a distribution function of stars in orbital energy. Here we make a different assumption that I'll come back to later in the talk, the assumption of isotropic velocities. So if you have anisotropic velocities, this conversion is a little more difficult, but if you assume isotropic velocities, then you can use a simple Eddington integral to get your distribution function. Once you have the distribution function of stars in orbital energy, you can then compute orbit average diffusion coefficients that describe how quickly stars undergo a random walk through phase space due to uncorrelated two-body encounters with each other. And then using these orbit average diffusion coefficients, you can calculate the flux of stars into the loss cone at any given bin of orbital energy. And that's what I'm showing in this plot here for two nearby elliptical galaxies. One very salient point to take away from this plot is that the flux of stars into the loss cone is a very steeply peaked function of orbital energy. So if you look at this y-axis right here, you see that this flux of stars spans about 10 orders of magnitude over a relatively physical range of orbital energy values, so that most of the stars that get tidally disrupted in any galactic nucleus are coming from a very specific range in orbital energy space, which is to say a very specific radius that more or less by coincidence coincides with the black hole influence radius. So most of the stars that get disrupted in realistic galaxies are being fed in from parsec to 10 parsec scales. This is why Oleg's earlier comment about parabolic orbits is very well motivated. These are essentially zero energy orbits. You can then, there are other assumptions that you can vary. You have to think about the stellar present day mass function, scaling relations that you use to establish the galaxy parameters. I'll talk more about these in a second. In general, most of these things don't affect our final results too much. But one important thing is to make sure that you have realistic surface density profiles to anchor this calculation. So rather than use some sort of ad hoc theoretical profile, what we did was to take the nuclear sample of high-resolution Hubble photometry of 200 nearby galactic nuclei. So using this sample, we took fits of this somewhat ad hoc surface brightness profile, the nuclear profile. It actually fits the inner regions of galactic nuclei pretty well. For as a sanity check, we compared this to different surface brightness profiles. Choice of parameterization doesn't really matter too much. We used the M-sigma relation to estimate black hole masses. After rejecting some galaxies from the very high mass end, where they wouldn't affect our final results very much, we're left with 144 galaxies, which is a much larger sample than has been done in the past for computing tidal disruption event rates. So here are our final results. This is a scatter plot of tidal disruption event rates, stars destroyed per year, as a function of black hole mass. The black line is a fit to our entire sample. You can see that it increases as you go to decreasing black hole mass. At black holes of about 10 to the 6 or 10 to the 7, you're typically looking at maybe one star every 10,000 years being tidally disrupted by the black holes. If you want to compute a volumetric event rate for the local universe, you need to convolve this sort of power law best fit with a Schechter function that describes the densities of galaxies, and then some assumption about black hole occupation fractions in low mass galaxies. Because as you can see from this plot, it is the smallest black holes that exist in the universe which will dominate your volumetric event rate. So we're kind of agnostic about this because the bottom end of the SMBH mass function is not well constrained at present. We looked at ad hoc cutoffs in the occupation fraction. Our most conservative choice, this gray line right here, cuts off at a few times 10 to the 6 solar masses. That's probably too conservative to be in agreement with observations, but take this gray line as the most conservative possible case for how low supermassive black holes can go. If you convolve all these things together, you get volumetric tidal disruption event rates. So this is number of stars disrupted per cubic megaparsec per year. You You can convert this into a per galaxy event rate by dividing by the 0.015 galaxies per cubic megaparsec. And what you see is that even in this most conservative choice of black hole occupation fraction, you get a few times 10 to the minus 4 disruptions per galaxy per year when volumetrically averaged over the nearby universe. This is still an order of magnitude larger than the best observationally inferred rate estimates, and this uses an occupation fraction which is probably too conservative to be realistic. So as you go to these more liberal occupation fractions, where you have black holes at smaller and smaller masses, this discrepancy gets worse up to a 2 order of magnitude discrepancy if you have black holes all the way down to 10 to the 5 solar masses. This slide is slightly out of order. I'll come back to it in 1 second. Let's talk about this discrepancy. It's ultimately a persistent one. We tried varying a lot of different assumptions in our calculation to see if there was any way we could make it go away from the theoretical side. The short answer is no. And in fact, our calculation was conservative in a number of ways. We considered two-body relaxation only. Work by other dynamicists has shown that you can increase TDE rates by up to an order of magnitude if you consider non-spherical geometries and collisionless relaxation. We neglected enhanced sources of diffusion from massive stellar remnants, stellar mass black holes. The assumption of spherical symmetry, as I said, was a conservative one. So what are the ways out of this? How can we resolve this tension between theory and observation? So it's probably not occupation fraction of supermassive black holes. As I showed you a second ago, even a very conservative choice of this still produces a large discrepancy. It's probably not dust obscuration for observational reasons. It could be observational selection effects. So generally speaking, when observers try to back out an inferred TDE rate from a sample of their flares, there are a lot of selection effects that are often poorly quantified that go into this. So maybe it is kind of a problem with the inferred rates. But on the other hand, there's, I think, a very nice piece of work by Short, Van Velzen, and Glennis Farrer that looks at a flux-complete, albeit small number, sample of TDEs from SDSS and finds a relatively low TDE rate, 1 times 10 to the minus 5 per galaxy per year. So if you take this paper as sort of a gold standard for observationally inferred rates, you still have the large discrepancy. Another possibility has to do with the one non-conservative assumption we made in our dynamical modeling, which was an isotropic velocity distribution. So realistically, galaxies probably don't have isotropic stellar velocities in their centers. They can have anisotropic distributions with either a radial orbit bias or a tangential orbit bias. And if a majority of low-mass galaxies have strongly tangential velocity anisotropies, then it becomes much slower for stars to diffuse to low angular momenta, and TDE rates will be correspondingly suppressed. However, a follow-up study by Eugene Vasiliev after our paper came out seems to indicate that this just doesn't work. Low-mass galaxies can't sustain tangential velocity anisotropies for Hubble times. The velocity anisotropy relaxes away to isotropic velocities of order a gigayear for the galaxy sizes of interest. I think the only way to make this possibility work is if you have some dynamical feature in low-mass galaxies that pumps up the tangential anisotropy. Persistent black hole binaries would do this. So if galaxies are really, really bad at solving the final parsec problem, maybe that's a way to explain this discrepancy. But since low-mass galaxies are thought to be the best ones at solving the final parsec problem, my preferred resolution to all of this is that there's a strong bimodality in emission from tidal disruption flares. Only a small fraction are able to make bright flares, and that means that when observers back out an event rate from an observational sample, really what they're backing out isn't the true event rate, it's the rate of bright flare-producing TDEs. So one possible way to explain this, I think there are a few possible ones, but one I want to highlight is the idea that circularization may depend very strongly on how relativistic your pericenter is. So if you need a very relativistic pericenter of order 10 gravitational radii to give you strong apsidal precession and a self-intersection of the debris streams that's close to the tidal radius, then that means that only a small fraction of low-mass of tidal disruption events around small black holes will quickly produce an accretion disk and will be able to accrete onto the black hole at high m dots. So we sort of redid this volumetric rate calculation, assuming that you needed orbital pericenters below 12 gravitational radii to make a luminous flare. And while that really beats down these enormous event rates that you get if you assume 10 to the 5 solar mass black holes exist, it doesn't do that much to change the event rate for for our most conservative choice of occupation fraction. So even assuming this relatively stringent cut on orbital pericenter and a conservative choice of black hole occupation fraction, you still have a galaxy averaged event rate of 10 to the minus 4 per galaxy per year. So I think this assumption could work if the pericenter cutoff for efficient circularization is very small, maybe of order 7 or 8 gravitational radii, but I'm not sure that's well motivated by theory. So I think we need to think about other ways in which you can produce a strong bimodality in flare luminosity. That's pretty much all I have to say. I'll leave my conclusions up here. This discrepancy between theory and observation appears very persistent. I'm investigating some possible solutions to it right now, but I think this is a very interesting thing that has emerged now that we have a larger sample of observed tidal disruption events. So I'll be happy to take any questions that you have.
And I might comment that Brian Metzger was a former Einstein fellow.
That's true, yeah.
Yes.
So you talked about this bimodal emission,
Mm-hmm.
saying that when you have a close encounter, you get rapid accretion and high accretion rate and high luminosity, and then you can observe such objects. But why is it bimodal? Should one rather not expect like a smooth transition and smooth luminosity population?
That's certainly reasonable. Bimodal was maybe sloppy wording on my part. Basically just a large range of optical luminosities for tidal disruption flares. You need to vary it by about an order of magnitude, I think. Yeah.
So you showed on your distribution of rates that there are some galaxies that are down at the 10 to the minus 5 level and some at the 10 to the minus 3 level.
Mm-hmm.
Is there any reason to believe the ones that are at the 10 to the minus 3 level, since they're more cuspy, maybe are the ones that are missing black holes? Like the occupation fraction might have a relationship with the stellar profile?
That's an interesting hypothesis. So what James is saying is right. The galaxies that dominate the rate in our empirical sample are ones with steeply cusped stellar density profiles, where the stellar densities get high and the two-body relaxation time becomes pretty low. I don't see So generally, chord galaxy profiles, sort of shallower ones, are associated with depletion of stars by a black hole binary in spiral. But by the same token, you often see cuspy density profiles around dynamically measured black holes. And the thought is that star formation has rebuilt the cusp since the last major merger. So it's not obvious to me that works. But it's not obvious to me that correlation exists. But if it does, that could help to explain this discrepancy.
Okay, let's thank.
Maybe you already said it, but do you assume that all the stars are just the same type, just point constantly floating around, or?
No, so that was actually one thing novel in our work relative to past calculations. We looked at different IMFs and different present-day mass functions. Choice of PDMF turns out not to matter that much, except that if you do have a lot of stellar mass black holes, they can increase the diffusion coefficients by a factor of a few. So generally, the most massive things that you have dominate the rate of angular momentum diffusion.
So you actually take into account that, like in the two-body relaxation, like the mass difference and also the loss cone would be different sizes for different stellar objects?
Well, we take the different size of the loss cone into account for everything. So yeah, I mean, red dwarfs dominate the TDE rate because there are more of them, but they don't dominate it by as much as you would think because they're harder to disrupt. They're denser. They have a loss cone that's smaller. We neglect the enhanced rate of diffusion from stellar remnants to be conservative, but I think that's potentially another way that this discrepancy is persistent.
Just a very short technical. So is there many cases where there's different stellar type where the Schwarzschild radius is very close to the tidal radius, or?
Yeah, so I mean the Schwarzschild radius goes linearly with black hole mass, and the tidal radius goes as the 1/3 power. So as you go to larger black holes, you'll always get to a black hole that can't disrupt a star outside the horizon.
Basically, for some of the stellar types, you don't have a loss cone, but you just have a very small slit, like where you.
Yeah.
That is something you take into account into the formalism, that you don't have a cone, but you.
That's right.
Only have a small region where you.
Yeah, we account for that in the calculation. Thanks.
Okay, let's thank Nick again. The final speaker for this session is James Buson, who did his grad work at UC Santa Cruz and is now here at Harvard, who will be speaking on the role of magnetic fields in the tidal disruption of stars.
Drum roll, please. You can disconnect and reconnect. Sometimes that helps. It seems to detect it. Perfect. Okay. 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 So this is my third and final year as an Einstein Fellow. So first, I'd just like to thank the Einstein organizers for giving me the privilege to use their money to do my research. So I really enjoyed my time as an Einstein Fellow, and I think it's been really great and very good for my productivity. So today I'm going to be talking about the roles of the magnetic fields in the tidal disruptions of stars, and I really mean like during the disruption, not during the circularization, which I think Oleg showed some hints of how some of the issues associated with the circularization after the star returns and accretes onto the black hole. This is more trying to figure out if I have some initial field configuration in the star, what happens to that field during the disruption. And this is work I was doing primarily with Mike McCourt, who was my office mate last year and knows a lot about magnetic fields. It got me all excited about them. All right, so a brief outline. First, I'm just going to talk about magnetic fields in stars. Then I'll give you a tiny overview of tidal disruptions, since I think you've heard quite a bit of the basics. Then I'll talk about magnetic fields in disruptions and why you should care. And I'll show you some preliminary results, which I may show in a Sasha-style interpretive dance. But we'll see. All right, so magnetic fields in stars typically are very weak. There's something like 1/1,000,000th of equipartition in the sun. And they're only really competitive with gas pressure sort of in the photosphere, and that's why you see these very beautiful prominences and stuff on the surface of the sun. And the sun is our best laboratory. We have very high-quality data of it now, but we really only know the structure of the magnetic field on that surface layer. And inside the sun and other stars, we have some sense for what the strength of the fields are, but we don't really know the configurations of the fields in detail. That mostly comes from theoretical modeling. And there's a lot of uncertainty there. And only in a few kinds of stars are the magnetic fields dominant in modulating the dynamics. So one example is a subclass of A stars known as AP stars. This is some simulation work by Featherstone in 2009 showing very large-scale twisted field configurations in the convective zone of the star. Here's another simulation paper on the same kind of star by Braithwaite in 2006. This is a slightly different, more global configuration. Another example is that of a young, rapidly rotating sun, where you get these things that they call magnetic wreaths, where you have counter-rotating or counter-directional magnetic fields along the equator of the star. So some very interesting magnetic field configurations inside of different kinds of stars. And there's really kind of two flavors for magnetic stars. Either the magnetic field is sort of actively sustained by some sort of convective dynamo process. So examples of that are protostars, the AP stars I just showed you, K and M dwarfs, which are fully convective, red giant stars, things like that sort of sustain the magnetic fields inside them by driving motion. Or they might have had such motions in the past, and that's frozen into their structure. So some examples of that are mostly compact objects, magnetic white dwarfs, magnetars. An interesting thing, and there's a nice review paper by Reisenegger in 2009, is that the flux value in all the extreme magnetic stars that we know of is roughly the same value for both neutron, like magnetars, and these very magnetic AP stars. It turns out to be about 10 to the 27.5 Gauss centimeter squared, which is interesting. Okay, so tidal disruption is brief. Star approaches the black hole. The tide is raised on the star. You get two lobes, one that's bound and one that's unbound. And sometimes you have a surviving core, depending on how close to the black hole the star approached at pericenter. So this is a movie example showing density, a slice of the orbital plane of a partial disruption. So we can just watch and see hydrodynamically what happens. Get these two large tails that extend outwards. In this case, the core survived. And these tails continue to extend, but they actually feed back onto the core and start spinning it up. And you start seeing these interesting instabilities and rotation developing in the surviving core. So that's just a pure hydro simulation to give you a sense of what that looks like. Here's an example of a full disruption. This movie is a lot faster in the amount of time I'll let it run over. But in this case, there's no surviving core. It very quickly gets obliterated and turned into a very long, extended stream-like structure with a very narrow width. So those are kind of the two extremes of disruptions that you can get. To examine this problem of magnetic fields in stars, I'm using Flash, which has been my bread and butter hydro tool for many years now. The MHD solver is an unsplit staggered mesh constrained transport method. So the main problem in a lot of MHD codes is that they have a hard time obeying Maxwell's simplest equation, which is that the divergence of the magnetic field should be 0. So Flash's method, the constrained transport method by design, by construction, should constrain this to numerical precision. But my findings have suggested that there actually are very subtle bugs related to refinement and de-refinement that do lead to non-zero divergence from time to time. I do think it's a bug, but it's a very subtle one, and I've had back and forth with the Flash people over the last couple months trying to track it down. The current workaround is to de-refine as little as possible. The errors that you get are something like 1 in 1,000, but that's sort of disappointing when you expect the method should give you 1 in 10 to the 16, sort of numerical precision type errors. That being said, this sort of error is confined mostly to the fluff, which is the background gas we have to put into these mesh-based simulations anyway. And they're small enough that they don't affect the dynamics. And compared to other methods which have order unity errors, it's better than that, at least. Okay, so the initial conditions, we do two different disruptions, a beta of 0.7 and a beta of 1.5. Beta of 0.7 is a grazing encounter. That's a partial disruption. 1.5 is a full disruption. We use a polytropic index of 3/2. It's a fully convective star. We do two different magnetic field configurations. We do a tangled field and we do a dipole configuration. The way we initialize it is based on the vector potential because we can guarantee at least div B is 0 in the initial conditions. The star we resolve is about 100 cells in diameter. Initially, we use a ratio of gas to magnetic pressure of 10 to the 4, although I actually vary this in a few of the simulations you'll see. But this is very, very strong. Mega Gauss fields, much stronger than the sun. The reason being is that we do want to actually see if this influences the dynamics when the star is at this sort of as magnetized as it can be state. So the field is only defined within the star. In principle, something like the sun has fields that extend to large distances. But numerically, it's challenging to include those because the Alfvén speed gets really high in the vacuum surrounding the star. Okay, so this is a partial disruption, again, with the magnetic fields turned on, just showing the density. At the surface, you don't really see anything that really suggests to you that there's magnetic fields in this problem. But I assure you that there actually are fields in there. And this is a 3D rendering of what the tangled field conditions look like, which is sort of this multicolored yarn ball. So everyone's been showing their children in their talks. So I'm going to show my furry child. And one thing I realized today was that she has this yarn toy that looks very similar to the initial conditions I've been using here. So anyhow, so let's just see what this looks like in motion. So the star disrupts. And what you'll notice actually is that it tends to stretch out the field lines at first, but then you'll notice that there are these two huge vortices that develop that start twisting magnetic field lines into them. as the star basically collapses back on itself after the disruption. So those two vortices last about a dynamical time. They're basically the size of the star. You can actually see them in the density quite clearly as these sort of evacuated holes in the star. So that's actually due to the fact that when the arms return back to the surviving core, they don't return directly towards the center. They have a little bit of an offset because they've acquired some angular momentum relative to the surviving core. And the star is basically trying to accept this new matter, which is coming in at almost escape velocity. So you end up with these sort of tidal waves that are star scale in this thing. It only lasts for maybe a few rotational periods of the star. So that's important later. So the fluxes through surfaces are conserved when you're freezing them to the matter. And in these disruptions, the main thing to remember is that we're taking this star and we're stretching it primarily in this direction. So the cross-sectional area of the star isn't really changing very much. So that means that the component of the field that is perpendicular to that direction is not really changing much in strength. But the field strengths in the directions perpendicular to the stretching are being degraded significantly. So this is a field geometry after disruption for a full disruption now. So we're looking at the top of the star and the top and the side and the bottom. And so we're just going to scroll past what that field geometry looks like. So what was interesting is that I started out with a tangled field. But if you look at the final field structure in this thing, it's actually pretty regular looking. It looks mostly stretched along the direction that the tides are stretching the star. There's not really indication very much that it was tangled initially. And the reason for that is that it's basically obliterated all components of the field that are tangential to the stretching, and the only thing you have left is whatever happened to be parallel to the stretching pre-disruption. So really the simple way to think about this is that we start off with some magnetic field configuration. In the partial disruption case, we have a surviving core that twists up that configuration. In the full disruption case, we just take that shape and stretch it. And so now we're going to look at the partial disruption. This is beta, so this is showing the ratio of the magnetic energy density to gas. And in this image, black is stuff that's magnetically dominated, white is stuff that's gas dominated. What you'll notice is that in the center, it's pretty much gas-dominated, not influencing the dynamics tremendously. But in the arms, where it's been stretching out adiabatically, it's actually become magnetically dominated. So I'll show that one more time. So if you look at the arms, you'll notice that they go from being white to black as the movie runs along. And that's just because the internal energy due to adiabatic expansion is degrading, and the magnetic field energy is not degrading. Yeah, Nick? I think you'll see where that comes from in a second. Yeah. Yeah, actually right here. So this is going to show you a CAT scan, basically of the field geometry through this partial disruption. So red is coming out of the plane and blue is going into the plane. That line that you're seeing, Nick, is actually the separation between the two magnetic field directions. So there's a field reversal there, and that's why the beta ends up going to gas pressure dominated right between the two. So really what it does is it just preserves the original tangled field but stretches it in this one direction. So whatever profile you happen to have parallel to the direction of stretching, that gets imprinted on the star. And this is the top-down view of the Z component of the B field after it started circularizing for a while around the surviving core. So you see a really tangled mess here. So when I saw this originally, it was hopeful that we'd actually get something like the MRI, because it looks like you have a lot of turbulent structure. So one thing you can definitely see the magnetic fields influencing is the width of the streams. The reason being is that they provide an additional source of pressure, and they don't actually degrade as much as the gas pressure does. So if you include a magnetic field, it actually leads to wider streams in the post-disrupted star. That might be interesting for a couple of reasons. Okay, so now we're just going to show what's happening with the magnetic energy. So if you look at the orange curves It's a little bit disappointing, but not very much, honestly. So the thick line is the partial disruption where you had this twisting dynamo action, and it looks like it's increasing by maybe a factor of 10. So the hope was that maybe we can build up a significant field dynamo that can lead to a very large-scale field within the star. Unfortunately, it didn't seem to happen with the first set of runs that I did. So we tried a few different things. We tried increasing magnetic field strength further relative to the original initial conditions. We also tried a dipole field geometry, which has a little bit more favorable large-scale structure where you'd hope that perhaps it would twist up a little bit more uniformly. So the orange lines just show varying those parameters, strength, dipole versus tangled. In all of them, you see that you get sort of a fixed amplification factor in the partial disruptions of maybe a factor of 10. It actually seems like it's saturating. Like if you start with a higher initial field, it doesn't amplify as much over the original field as in the cases where you start with a low field energy. So we want to compare to some analogs. So merging stars resemble these partial disruptions reasonably well. And as far as I'm aware, those have only really been done with magnetic fields turned on for white dwarf, neutron star, mostly compact object mergers. And most of the simulations have been done with divergence cleaning methods, which introduce errors on order unity in the divergence. Some have been done with constrained transport, specifically the neutron star merger simulations by the Japanese. So if we actually compare those, the ones that have constrained transport and control the divergence, the amount of amplification that they get in these neutron star mergers is on the order of a factor of 5 to 10. The resolution that we have in our simulation is somewhere around their mid-range resolution. So we're actually getting stuff that's fairly comparable to these neutron star merger calculations. The ones that don't control the divergence, sometimes you can get extreme amplification in the fields. And if you look at this curve here, it goes from 10 to the 24 ergs in magnetic energy to 10 to the 48. So it goes up by 24 orders of magnitude in those calculations. So why is this happening? Well, there's a couple of reasons why. I'm not entirely sure, but it could be physical. One reason is that when neutron stars merge together, you end up with these very large scale Kelvin-Helmholtz rolls that are the sites of enhanced magnetic fields. Those persist for quite a long time in the merger and can lead to amplification. Another reason is that perhaps they're not running with enough resolution. Or the other reason is that perhaps the methods that don't conserve divergence are flawed for some reason. So I'd say the primary findings are we find that the magnetic fields can retain close to their original strength in the star within the arms. And at some point they become dynamically relevant to explain how the arms evolve hydrodynamically. And that might be important for the circularization process. The caveat is that in the simulations I showed you, I started out with fields that are much higher relative to something like the sun. So in reality, it might take longer for the fields to become dynamically relevant if you do a realistic disruption of something like the sun. The magnetic field geometry that results is always parallel to the direction of stretching. So when I started with a tangled field or a dipole field, it looks very, very similar in the end. So that suggests when you're doing the circularization problem that your field lines are going to be wound around in a toroidal configuration rather than having an azimuthal configuration. And so that might be important if you're considering how the MRI might develop in the post-circularization disk. The core itself sees a mild amplification, perhaps a factor of 10. We don't see a crazy high amplification there, but that might be a result of a couple of things, and we're still trying to work out what that is. So the to-do is to do a very high-resolution run to see if that's the answer to our issue, where we're not able to get very large amplification. I've been trying to run this on NASA Pleiades for the past 6 months, and so I'm going to use this as a platform to complain a little bit, because there was some decision made 6 months ago to cut Astro's allocation at NASA Pleiades by a factor of 4. So now if you want to run a job that's a few thousand cores, it can take you many weeks to even start it running. And they've been having technical problems every couple of weeks where Unfortunately, every time it starts to run, it runs for 2 days and then the hard drive dies, and then I have to restart it. So for 6 months, I've been trying to run the highest resolution simulation here and haven't been able to do it, partially because of this change in policy and partially because of technical issues. So I know a lot of others in this room use NASA's computers to do supercomputing, and perhaps you've experienced the same thing. But the other things that we need to do is to compare a little bit to control simulations with no fields and do a bit more quantitative analysis. Currently, we've been looking at more qualitatively how things change, but it'll be interesting to see very specifically how the widths of the arms change and such with changing conditions. And that's all. Thank you.
Questions to finish off the final session here this morning?
Do you have a feeling what the source of the magnetic field amplification is in your core? If it's like in neutron star mergers where even the highest resolution you still have nearly no hope of actually resolving the growth because the mechanism is on a very small scale, or if it's more like the MRI and you have actually a chance of by going to high resolution of actually resolving the growth and saturating.
Yeah, so I see one primary role, basically like one curl of stuff in the simulations I've run so far. I'm not seeing like a cascade to smaller scale roles yet at the resolutions that I've been doing. I think partially you're right that if you can cascade to smaller scales, you have the possibility of using that to amplify the fields further. At least at the resolutions I've done things, we're not actually developing sort of that cascade yet. And it's possible that's physical. I mean, the roles that I'm resolving in the simulation now are not that badly under-resolved. We have, something like 50 voxels across those structures. So it is possible that if you go to higher resolution, that you might be able to do that a little bit better. But I'm not sure at this point. Yanfei? So it is a definite gradient where the core doesn't get spun up very much at all by the encounter. And the stuff that falls back onto the core actually will have super Keplerian motion. It'll technically be on elliptical orbits but because there's other matter that gets in the way, it sort of crashes into that stuff and starts to circularize. So there's definitely angular momentum redistribution when the core sort of reforms from the infalling streams. But it does have this sort of radial dependence where it's close to zero in the center of the star, and it goes all the way to Keplerian and you get to the very edge.
After this is just because the differential rotation is also important, for example, if you want the MRI to work.
Yes, that's true. And in just comparing to the neutron star simulations, it seems like the amount of differential rotation we have, at least on the edge, is comparable. But it's not clear to me exactly why we're not getting the levels of amplification that you see in some of the merger calculations that have been done.
Would you expect any difference in more deeply plunging encounters where you can have shock heating and high degrees of compression?
Yeah, so Oleg's simulation, his initial conditions, were for a much higher beta encounter. There's some threshold beta where it goes from being this thin stream case to a wide fan. It's probably around beta of 3 or 4, somewhere in that range. One of the open simulation questions that needs to be addressed is actually where does that threshold in beta lie? Because it evolves really quite differently, I think, if you have a very high beta encounter versus a more common low beta encounter. So I did only do the low beta encounters in these calculations. My feeling is that the magnetic field will degrade more extremely in those encounters because it fans out and basically spreads out the flux over a larger area. So I haven't done those, though. That's just my intuition as to what would happen.
Two last questions, please.
So on the initial condition, imagine that the star encounters an accretion disk that's already turbulent, that's already magnetized. So I don't know, do you have any plans for including those sort of initial conditions where there's already a magnetized disk?
So there was a paper by Luke with Ramesh where he looked at the possibility that the stream, when it falls back in, can sort of gather magnetic field lines from a fossil disk that's present around the black hole previously. I don't think anyone has actually simulated the global situation where there's a disk already. That might be something interesting for the people simulating the global situation to try. One of the main problems with generating the jets is that there is a deficit of magnetic flux, which is something you think you might need to actually generate a powerful jet. And in Oleg's calculations, we saw that the magnetic field strength was relatively weak. And in principle, if you had a fossil disk already present, that might change the picture a little bit. So it'd be interesting to think about what happens in that situation.
Yeah, this is tying back to Francois' question about a physical detail. So if you're seeing amplification factor is not like high enough for what you would expect compared to star simulation, have you tried with like with a weaker initial field? It seems like you're leveling off at some kind of level.
Yeah.
You could get the amplification factor you want, but not the absolute magnitude of kind of saturation.
Yeah, so we tried with the weaker one. That was this bottom line here. That was the weakest one that I started out with. If you look at that, it does look like it amplifies more than all the other cases. Maybe in that case it's going up by a factor of almost 30. Yeah, they're the total energy in the domain. So that includes both the stretching tidal arms and the core. In these cases, though, the partial disruptions, the magnetic energy is dominated by the core. The arms just provide like a 10% contribution.
Okay, well, let's give James and all the other speakers in the session
So
another hand.
lunch has magically appeared once again, and let's reconvene.
Thank you.
For talks at
Did you need a
1:40.
copy for like?
That's mine.
Oh, sorry. Did you need a copy for like the website or something?
If you want to post it, you don't have to.
Okay.
But I guess, can you make the PDF?
I can save it as a PDF. It's just like none,
Okay.
none of the movies
Yeah,
will.
the PDFs are easiest for us to post.
Very nice. Thank you.
So yeah, whenever you get that to us, we're not going to post anytime soon.
Okay.
It's not muted. So
Okay.
don't say anything you don't want to record.
Shit. CFA sucks. No. That you didn't get shouts of agreement that people can't hear you.
Right, yeah. Otherwise, it would have expected everyone to join in chorus.
I think we're getting close to getting ready to start the afternoon session here of day 2 of the Einstein Fellow Symposium. Let me just briefly introduce myself. I'm going to be the chair. My name is Mike Novak. I work for the Chamber X-ray Science Center and specifically the High Energy Transmission Grading Group over at MIT. So I'm part of the software data science team, so we're the folks that help specify the software that you use to analyze your chamber data and also deal with things dealing with transmission grading. So that's and my personal work is on black holes and neutron stars, so I'm really interested in hearing all the talks in this particular session. So 20 minutes for talk, 15 minutes talking time, and 5 minutes for questions and
Sounds
answers.
good.
First up, we have Grant Tremblay, who did his PhD at Rochester and is now working at Yale University, and will tell us about cold patterns pumped by black holes.
Cool. Thanks, Mike. So I'm going to give you the cheap knockoff version of the beautiful talk that Massimo gave earlier this morning. And I'm going to do so by showing mostly pretty pictures with almost no science whatsoever. So it occurred to me just now standing here that this is just the perfect depressing metaphor for my career so far. It's okay, you can comfort me later. I will attempt to make one scientific point, and that is that cold molecular gas can couple to black holes by both feeding and feedback. And I'd argue that neither of those points were necessarily obvious as early as 5 years ago or so. Because if I were to tell you that cold molecular gas couples to black holes by feedback, and then show you a jet-driven cold molecular outflow driven by jets launched by a black hole, that'd be like saying that I have a brick here, and then I go and expect the brick to fly off in the opposite direction in terms of volume filling factor and willingness of a molecular cloud to talk to the magnetic field associated with the working surface of a propagating radio jet. It's weird. You don't expect it. And then feeding, cold molecular gas coupling to a black hole by feeding, is also not necessarily obvious if you consider it in the sort of classical Bondi type hot mode scenario that many people in many simulators have been thinking about for years, right? So I'm going to start an AGN feedback talk in the most groundbreaking way by showing you the most cliched thing ever, which is an image of Perseus. And I do this only to remind you yesterday of much better talks given by Christine and Becky and Karen and Massimo earlier today. And this is also to remind you that anything, a big dark matter halo with a really big virial temperature will result in a really big ball of hot gas. And if the central density of that gas is very dense, it can cool very rapidly and should give rise to what's effectively an overcooling problem suffered not only for giant galaxy clusters, but for effectively every galaxy more massive than L-star, right? The cooling flow problem is not something that is unique to giant clusters of galaxies, right? We think we have a solution at least at the high mass end, and that's if you zoom in, we think that this rain of cooling gas feeds a black hole, which then launches jets, which then excavates this beautiful network of buoyantly rising X-ray cavities, and we hope and pray that these cavities contain enough energy, and they often typically do, to save us from the overcooling problem, at least in these massive systems, right? But if AGN feedback, or in this case mechanical AGN feedback, also called radio mode AGN feedback, can save us from the cooling flow problem, it can't do it with 100% efficiency at all times, right? Because if I blink this exact same X-ray field with the exact same optical field, you find that relative to all the other galaxies in this cluster, the brightest cluster galaxy that's sitting under this rain cloud that is the cooling flow is lit up, right? And effectively every waveband that you pick to look at, choose to look in, right? Beautiful 30 kiloparsec scale H alpha nebulosities, radio sources, cold molecular gas, ongoing star formation. And the reason for that is that cooling flows do actually cool, and they do actually flow, right? They're not the monsoon that we would expect in a classical sense, but there is a light drizzle, right? So if there is an entropy floor, that floor is porous,
right? Or it raises and lowers as the AGN varies in power or switches on and off. It's now becoming much more instructive, perhaps, to think about this not as a radial gradient in cooling time, but rather as a radial gradient in the longevity or survivability of thermal instabilities. And this is something that Massimo talked about earlier today. The idea is very simple. You don't even really need any math to imagine it. Imagine I'm a ball of gas right here, and I want to say, okay, now I'm a thermal instability, and I'm going to cool, right? So, okay, I start to cool, right? And I start to sink because cold stuff sinks and hot stuff floats, right? But if I sink too fast, much faster than I can cool, then I will simply sink to a lower altitude region, which is now colder, and now I'm in thermal equilibrium, and I'm no longer a thermal instability, right? But if I can cool much faster than I can sink, then my lifetime as a thermal instability can be longer, or perhaps very long, and I can give rise to this precipitating, clumpy, cooling, inhomogeneous, multi-phase medium that we generally tend to find, or predict at least in simulations, to be roughly within this threshold, and I use the term really, really loosely. It's not so much a threshold as it is a really fuzzy boundary with a lot of scatter around it. But I want to give credit where it's due. A lot of people have worked on this. Massimo did some of the really pioneering stuff on this, along with Mike McCourt, who's here, Pratik Sharma, Juan Lee, Mark Voigt has a really nice series of papers this year out on this that applies it to galaxies as a whole. But this builds on decades of work by many people in this room, and I want to give credit where it's due, right? None of this is mine, unfortunately. I really wish it was. So the model explained very briefly and qualitatively is this. Your hot ball of gas starts disrupting and precipitating as a multi-phase medium whenever you meet this threshold, or roughly where you meet it, right? That then gives you the sort of cold chaotic accretion model that Massimo talked about earlier today, which then in principle, if you have enough angular momentum cancellation, can boost the black hole feeding to about 100 times Bondi, right? You then trigger some newly launched jets, which then propagate outwards, excavate your X-ray cavities, hopefully heat the gas. But also at the same time can drag lower entropy or cooler gas to higher altitudes, where you now bring them to a region where they're now able to be thermally unstable, right? You drag them above this precipitation threshold, and then you create more rain. So you have this sort of weird scenario where the jet is simultaneously heating the gas, but also precipitating a lower level of cooling at the same time in a preferential direction along the jets, right? And because you do this, the system very quickly self-regulates at about 10 times at this threshold, right? I'm not saying this is right, but if you go read these rather convincing papers by Mark Voigt, you say, well, it could be totally wrong, but if it's totally wrong, someone has some explaining to do, right? And so this is what I've been working on for the past few years, trying to test this model with observations. It turns out to be not totally trivial, but that's what I'll talk about for the rest of this talk. You know a fountain in front of a fancy casino? A fountain has a pool. The water from the fountain drains into a pump, which then shoots the water out in a plume, and then it rains back down into the pool again, right? And so if you imagine the pump is this black hole, and the pool is cold molecular gas, I think that might be what's going on in this system. So you look at this fountain right here, and the plumes of water have all these very different morphologies, right? But nothing really fundamentally different is going on. It's still just a pump, right, that's shooting water out. I think that's what this is. I think these are plumes, okay, raining in and being pushed out, and all of this chaotic stuff, time varying, and maybe these are snapshots of what is ultimately the same galaxy at just different times throughout an AGN outburst cycle, right? So this is these are young stars. This is HST far ultraviolet continuum. The scales you're looking at range from about 100 parsecs to 50 kiloparsecs. The star formation rates you're looking at range from effectively 0 solar masses per year to 150 solar masses per year. And the point is that in simulations now, based on models that Massimo has pioneered and others in this room, we can recreate all of these observed FEV morphologies that we see with basically no physics other than an AGN and some cooling, right? You don't need to invoke mergers. You don't need to invoke large-scale gas dynamics or sloshing. You get all of these morphologies really easily in one run of a simulation. I'm showing Juan Lee's beautiful simulations here, but I could just as easily show Massimo's simulations or Karen's simulations that she showed yesterday, right? And so just to very quickly run through and show you how we recreate some of these morphologies, totally qualitatively. It doesn't mean this is what's going on. Here's Hydra A, for example, this beautiful rotating disk. Here's the same observations of Hydra A, where blue is X-ray, red is H-alpha, and the white here is the far ultraviolet disk. And if I show you the simulation, just one snapshot, no tuning, it's barely indistinguishable from the observations. And that turns out to be the case for all of these, right? At the same time that you match the morphology of the star-forming gas, you also match the star formation rate, which is really nice to see. But anyway, I'm not saying this is what's going on. It's just something to think about in the context of these fountain-like plumes that I'll talk about in a second. And then as a quick side note, and I wouldn't normally do this because I have about, 5 minutes left, there is one merger in this. So I'm showing you a small subset of a large sample of cool core clusters of galaxies. This is our only merger, so these are two giant merging elliptical galaxies. So this was our release last year. So these two giant elliptical galaxies are merging in the center of this strong lensing galaxy cluster. And there's this gorgeous 30 kiloparsec beaded string of star formation that spans the distance between the two nuclei. And we think what's happening here is that the filaments are breaking up into Jeans length clumps by what's effectively the plateau Rayleigh instability for the same physics that rain falls in drops from the sky rather than in unbroken filaments, right? A filament of fluid is inherently unstable and wants to break up into clumps. It turns out these clumps here are roughly Jeans length and equally spaced by 1 kiloparsec from one another. And the only reason I point this source out is because this morning I got a gorgeous Chandra observation, which I won't show you, but it's beautiful. It's beautiful. It really, the X-ray morphology follows the arms, and there's this bright ridge between the two nuclei. Okay, cool. I think the two merging galaxies are associated with two hot halos. You slam the galaxies together, you also slam the halos together, and so you could set up what I think is a higher density ridge of X-ray gas and maybe a waterfall of rapidly cooling gas at the interface between this merger. I don't know what's going on, but I just got the data, so give me a break, right? So fine. If these are fountains, so forget about the merger again, and go back to this sort of picture of nothing more than AGN heating and ICM cooling, and you get this sort of chaotic, messy flow that varies wildly through time. If these are fountains, do we see a drain? I think at least in one case the answer is yes, and I can only give you one case because it turns out that ALMA data is hard to come by. But here's Abel 2597. Okay, so I'll show you this one. So this is the Chandra image. That scale here is this is a couple hundred kiloparsecs. Like all cool core clusters, it has this beautiful network of buoyantly rising X-ray cavities. 100 kiloparsecs. Radio source that fills in the cavities, just like Perseus and M87, etc. And then here's the R-band isophotes of the host galaxy, the giant elliptical galaxy. And here it is. And like all cool core cluster BCGs, or most cool core BCGs, it has this beautiful 30 kiloparsec scale emission line nebula that spans the minor axis of the galaxy. Okay, so here's the emission line nebula in actually Lyman alpha in this case, but the Forbidden and Balmer lines look exactly the same. And there's to very quickly summarize a very long story, there's clear evidence for very, very rich dynamical interaction between the propagating radio source, which I've overplotted in red, and the star-forming gas here, as well as the warm ionized gas. You see the IFU maps are beautiful with these long, streaming, 300 kilometer per second outflows, possibly jet-triggered star formation here, et cetera, et cetera. Anyway, this is our ALMA observation. It turns out that the ionized nebula is actually also entirely molecular. I think what you're looking at is a superposition of many, 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 many cold molecular clouds with warm ionized skins, right? So I don't think this is a monolithic slab of gas. I think it's many, many individual smaller clouds that you see in projection. And then just for size scale, this radio source here is about 10 kiloparsecs from end to end. The fountain has a plume. In this source, we see a billion solar mass jet-driven cold molecular outflow, which would have been really cool news about 5 years ago, but now jet-driven molecular outflows are all the rage. So here's another one. So in the interest of time, I'll just be really cheap and have you take my word for it. But velocity maps and velocity dispersion maps, et cetera. It's a lot of mass in that thing. But what I think is the really cool part is the potential fountains drain, and that's what I want to show you. So we think we see a slow trickle of gas down the filaments, which I think is happening mostly in the plane of the sky, so you don't get much velocity information here. But if you go down to the nucleus in the ALMA data, I'm sorry I'm rushing so much, but this is ALMA CO2 to 1 data with almost the full array. So if you highlight if you extract the CO2 to 1 spectrum from, say, this messy region, you get that. And if you kind of zoom in and highlight this region of the spectrum, so at about plus 300 kilometers a second, you get this, right? And so what's this blue spot here, right? It turns out that this blue spot is exactly the millimeter core and the X-ray photocentroid and the radio core and the isophotocentrale of the galaxy. So it is a cross-section of the galaxy at whose very central volume lies the accreting supermassive black hole, right? And so if you extract the spectrum from here, you get these three very deep continuum absorption features. Okay, so these are at plus 300 kilometers a second, roughly. And what I think these are is giant molecular clouds falling into the innermost regions of the galaxy toward the black hole accretion reservoir on what are effectively radial orbits, because the infall speed of these things is almost a circular speed. So this could be a very low net angular momentum radial orbit. So a ballistic rain of cold molecular clouds onto the black hole, or at least into its accretion reservoir where it might wind up into a disk. In fact, you really hope it would. So they're continuum absorption features because they cast shadows. If the black hole is effectively a light bulb or a bright backlight, meaning it's the millimeter AGN continuum serves as a bright backlight, that backlight will cast shadows back toward the observer, right? And we see those shadows manifest as these continuum absorption features. I'm very much out of time, so I will really, really shortchange you on the argument here. But we don't think that they're in the galaxy outskirts for these reasons. We think they have to be within the innermost 500 parsecs. And so to summarize our cold molecular rain properties, we think these are giant molecular clouds about 40 parsecs in diameter, so like Milky Way type giant molecular clouds, 1 million solar masses each, a pretty big column, a nearly radial orbit, and about less than 500 parsecs from the black hole, which means a short crossing time because they're falling in at 300 kilometers a second, which means a really substantial mass flux that could power a super Eddington quasar if you were to dump all of it onto the black hole, which means some of it must wrap up into a disk on, I don't know, what, parsec scales? Fine. And in principle, you could reobserve this in a while and see a movie of cold chaotic accretion over like 1 year timescale. You should see the absorption features change. I'm out of time, so I will only advertise the close AGN reference survey because I'm contractually obligated to do so. We have this gorgeous MUSE data. MUSE is a 1x1 arc minute IFU in the south. And now we're doing Chandra follow-up. And this is a totally different thing. These are quasar host galaxies, nothing to do with cooling flows. But we see these beautiful radially expanding super bubbles expanding throughout these galaxies with ionized outflows. And we just got some Chandra observations of these, so I'll just leave these up to show off. Thanks.
We have some time for some questions? Well, let me ask you a question. Since you just gave us the molecular cloud masses, have you tried to convert that to the efficiency that you've seen in the AGN?
Yeah, that's right. Yeah. So
what do you get for that?
Right. So we calculated the mechanical luminosity required to launch this jet-driven billion solar mass outflow, and it turns out to be the same mechanical luminosity that you have being put into the X-ray cavities. So in principle, there's enough energy there. How a jet actually launches a cold molecular cloud, I really don't know.
Well, in
Paul
terms
Nelson
of
has
the
mentioned
cold
this.
molecular clouds you see falling in and converting that into m dot c squared, what kind of efficiency?
Yeah. No. Yeah, so you've got to wrap, so this stuff is probably low net angular momentum, but you can't accrete it directly onto the black hole because this thing would be a huge quasar, and it's very much not, right? So you have to wrap it up into a disk that then very slowly dribbles onto the black hole. Otherwise, you got a problem. It's a lot of mass that's falling. We see 3 clouds just along our line of sight at 1 million solar masses each, falling in on a very short crossing time. So that's a substantial mass flux to the accretion reservoir. Cold molecular mass flux, right? There's a lot of gas.
Questions from the audience? Yeah, back there.
This is really beautiful that you have this multi-wavelength outlook. Have you compared the second moment maps of these different tracers to, you flashed through that really quickly.
Yeah, I did.
Can you compare them to things like temperature maps from the X-ray data?
Oh, yeah. So let me very briefly. Okay, so there's a velocity map, so moment one, and these are dispersion maps, so effectively moment two. And we have differing versions of these maps with double Gaussian fits, etc. The long story short is that this is 3 sigma emission, but if you go really quickly, right here. So we have detailed comparisons with our deep Chandra observation in these filaments, and it turns out that the cooling rate, the m dot from the Chandra, which you got to be really careful, right, roughly matches the local star formation rate in the FUV. So there's really beautifully detailed stuff going on in comparing the Chandra map with this ALMA map. Turns out that Chandra looks at the rain cloud and ALMA looks at the puddle, right? And so they're directly connected.
Well, I have time for a quick question, if there's any. I think we're there.
So you said 1 kiloparsec is roughly where the radial flows would fall to. Is that particular scale well constrained? Does it fall into the inner kiloparsec or inner tens of kiloparsecs?
Are you talking about the molecular clouds raining in?
Yes.
Yeah, so I think based on a simple geometry argument and then virial and full width half max and continuum blanking arguments, I think they're within the innermost kiloparsec and probably closer to a few hundred parsecs. And so the absorbing, the things casting the shadows could be next door or way out in the outskirts of the galaxy. You can never know, right? The only thing you know is that the black hole's here and they're redshifted, so they're between you and the black hole, so they're falling closer to it. But all the 300 kilometer per second gas in emission is confined within the innermost 800 parsecs, right? So you'd expect to see the clouds casting shadows at least in emission, or at least the population that you draw from to cast those shadows. So there's no gas at 300 kilometers a second way out in the outskirts of the galaxy, at least projected in the 2D plane of the sky.
Well, let's thank our speaker.
Thanks.
All right, our next speaker is Kazumi Kashiyama. He has his PhD at Kyoto University and is now working as an Einstein Fellow at Berkeley University. And we'll be hearing about how to identify newborn black holes.
Thank you. So today I'd like to talk about one of the projects that I have been working on since I moved in Berkeley last year. That is how to identify or find newborn black holes, and especially in the era of time domain multi-messenger astronomy. Okay, thank you. Yeah, anyway, thank you. So, the target is not supermassive one at the galactic center, but stellar mass guys. So far, those are all found in the so-called X-ray binary. If you look at them with the optical telescope, you'll find a stellar counterpart. And from the spectroscopy and light curve, you can estimate the mass of the stellar companion and also the rotation velocity of the stellar companion. And by using Kepler's law, you can estimate the mass of the central compact object. And this is a list of the mass of the compact object in the X-ray binary. And as you can see, some of them have a significantly larger mass compared with a 2 or 3 solar mass, which is a kind of theoretical limit, upper limit of the neutron star mass. And these are most likely stellar mass black holes. So there do exist astrophysical stellar mass black holes. So people including me want to understand how they are formed. And although I'm a basically a theorist, but eventually in the future I would like to see some data, look at some data and say, oh, here is a newborn black hole. And to do that, as a theorist, I would like to consider what the possible smoking gun signal of the newborn black holes, and also the possible or optimal observational strategy in the era of coming time domain astronomy. And so to do that, one of the important questions is which progenitor produce black holes, not neutron stars. So as you know, there are several classes of massive stars which can, in principle, experience core collapse at the end of their evolution, red one, blue one, wolf-like star, they are totally different in terms of the structure, especially radius and outer density structure. On the other hand, whether or not the neutron star or black hole forms is essentially determined by whether supernova shock is stalled or not. And of course, still, this is a long-standing problem, and no one knows. There's no consensus about the explosion mechanism of supernovae so far. But there's a kind of consensus about the key to determine whether or not shock stalls or not is the inner density structure. When I say inner, that's say up to 1,000 kilometers or something like that, and also 2 or 3 solar mass in terms of enclosed mass. This is very natural because this is the most difficult part for the shock to go through. And if you calculate the so-called compactness of massive stars, this is the initial mass of the star, and this y-axis shows how compact the inner core is. And this kind of threshold value for the shock driven by neutrino mechanism can succeed, and above which stars would finally form shock stalls and the black hole formation would result in. So what I want to say here is that these are red supergiant, blue supergiant, wolf-like star. The message is that all types of massive stars can result in black hole formation. This is an important thing to discuss about the possible outcome and also diversity of the observational signal. So, but of course, the stellar time is not only the complication we have. There are well-known complications in all the entire astrophysical community. That's rotation and magnetic field, because how fast the progenitor rotates and how magnetized the progenitor is determines whether or not disk or jets are formed. That would be the key ingredients to discuss about the possible outcome. But unfortunately, it is currently difficult to do a first principle numerical simulation of black hole formation, including both magnetic field and rotation consistently. So, especially for me, that's difficult. And so today, I'd like to more schematically explore what the possible outcome of stellar black hole observation signature associated with black hole formation. So to do that, this is an interesting, useful figure given by Chris Kochanek. So it shows the possible bifurcation of pathways to finally form stellar mass black holes. One of the fascinating and the most violent way to form black holes is like this. So in case which the progenitor is extremely rotating fast, so that even the iron core rotates so fast to form accretion disk. And these accretion disks are so intense that they can eject a very strong, powerful jets and outflow, which can eventually drive an explosion, even if the supernova shock itself is failed. And finally, these shock outflow and jets can can power the most luminous transient in the universe, like gamma ray bursts and superluminous supernovae. And of course, this is in a sense, that's a very straightforward way to find newborn black holes. But the problem is they are extremely rare. So they are like 0.001% of the core corpus supernovae. On the other hand, say 10% massive end of the stellar star results in black hole formation. If that is true, these guys are kind of, well, very minor superstar in black hole community. So 1 out of 10,000. So very, very rare. And as an ordinary person like me, I'm more interested in ordinary guys in black hole community. So let's forget about these guys today and consider more ordinary one in the black hole society. So significant fraction of black holes should form in a more mild way. Maybe the most boring case would be like this. So star is not so rotating fast, and essentially everything is just swallowed. This might be the most boring case, but probably this is the most abundant case. Of course, that depends on the stellar rotation structure. But this may not be totally boring. So as proposed by Nodeschem in 1980s and recently confirmed by proof of concept simulation by Lovegrove and Uzre, in the case of red supergiant, which have a loosely bounded hydrogen envelope, those envelopes can be ejected away by a weak shock, which is driven by the mass, essentially driven by the mass loss of the protoneutron star by neutron emission, the gravitational mass loss of the core of the mass loss of the protoneutron star. And this shock is still weak, but since the hydrogen envelope is highly loosely bounded, so they have an explosion like this, and eventually these kinds of events can result in red transient and with a luminosity in between the nova and supernova. So, and this is a unique detectable signal, so it might be interesting to see these. And actually, there are candidates of these events. So people, mainly in Ohio State, people do interesting monitoring. That is, they monitor 10 to 6 red supergiant in a very close universe, say up to a few tens megaparsec. Since the lifetime of the red supergiant is like 10 to 6 years, so if you monitor 10 to 6 stars, you would have 1 collapse every year. That's good, very, very straightforward, nice strategy. And actually, during the 5-year or so observation, they discover 3 co-collapse supernova and 1 luminous red nova-like candidates. So this, well, of course, still we need to be careful about, careful to claim this is the case, but we may start to see some interesting pathway to form black hole, black hole formation here. So this is the case of red supergiant. So how about the other progenitors? So as I said, both blue supergiant and Wolf-Rayet is a kind of possible progenitor of black holes. But unfortunately, in these cases, they have a very tightly bounded envelope. So the shock like this is not powerful enough to eject the outer envelope. But so then let's consider not totally not boring, but not simplest, but still not boring, but second boring case. So they have no extremely rotating. They do not have extremely rotating core, but still mildly rotating, and only minor fraction of the outer layer can form a disk, and that kind of thing can happen. Maybe not so rarely, and I think like this because this kind of state of evolution calculation in which they assume this is results of the state of evolution angular momentum density, and this is a blue supergiant case and Wolf-Rayet in binary. Anyway, what I want to say is that So in this calculation, they assume as the initial condition rotation consistent with the OB star observation, and what they found is that what I mean is there's no fine tuning. They just do up-to-date calculation based on the observation. And what they found is that a tiny, minor fraction, this is a calculated angular momentum density, and the solid line shows the threshold angular momentum density to form a disk around central black hole. So as you can see, a minor fraction of the star, say a few solar mass, at most a few solar mass, can form a disk, but other than that, everything just swallowed. Those kind of situation maybe naturally happen in the old black hole formation. This types of collapse happens. What we expect would be like this. So everything except for the outer layer swallowed, and only tiny fraction form a disk. So let's consider what will happen is my question. So as I said, that in both Wolf-Rayet and blue supergiant case, say up to a few solar mass, only a few solar mass can form a disk, and these mass shell falling down very, very close to the black hole with a time scale of free fall time. That is, and the mass accretion rate is essentially determined by this mass divided by free fall time scale. That is still much, much higher than the Eddington accretion rate. So, and like this. So, as you can see here. So then what is the outcome? As we know from OREX simulation and also EFAN's simulation, the results would likely the strong outflow ejection from the system. Because the accretion rate is super Eddington, it is likely to have outflow, say 10% of the disk mass ejected away with a velocity close to the escape velocity. And by plugging these numbers, we can estimate the temperature at temperature at the launching radius and density and so on, and let's say assume these wind keep on going with the time scale of this accretion time scale, then we can know how the wind evolves in terms of density and temperature. At the launching radius, these wind are highly optical thick and high temperature. But as the wind expands away, the optical depth decreases and temperature also decreases. And finally, at some point, the radiation comes out. And that's what we calculate using a very simple analytical model. The result is that this kind of event can result in optical transients with a duration of days to 10 days or something like that. And the luminosity is roughly comparable to the supernova. Very rapid but still bright transients. And temperature, typical observed temperature should be like 10 to 4 Kelvin, so very blue spectrum. This is what we obtain from the very simplified analytical model based on this picture. And so our point is this kind of event may be observed, and actually this kind of similar new class of transients recently discovered by a survey project led by Maria Drout here in Harvard. What they discover is roughly broadly consistent with what we predict. Say the duration is very, the evolution of the light curve is very fast compared with the supernova. Supernova case, the light curve evolves with, say, a few tens days. But in this case, much smaller, significantly shorter than that. And peak luminosity is something like this, as bright as supernovae. And temperature is 10 to 4 Kelvin, a few times 10 to 4 Kelvin, or something like that. And there's no line bracketing signal. That means the energy source of this event is not nickel powered, but something else. So that's also consistent with our scenario. And their host galaxy is star-forming galaxy. And the interesting point is that the event is not so rare, like 4 to 7%. So this is very interesting for me. Well, they are not rare. They are not discovered. They are not frequently discovered so far because this type of high cadence surveys now it's possible, but previously it's not possible. So we start to see some this type. So anyway, yeah. And the point is that these guys are not rare. So that will be interesting in terms of the black hole formation scenario because, as I said, black hole formation itself may be not so rare, and that will be consistent with these kind of numbers. So here's a summary. And so we start to see, so the motivation is want to find newborn black holes to understand how the black hole forms and how that relates with the stellar evolution and galaxy evolution and so on. And we start to see some interesting candidate events, including vanishing stars, luminous one, and in our case, fast blue transients. And I think that this is not enough as a smoking gun, because this optical transient can be, this type of fast transient can be formed in a different scenario. For example, some tricky shock breakout event or something else. So I think to claim this is really the case of black hole formation, we need multi-messenger or multi-wavelengths approach. For example, in our scenario, it is inevitable to have radio counterpart, very, very strong radio counterpart, because this will be quite similar to the tidal disruption event and so on. So hyper-radiation accretion disk and a strong outflow, and these outflow can inevitably produce radio counterpart. And also maybe these disks can experience Papara spring-like instability, then the anasymmetric structure forms in the disk, and that can be a plausible gravitational wave source, because this kind of event can happen in, say, a few 10 megaparsec or something. So that can be detectable in terms of scarcity order of magnitude estimate. So these kind of arguments would be interesting in the near future.
Time for some questions over here.
So what's setting the maximum volumetric luminosity? Like why is 10 to 43 the brightest that they can get?
So in our scenario, the intrinsic energy budget is the energy dissipation occurring here. So that is determined by L equals G times M dot M divided by circulation radius. And then after that, all we assume is, in some sense, conservative thing, just adiabatic cooling after that. And the wind blows with escape velocity and just experiencing adiabatic cooling. So in that sense, energy brightness is determined by the energy injection point and mass ejection rate, because that determines the point where the wind becomes optically thin.
So it could be brighter in principle.
Yeah, I tried, but this kind of maximum. So if you're trying to have, say, 10 to 44, it's tough.
I mean, the reason why I bring it up is that there's a bizarre tidal disruption, plane
Yeah.
disruption event, W, which is
Yeah.
maybe 2 orders of magnitude brighter than
Yeah.
this thing. So the interesting thing about it is it's very short in duration.
Yeah.
It's only peaking in a few days.
Yeah.
It's very hard to fit that with the normal PDE model.
Maybe it's elevated? Elevated?
I'm not sure.
Radiation elevated?
Yeah.
So intrinsic luminosity is less.
Yeah, or you mean in this case?
Yeah.
Yes.
Yeah, and in your case, would you expect collimated outflow?
Well, not really. Well, basically here we assume the approximately spherical wind. But I noticed that event during playing with this, that it's difficult to reproduce the observed data.
Another question? Yeah, Jack?
Can you say something about what sort of spin you expect to be associated with the black holes that form sort of in this case?
I have no idea. Of course, if you use, well, yeah, for example, if you use this kind of pre-corrupt structure, and then you can say what, you know the angular momentum density here, so you can argue what the possible car parameter when these guys circulate around the black hole. But I do not dig into that point. So that may be also, well, of course, that affects the factor 2 or 3 of the circulation radius and so on. So that will be important in terms when you're trying to discuss more details of the this scenario. But yeah.
And there's something that you'd be able to access from this.
Yeah. At least we can access.
Maybe if there's a quick question while we swap out the computer. Thank the speaker again. Okay, next up we have Ashley King, who did her graduate work at Michigan, and now brief stint at Cambridge as well, very briefly, and chose to go to God's country. It's my alma mater as well, way back in the day. Very good changing the winter weather for California. So we'll hear about some really interesting high-energy transmission gradient spectroscopy of a very fascinating black hole.
So hi, thanks Mike, and my name's Ashley King. I'm at Stanford, and before I begin, I just want to thank all my collaborators, especially John, who has not only been integral in this work, but I think has just as much enthusiasm for this data set as I do. Excuse me. And I'd also like to thank the Chandra team, not only Belinda, but also the calibration team for granting us this targeted opportunity and helping set up these gratings and not burning a hole in Chandra, as this is maybe the brightest or second brightest source that Chandra has ever looked at. So thank you guys very much. So for those of you who don't look at X-ray binaries, shame on you, but I just want to give you a little overview of the transient behavior that many of the X-ray binaries go through. So many accreting black holes spend most of their time in quiescence, so we don't really see much of them. But every once in a while, something happens in the disk, and we have a change in mass incretion rate, and they start increasing in luminosity. So we generally think that they follow this trend in what we call the hardness intensity diagram, or the Q diagram. I've even heard this called the turtle diagram, as it kind of looks like a turtle's head. But anyway, it shows the X-ray luminosity on the y-axis versus the spectral hardness on the x-axis. And what you really just need to take away from this is that everything on the left here is thermally dominated by the accretion disk, and everything on the right here is dominated by a power law, which we associate with the corona. which may be a hot atmosphere above the accretion disk, or it might be associated with a jet. But regardless, our black holes start accreting. They rise in luminosity. They tend to be very hard. And while they rise in luminosity on this side of our Q diagram, they also tend to have strong but compact radio emission. So we know that there's this compact jet that's associated with this hard accretion state. Then if they reach a high enough luminosity, they make this transition into this thermally dominated state. And this is where we see the optically thick radio emission move to optically thin. And in the best cases, like GRS 1915, we see relativistic jets move out as it transitions to the soft state. Now, in the soft state is not necessarily boring. We actually have outflows that are associated with the accretion disk here, but instead of highly collimated jets, they're now wide-angle winds, which we actually see in absorption in the X-ray instead of emission in the radio. So there's still interesting outflows that are associated with the accretion disk here. Now, X-ray binaries can go through this behavior quite often, or if you're like V404 SIG, which I'm going to talk about today, it didn't happen. The last time it went into outburst was in 1989. And I think before that, I mean, of course, we didn't have any X-ray telescopes much before that, but we have optical nova of the source, and it went off, I believe, in 1956, and in 1938 we actually have it. So every 30 years or so, you know, plus or minus a few, the source likes to go into outbursts for maybe a couple weeks, and then go into quiescence, and we don't really hear much from it. But in terms of typical X-ray binaries, V404 is actually pretty typical. So here is a plot of X-ray luminosity versus radio luminosity of V404 in its 1989 outburst and then into quiescence. And you can see it follows a similar relation to two other X-ray binaries, GX339-4 and XEJ1118. So it's pretty typical in terms of its quiescence X-ray and radio luminosity as well. But in June of this year, we had a bright outburst. So here's it quiescence, and then June, I believe it's 14th or 15th, SwiftBat detected this outburst, and this thing got really bright. I mean, we're talking, I think the record in the X-ray was an instantaneous flux of over 50 crab, 50. I mean, it just got extremely bright. And just about every telescope on Earth and in space has looked at this. So we have everything from radio, infrared and optical, all the way up to X-ray and gamma ray. And of course, the best telescope, Chandra, looked at it on June 22nd and actually June 23rd as well. We originally had one observation scheduled for June 22nd, but the universe conspired and had a solar flare, so we had to put Chandra in safe mode. And then the Chandra team was nice enough to finish our observations the next day and give us another 25 kiloseconds. And you can already see here we have a wonderful signal to noise. We have clear emission lines, both at low ionization states and high ionization states. And there's even a difference in continuum just between these two epochs. And not only do we see this variability between the two epochs, but we actually see variability within each observation. So this is the second observation, and I've divided it into about 3 kilosecond segments. And so time goes from the bottom here to the top. And I'm just showing 4 different species. So you have magnesium and silicon, sulfur, and iron, different lines here. And what's amazing is, I mean, we've just scratched the surface of this data set. We're going to be able to look at the changes in ionization state throughout these different epochs. And what's interesting is you'll see that mostly we see emission, but at the highest flux, oh, I should mention that the flux also increases throughout this observation. At the highest flux, we actually see evidence of absorption and, in fact, P Cygni profiles. So there's an outflow at the highest luminosity in these observations. So we just have a plethora of information that we can learn from all these different ion species, both at low ionization, high ionization, and we've just begun to look into what this data set is trying to tell us. So the obvious thing is, first thing is to use the helium-like triplets we see. So here is the silicon triplet, these 3 lines here over the different epochs. And we can use the ratio of the intercombination and forbidden lines to either give us an estimate of the density if the UV field is unimportant, and that gives us a pretty high density actually of about 10 to the 13. But we know from other observations, which aren't necessarily simultaneous, but we know that the UV field is quite bright in this source, and so probably we have a lot of pumping of the intercombination line. So instead of giving us a density estimate, we actually have an estimate for the radius of emission, and that puts it at about a few by 10 to the 11 centimeters. And to give you an idea, the orbital separation of the system is a few by 10 to the 12. So we're looking at emission in the outer disk. We can also use the ratio of the resonance line to the forbidden intercombination line to understand if the gas is collisionally or photo-excited. And we find kind of an intermediate case. So what might be happening is we have the lines are being photoionized, but collisions might becoming important. Or what we actually think is really happening is that we have some contamination of the resonance line by a wind, which we see as evidenced by a slight change in the velocity in the emission line, as well as the absorption at high fluxes, these P Cygni profiles. So likely this is giving us a higher ratio than we should really be measuring, and we're more likely in the photoionized case. So we can also use a separate line of tactics, I guess, to measure the radius of emission using the emission measure and the column density of the silicon lines, and we get a slightly further out radius of about a few times 10 to 12. Again, this is right near the binary separation, so we're looking at the emission at the outer edge of the disk, and it gives us a more reasonable estimate of the density of a few by 10 to the 10 per cubic centimeters. Now, what's really interesting to me is looking at the outflows that are produced during this outflow. I should mention that at the outflows that we see these absorption features and emission red word of these absorption features is at the highest luminosity. Now, just taking the luminosity at face value, this is a few tens of % of the Eddington luminosity, and that's not even accounting for the absorption. So likely the source is going near its Eddington limit during these highest fluxes. And that's really interesting because we expect these outflows when sources go super Eddington. And so we see these outflows, and this is your typical P Cygni profile. Now, to remind you all what a P Cygni profile is, if you have an emission with an outflowing shell, you're going to get absorption along your line of sight that is blue shifted towards you, and then the emission from the rest of the sphere will be at the rest wavelength or maybe slightly red shifted, and you'll get this profile that looks like this. Now, the interesting thing is we don't necessarily have a spherical outflow. We know that there's a disk, and that's going to change the geometry of this profile. And actually, by measuring the geometry of the line profiles that we see, we can get an estimate of a number of different parameters. So you can see here that the line profile will depend on inclination. When you're face on, you're going to be getting most of the absorption component, and when you're edge on, you see more of the emission. V404 is about 70 degrees, so we see a lot of emission, but we do see some absorption in these profiles. Then, of course, the line profile will also depend on the mass accretion rate, and it also depend on whether the wind is accelerating or not. You can see here that at low ionizations we have a very narrow absorption feature, but when we move to the high ionizations we have a very wide feature, which is suggesting that it's not a constant velocity, that maybe the wind is accelerating in this picture. Let's see. Oops. There we go. Okay, so I just want to compare V404 to typical X-ray binaries. As I said, we do see these absorption winds in typical X-ray binaries, but this is in a thermally dominated state. The winds in V404, which you can see here are in a state that's still dominated by the parallel. So they're intrinsically different from your typical X-ray binaries. So this is at high energies. This is iron 25 and iron 26, and you can see clear absorption here. And we see the absorption, it's only less clear because I didn't put a great axis on this. But you can see here the same absorption, but we also have emission in V404 here. The other thing I want to point out is that the velocity shifts here are maybe 600 to 1,000 kilometers a second, whereas in V404 we have up to 4,000 kilometers a second outflow rate. So the other thing that differentiates V404's winds is that typical X-ray binaries are in this thermally dominated state by the winds. So wind detections are shown in these circles. Upper limits are in these triangles. And V404 is over here. It's in a very parallel dominated state that's reaching its Eddington limit. So there's something intrinsically different about this wind than your typical X-ray binaries. We can determine the mass outflow rate using the velocity and the ionization. Sorry, this should be 10 to the 3, not ionization of 3. And we find that when we calculate the mass outflow rate of the wind compared to the X-ray, the mass accretion rate inferred by the X-ray, we get a factor of 30 times greater, which means that the wind is disrupting the outer disk, is blowing a lot of material, and only a little bit amount of material is able to accrete onto the black hole. In the future, we're looking into more physical modeling of this data set. So here is just the preliminary results using X-star, using supersolar abundances, which we get from the optical companion, as well as a density of few by 10 to the 10. And you can see it has a nice fit here at low ionizations, but we're still having a hard time fitting at high ionizations and getting the velocity structure. There's still some residuals. And so working with John, we're working on a more physical model of the wind acceleration and the P Cygni profiles to take this into better account. So I'll leave you with my conclusions, and this is a really great and fun source to work on, and we have lots of work to do in the future with this data set. So thank you.
Lots of time for questions. Back there, Frank.
That's amazing, actually. Thank you for developing Chandra. Can you show that observation too again, and the variability of your line structure?
Sure.
The magnesium line, the shape variability looks really weird and unlike your other lines. And I'm wondering if there's an interpretation for that.
We've been primarily looking at the time average. We haven't modeled the individual segments yet. So I haven't thought in particular about that yet, but I will.
Yeah.
So what was the luminosity and Eddington units for these two observations? And how long were these observations? And was the source very variable during these observations?
So the source was variable. It varied by over a factor of 10 or so. But the average luminosity was actually pretty low. It was about 5 or 10% of Eddington. So Eddington for the source is about 10 to the 39, and this is just about 10 to the 37 is the average luminosity of these. 1% of it. Yeah, but this is the absorbed flux, so it doesn't take into account. It's not the unabsorbed luminosity, and I mean you can see how flat the spectrum is. There's definitely some absorption.
So that's the absorbed 2 to 10?
Yeah, that's the absorbed 2 to 10. Sorry?
That's just the luminosity in the Chandra band?
Right, exactly. So the bolometric luminosity is much more luminous. We were definitely conservative.
Jack? I just wondered, I guess since you said it was varying by a factor of 10 or so, that may rule this out, but I wondered if you had thought about checking for any signature orbital variability, see if I don't know, you can see any sort of spots in the disk or something that might be...
Like a QPO or something like that?
No, I mean, like if you might see some line changes sort of indicating that the wind is a function. Seeing changes in the wind is a function of orbital phase.
Yeah. So the orbital period is about 6 or 7 days, 6.5 days, I think. So it's on a lot longer time scale.
When was the peak?
When was the peak? It was... So our observations were kind of in between two peaks, but I think the brightest was a day or two after our observations. So.
back here.
The outburst lasted for a week or so, right?
Yep.
So what is special about this source that the ratio of the outburst to quiescence is so small?
That is a good question. I don't think we know enough about the triggering mechanisms. We do know that the optical luminosity preceded this, suggesting that the accretion event was from the outside in, so something, maybe the ionization or viscosity changed in the accretion disk, but I'm not sure. There are many X-ray binaries that are in quiescence that have, we see them outburst once and then they're in quiescence. So I don't think it's unusual for the entire population. We're just dominated by selection effects of the most persistent X-ray binaries.
Are there up the top there?
Can you comment on why the winds on this source might be much higher than the typical X-ray binaries?
Sure, I think there are different driving mechanisms. So let me see. There we go. In typical X-ray binaries, we think that they might be magnetically dominated, whereas in V404, you either have high radiation pressure, so radiation-driven wind, or actually the spectrum gets quite hard at these high luminosities, so we might be reaching the Compton temperature, so it might be a thermally driven wind as well. So I think it's a different mechanism that is driving these winds as compared to the soft state winds in regular X-ray binaries.
Any other questions? If not, let's thank Ashley again.
Thanks.
Next up, we have Jack Steiner. Jack is local. Did his PhD here at Harvard before brief stint at Cambridge, before coming back to Harvard with a Hubble Fellowship, and now has moved to MIT with an Einstein Fellowship. So he'll be telling us about measuring spins for stellar mass black holes.
All right. Well, this is my first year here, so I want to say thank you very much for giving me this opportunity. It's a great honor. And because I'm almost 4 weeks in, I'm not going to be telling you about my work so far in the fellowship, but I'll tell you just a bit of backdrop about black hole spins, and I'll sort of discuss where I hope I'll be able to go and maybe take you with me in the next couple of years. So just to remind everyone here, wonderful black holes are incredibly simple. They're described completely and fully by just 3 numbers, according to the no-hair theorem. That is their mass, spin, and charge. But of course, in astrophysical settings, black holes are embedded in plasmas, so charge goes to 0. And so it's really just 2 numbers, masses and spins, that completely tell us the properties of the black hole. That's a macroscopic object. Is sort of a remarkable thing. I mean, it's in fact so remarkable that I don't trust myself to communicate that to you adequately. I'm going to sort of invoke LeVar Burton and don't take my word for this. So I'm going to go to Chandrasekhar, who I think is an eminent enough authority here to impress you. So Chandrasekhar said that the most shattering experience of his career was to realize that the exact solution of Einstein's equations in GR, that is effectively that this no-hair theorem describes black holes, that this provides the absolute exact representation of untold numbers of black holes, that's the most shuddering experience of his career. That's a powerful statement. So hopefully you are all interested in the property of black holes, the spin. And that's what I'm going to try to tell you how we go about measuring. In fact, there are a few techniques around, but the backbone of most of these methods for measuring spin is really to pull out the inner edge of the disk. So if you put an accretion disk around a black hole in GR, you get a special radius, this innermost stable circular orbit, inside of which if you pluck a little parcel of matter, it'll just plummet into the horizon dynamically. So it's effectively, there's this truncating edge, this ISCO, and everyone is trying to measure this. And the reason we want to measure this is because it's intimately related to the spin. As if you have a non-spinning black hole, this ISCO radius is at 6m, which for a stellar mass black hole that I'm interested in, it's 90 kilometers or so. And if you have an otherwise identical black hole but just make it maximally rotating instead, this inner radius goes down by a factor of 6 to 1m,
15 kilometers. So this change by a factor of 6 may not sound like much, but in terms of the radiation that you get out as an observer, it's dramatically different. So here I'm showing you just taking, again, the same mass black hole, in fact, the same mass accretion rate, and just ratcheting up the spin. And this is showing you the amount of luminosity coming out as a function of radius. And you see you get dramatically more emission. And in fact, this goes up from about 6% to about 40% as you go from 0 to 1 efficiency. And you get more and more emission from closer in, so it's hotter, everything's brighter. So this is the change that we're trying to measure as observers. So there are, in fact, two main methods by which spin has been measured. There are others. You know, we hope to get a polarimeter. We hope to be able to use timing and some other signatures. But these are the two major methods which are producing results for black hole spin. So I'm going to mention both of these as continuum fitting and the iron line or reflection technique. I'm going to begin with continuum fitting, which is wonderful because it's also a very simple idea, and I think all of you will be familiar with the challenge of how do you measure the radius of a star when you can't actually resolve it on the sky. Now, and blackbody radiation is wonderful. It only cares about the emitting area and the temperature. So that is to say, if we can go out and measure the temperature of a star, which is straightforward to do, and if we can also calculate its flux, which is straightforward to do, then if we know the distance, there's a unique mapping between the observables, flux, temperature, and which gives us a solid angle, and the radius of the star. Very simple. It's just drops out of blackbody radiation. Well, now a thermal accretion disk might sound a little bit trickier, but in fact it's the same problem. It's just instead of a single temperature, I have a temperature profile, and instead of a sphere, I have a cylinder, so there's a projection effect. But in fact, all I need to know is sort of a characteristic temperature, the flux, distance, and now inclination because of that projection, and I can measure a radius. It's beautifully simple. It turns out that I really want the dimensionless spin parameter. So what I need to do to go from r-ISCO, which has units of kilometers, into dimensionless spin is I need to know the mass. That sets the scale. So distance, inclination, and mass together with an X-ray observation of a black hole give me spin. And that is lots of data that look something like this are each able to provide an estimate of a black hole spin. So this is one of several hundred observations we have for this particular black hole system, LMCX3, and this is quite typical. I'm showing you here a nice thermal disk component. This is the not trying to jump into the future there. This is the thermal disk component that contains the information about spin from just the continuum model I was describing, and there's this sort of nuisance component. This Compton power law that Ashley mentioned, this comes from the corona. But this disk component is about 90% of the story for these sorts of data. And again, we have maybe tens, hundreds of such spectra regularly for our systems. And it's very straightforward to model them. So of course, you're probably wondering to yourself, how well can you measure spin? Well, this is how well we can do. I should warn you, this is a little bit abstract here. On the bottom are units of spin. On the top are units of inner radius in terms of the ISCO. So this is ISCO units, and this is spin units. The reason I'm showing it like this is you'll notice that the spin or the inner radius spacing is quite regular. This is because this is really our measurement space. We're sensitive to radius, but we're interested in spin. So things are nonlinear here, but they're pretty well behaved in radius space. So we can get roughly a 10% constraint folding in all of the systematics that we think we know about. You know, there might be some hidden piranhas or something that are getting us, but as far as we're able to estimate systematics, fold in statistical uncertainty, we can get about 10% uncertainty in the inner radius. Here that translates to about 0.1 in spin. So this is what we can do. And the next thing that you want to know is, well, how reliable is this method? Can I convince you that this is actually fairly robust? Well, the same system, LMCX3, happens to be a wonderful test case. It's been it's a persistent source, unlike many. I actually showed you this Q diagram that most systems go through that are transients. This one just hangs around staying X-ray bright. So since X-ray detectors started flying, we've had data on LMCX3. This is showing you the history of that source. This is a light curve spanning sort of reliably calibrated X-ray data. And we've taken all of this data, some 700 spectra. We've isolated with some selection criteria. If you really want to know technical details, you can ask me about. But there's this luminosity window where we think our model is most reliable, and we measure the inner radius, and we find that we can recover something that's constant to about 5%. So that's roughly the scatter that we get over decades for this one system. So our measurement is repeatable to about 5% precision. So that we're measuring some constant, some fundamental of the system. This gives us faith that we're actually probing spin and not just chasing our own tails. So with that sort of as backdrop on the continuum method, I do want to touch base on the reflection method. Now, as Ashley described, we have a disk around the black hole. We have a corona. And in fact, we don't know much about this corona. This is sort of the dark art of black hole spectral modeling is there's a corona and you need to know its shape and properties, and no one really does. So we sort of try to parameterize our ignorance as best as we can, but this is a continual source of frustration. In any case, what we do know is that this corona intercepts photons from the disk, and some of those photons are then returning to the disk, illuminating it, and we just term the reprocessing of those photons reflection. So this reflection component shown in green, you see the illuminating spectrum. In blue, you see the corresponding reflection in the local frame. In red, you see the integrated reflection that we observe. This is what we get back from the disk. And sort of this seemingly subtle feature here imprinted in the reflection spectrum is the iron line. Turns out to be the dominant observable feature from this so-called reflection component. Now, the reason we're interested is reflection is another way of probing the inner radius, telling us the ISCO, letting us infer the spin, because as you ratchet up spin from 0 to 1, you get this extreme red wing that comes out of your iron line because you're going further and further into the gravitational potential. So in a nutshell, this is how reflection works. And I want to just advertise, this is the brightest, or this is the highest signal reflection spectrum that any of you will have seen. At least to my knowledge, this is the most reflection that's been assembled together ever before. This is really great work done by Javier Garcia, who's just across the hall there. And this is for GX339. So this is the iron line right here, and this is a related feature called the Compton hump. In any case, so this is sort of the overview picture for how we go about measuring spin. And this is the punchline. This is about 10 years of work from my group and other groups who've been dedicated to this effort. And this is showing you roughly 20 systems for which we now think we have a pretty good handle on the spin with continuum fitting method and iron line methods. And this is approximately ordered from low spin to high spin as you go from bottom to top. So this is what 10 years of hard work has brought us. And now I think we're in a position to say, well, we have a lot of spin data, and what comes next? So this is what I want to do in my next few years here. These are questions I'm interested in, and I'm only going to spend time to tell you about one of them because I don't have time to talk about everything. But I think the most interesting questions in front of us are to figure out, first of all, how well do the two methods agree? This is more, I guess, technical, but we want to be able to understand both methods. We want to calibrate this and make sure that we're actually getting independent measurements for as many systems as possible. But sort of getting to fundamental physics, we want to know what gives us the spin distribution that we observe for these black holes. Is there one class, or the persistent systems distinct from the transients and so on? And there are interesting questions about the formation, as you heard from Kazumi earlier. we want to know, is there a link between spin and jets? This is one of the great outstanding questions in astrophysics of black holes. And I think whether you're supermassive or stellar mass in nature, you're probably wondering about this. And there are two big challenges in front of us, at least that I see. One is really to develop the models to make generational improvements and to bring full consistency where we're using something that's a Comptonized disk and it's also producing reflection all at once in a way that's mature and robust. We've really sort of handled either one half or the other, but not brought the two methods together in a consistent way. And ultimately, a signpost that I think is decades down the road, so I don't want to give you grandiose illusions that we're at a place where we can start doing this yet, but I think it would be terrible to ignore the possibility of using these methods to probe strong gravity and ultimately test GR. If we're in a position, hopefully sometime soon, that we really understand these methods very strongly, then I hope this is something that we can tackle with maybe another generation or two of X-ray detectors with a lot of work paving that road right now. So I just want to very quickly advertise what we've done so far investigating this question, the link between spin and jets. Here in green, I'm highlighting for you all of these black holes that are microquasars, that is, they produce jets. And this is showing you work done by Ramesh and Jeff and a little bit myself a couple of years ago, looking at the relationship between these so-called ballistic or transient jets and a few of these sources for which we've measured spin. I should say this is a result that's been highly controversial. There are other groups who strongly disagree with this. We have some predictions, so we hope to be able to test whether or not this relationship holds up, but we have at least an indication, a controversial indication, that there may be a link between the so-called jet power and spin of the black hole. So with that, I'll put up my summary here. We're measuring spin with two methods, continuum fitting and reflection. I didn't have time to talk about it, but they are consistent with one another to within about 2 sigma or so. I showed you that with LMCX3 we have good evidence for a stable inner radius that we associate with the ISCO, and that we've measured about 20 stellar mass black hole spin so far. So stay tuned. In coming years, I hope to address more of these questions and have a good story for you. Thank you.
Questions? Yeah, in the back here.
Could you say a few words about what dominates the uncertainty in each of the cases? Like, is it the inclination or the distance or continuum, like where you place it?
Yeah. So I would say right now for continuum fitting, I'm going to start back here. So for continuum fitting, the sort of width of this is usually set by our limited understanding of our limited constraints on inclination and on distance. Usually those are the two things that we know most poorly, especially if the inclination is rather high. It's a big limiting factor for us here. You know, there's always a possibility that there's some systematic that we don't have that we're not aware of, that we don't have a good handle on. But in general, because the continuum has so many counts, we're pretty robust in terms of signal, and it's just about having sort of the other inputs to the model. For the iron line, I would say there's more uncertainty in the model itself. You need to know something about the shape of the corona, and you're also modeling a regime where I guess I can sort of here. So the iron line peaks right here, which is roughly the regime where the power law and if there is a disk competing with it, everything is sort of happening in one little window. You have to know what the ionization is doing. So there's more knobs, I guess, to tune for the iron line model, and Javier in particular is doing tremendous work sort of advancing the state of those models, but I think there's a fair way to go, and there hasn't been as much investigation of the systematic model dependencies. So I would say that for iron line fitting, I see that as the sort of the way to make the most progress is to sort of make advancements on the modeling side.
Yeah, in the back
Yeah. So Yuchang Zhu and Akshay Kulkarni both led efforts to do this here, and then Julian Krolik's group has also done sort of similar work too, to try to assess, looking at synthetic spectra to test the effect of any sort of deviations in MHD simulations. So there's, I don't think I have the authority to say that there's consensus. I think there was more disagreement previously, and there's less disagreement now, is my impression. But the answer that Yuchang found most recently is that sort of there's a 1% or few percent error introduced in the inner radius when you consider modeling of those simulations. And I think Julian's group found something like 20% in terms of the effect on inner radius. But I think there were contention about which effects were included and not included by the team. So I would trust Ramesh's overview of that better than mine.
We had a question back here.
Your last view graph was really interesting. It shows that you get a lot of jet power for retrograde spin. But I noticed that you only have one source at the very bottom of your list that maybe has a retrograde spin. So do you think you can have those spins, or do they not exist in nature?
Yeah, so that's a very interesting question. There's been one strong claim recently for a retrograde source, this microquasar in M31. However, the mass isn't really known here. So I think there's a question mark with this, especially in terms of the error bars. But it seems like at least most of the transients don't want to have retrograde spin. Now, the reason that the other direction, the reason that my plot goes up here is I just plotted sort of spin squared, which, because the axes are a bit funny, it looks that way, but I think Sasha would tell you from sort of theory and simulations, you expect this trend, but that the retrograde would sort of peak lower by a factor of, I don't know, a few, compared to the prograde case.
I think we have to stop there and move on to the next speaker, so let's thank Kathy Ellis. Okay, next up we have Alexander Tchaikovsky, who did his graduate work at Harvard and is now taking his Einstein at Berkeley. And we'll be hearing about simulations of low luminosity black hole accretion jets and their emission.
Thank you very much for the introduction, Mike. It's an honor for me to be here. It's my final year of the Einstein Fellowship, and it's been really fantastic to be able to do all this exciting research. And now I'm going to share you one of the recent things that, a few of the recent things that I've done. What I'm going to be focusing in my talk here is how can we invert the observations that we see of black holes and translate them into physical understanding and constraints, what's going on near the black hole event horizon. We can observe black holes by looking at the spectra. In the next couple of years, maybe 2 or 3 years, and Shep will tell us exactly when it's going to happen, we expect to observe images of black hole shadows, actually images of the black hole shadows. So this would be just a few black hole gravitational radii. And how we're going to do this, we're going to make a really big telescope by correlating inputs from many radio dishes scattered around the globe and making them into a telescope with the diameter equal to the diameter of the Earth. And then at millimeter wavelengths, this will allow us to beat down the diffraction limit and actually get down to small scales to actually picture the black hole. And on larger scales, where the jets interact with the ambient medium, we can also hope to extract some information about near black hole physics, because these jets, they start very close to the black hole event horizon, and therefore they in principle carry away some information, so it would be interesting to try and unite all of these types of observations into one single coherent picture and try and back out as much understanding of the central engine as we can. So what kind of life cycle do black holes go through? We've heard that black holes go through bursts of activity, and there are different types of astrophysical systems that host black holes in different states. So here I ordered them very simplistically by this parameter that I call lambda. This is the Eddington ratio. It's the ratio of the luminosity that we observe to the Eddington luminosity. Here I defined roughly 3 states. Super Eddington state, it's a very luminous state where the black hole is consuming gas at a really high rate, and we saw we saw a few talks that discussed tidal disruption events that we think are occurring in this state. We also expect this to be powering ultraluminous sources, at least some of them, ultraluminous X-ray sources, and gamma ray bursts are another example where, for instance, this Eddington ratio is 14 orders of magnitude greater than unity. So we do know that such states, said black holes in such states exist. In between maybe 1% and 100% of Eddington, we have Kolmar, thin disk. They are really radiatively efficient, and these we think power quasars, black hole binaries, and maybe tidal disruption events. Once most of the star has been accreted on the black hole, mass accretion rate goes down, and the disk perhaps becomes thin, and we start seeing it in a way that we're used to. But the state that I'm going to be concentrating on in this talk is the slow luminosity state. This is where 2 of the largest black holes on the sky are located. One of them is the M87 black hole, and the other one is the Sagittarius A star black hole. This one is the black hole in our backyard. It's a few million solar mass black hole at the center of our galaxy. And M87 is about a factor of 1,000 more massive and 1,000 more distant. Therefore, these 2 guys appear to have almost the same apparent size on the sky, and they are the primary targets of the Event Horizon Telescope that Shep and others are actively working on. So as I mentioned, we expect to see images of these guys in just a few years. And so we should be ready on the theoretical side to interpret this exciting data set. But it turns out that interpreting this accretion state is really challenging. And the reason for this is because at these low luminosities, the innermost parts of the accretion flow become so dilute that the collisions, Coulomb collisions between electrons and the ions, they become so rare that there is almost no exchange of energy between the 2 species. So what happens in the end is that the plasma develops the plasma becomes a 2-temperature plasma, with the temperature of electrons and temperatures of protons being completely decoupled. The difficulty, this brings a difficulty because the simulations telling us what the temperature of the protons is, they don't tell us what the temperature of electrons is. And yet it is the electrons that emit. And this is what we see. So we need to know what the electron temperature is in order to make any sense of the observations. So what usually people do in this case is they paint the electron temperature on top of the observations. We literally in the field use the term paint. It's really accurate. We set, let's say in the simplest case, the ratio of electron to proton temperature to be constant that is less than unity. That's because we expect that in these low luminosity accretion flows, most of the heating goes into protons, and then electrons don't get almost any heat. So that's why this is a pretty good approximation. And so when you do this, and you try to fit the spectrum of the Sagittarius A star black hole, and this is the submillimeter bump, so this is the radio frequencies. These are lower frequencies, it's 10 to the 10 hertz. This is 10 to the 13 hertz, so this is about 1 millimeter. These are the frequencies where the EHT will be observing. So if you go to lower frequencies, then you see that the simulations and the theoretical spectra, they vastly underpredict the emission. So there is some physics that this very simplified prescription is missing. Recently, it became apparent that if you paint the polar regions above and below the disk with really hot electrons of about 10 to 11 Kelvin, then you actually can reproduce the so-called flat radio spectrum really well. It's flat because if you plot f nu, it's almost independent of frequency. Here it's nu f nu, so it's proportional to roughly nu. So this shows that actually it would be really nice to try and reproduce this kind of spectrum from first principles. Instead of having this freedom that you can paint the simulation the way you like to get what you want, what we decided to do is a different approach. We decided to put in the best physics that we understand of how electrons are heated in these low luminosity flows and see what comes out on the other end. If we can get a good agreement with observations, we can claim victory and we can actually make some predictions and take things forward. If we, however, do not get agreement with observations, it means that we miss some physics. We will go back, figure out what physics is missing, and this way we can actually gain an understanding of what physical processes are controlling the electron heating in these systems and therefore their observational appearance. This work has been pushed forward by a really bright graduate student at UC Berkeley who is working with me and Elliot Quatert, Sean Ressler. So what we've done is we have actually added electrons as a second fluid in addition to the ions in the simulation. We give electrons a fraction that we call Fe, or Ramesh told me I should call it delta, Fe of the total heat that the fluid receives due to turbulent heating. This fraction is very well understood from the modeling of the solar wind heating. And what's important there, it's not the details, but only one aspect for this work, is that electrons tend to receive more heat, the larger fraction of the heat of the total fluid, in regions where the magnetic fields are stronger. You will see in a second why this is important. There are a few other technical details. We include thermal conduction along the magnetic field lines. It's very important because the plasma is collisionless, so electrons can zip along the magnetic field lines and equilibrate the temperatures. This affects the spectrum. And since electrons are subdominant in their energy, we neglect the back reaction of electrons on the flow. We will later relax this in the future works. This simulation is done with brand new code, which we call Charmer. It's a three-dimensional general relativistic MHD code, really fast. And we're going to make it public in a few months, so if you're interested, stay tuned. So how does it work? Well, this is a vertical slice through the innermost accretion flow. It's about 20 times 20 gravitational radii on the side. And what you see in here is the black hole that's rotating at a speed of about 0.9. The disk is also rotating. It's coming out of the board here, coming into the board there. It's a 3D simulation. And what you are seeing in color is the electron temperature in the units of electron rest mass energy, MEC squared. So here it's bluish, so electrons are mildly relativistic. They will become relativistic as the simulation goes on. So we approximate the equation of state of electrons with relativistic fluid, polytropic index of 4/3. The protons are cold, non-relativistic, and so the polytropic index of that fluid is 5/3. And the solid lines show the magnetic field lines. So let us run the simulation and see what happens. So you see that turbulence generated by the magnetic rotational instability brings the magnetic flux and gas into the black hole, and we see two polar regions forming. And just around these polar regions, where the magnetization is strongest, where the magnetic field is strongest, we see really bright sheaths of hot electrons, just where they were inferred in previous work in order to explain the observations. But here it comes out self-consistently. So let us see what kind of observational signature will this distribution of electrons that we computed here leads. And to our great surprise, it actually fits observations really well. It reproduces the flat radio spectrum naturally without essentially any free parameters. The only free parameter in this model is the mass accretion rate, which tells you which shifts the spectrum up or down. In fact, there is zero free parameters in terms of the reproducing the slope here because the slope is independent of the normalization. So encouraged by this, we can now go ahead and compute the images of this flow on the event horizon scales. And what's interesting here is that most of this emission is coming from the sheath around the jet as opposed to the disk itself. So we might not actually be seeing the disk. So we're trying to understand what we're looking for here. What are the signatures of the disk? What are the signatures of the jet? How can we disentangle the various components in the flow? So let me now move out to larger scales and try and gain understanding on what happens at the very center. So this is the beautiful image in X-rays that we saw at the first talk yesterday from Anne. from Anna. The colors show the X-ray emission as seen by Chandra. The contours are showing the radio emission. And the black hole is sitting somewhere down there. It's a really small dot, which we cannot see on this scale. If we zoom in, however, using the HST image, the optical image, we will see a series of bright features. So the brightest of these are the core, which is roughly where the black hole is. The next one is the well-known feature HST1. And then there are a few other knots, D, E, F, and so on, that I will not focus on in my talk. What was getting me interested about these features is that the distance to HST1 is consistent with the radius of the black hole sphere of influence, so the Bondi radius. So I was thinking, and as many people before were considering this possibility, that perhaps HST1 in some sort of recollimation shock, when our two jets are coming out from the black hole, where they are collimated by the accretion disk outflow, and then once they get out of the Bondi radius, they realize that there is ambient density there, and so in order to readjust, they go through a series of jet recollimations, and so the standard lore here is that these recollimations heat up the jets because they lead to shocks, and this is what we're seeing here. So we decided to see how it works in the case when the jets are self-consistently produced magnetically. Will we see any emission? Because if magnetic jet, you try to shock it, you won't really expect shocks to produce much emission. By the way, just to convince you that indeed we're expecting to see something like this, a collimated jet and then a change of its shape, there have been observations of the shape of the jet that look like a parabolic jet out to roughly the Bondi radius, and then the jet becomes conical. So something like this is probably happening, so it's worth simulating this. And this is the result of such a simulation where we put a central compact object, spun it up, and then it produced magnetized jets. So what you're seeing here is the black hole is somewhere at the center at a very small radius. The large jets are bent sideways. It's the so-called external kink instability. But what's interesting is if you zoom into the very central region, where the jets start to interact with the ambient medium, you can see that the jet becomes visibly kinked inside of the jet. It's called the internal kink. And if you look at the colors, they show the magnetization of the jet. Yellow is high magnetization, greenish is low magnetization, and bluish is even lower magnetization. So once the jet starts to go wild and kinks onto itself internally, we see that the jets are getting more and more heated. You can see this visually, how this bundle of magnetic field lines is kinking onto itself. And slowly the field lines becoming less and less one, which means that this toroidal magnetic field component is getting dissipated and presumably radiated. So perhaps what we're seeing here is the mechanism behind the emission of this HST1 feature. So I would like to summarize here that what I've talked to you about is our effort in including faithfully the physics of electron heating in the simulations of low luminosity accretion, which will hopefully prepare us for the interpretation of the beautiful data set that is about to come in the next few years from the Event Horizon collaboration. And we're trying to understand jets on all scales, in particular how jets emit. This perhaps is giving us, these simulations of jets interacting with ambient medium is perhaps giving us hints that when we see not emission from the jets, or we see gamma ray burst emission, this could be an indication of magnetic instabilities in the jets where the magnetic energy is converted into heat and then into radiation. And I didn't have a chance to talk about the last point, so please ignore that. Thank you very much.
Say physically what's happening to keep those electrons so hot that somehow the protons are able to dump enough energy into those electrons along the sheet of the jet you showed in your simulation. You said magnetic fields. How does it happen actually? And and then that's one question. And the second is, have you applied this to some classical ADAF spectrum also in addition to jets?
So this is basically an ADAF. What we have is a non-radiative disk, which naturally develops high magnetization regions above and below the disk. It has a jet. We tried the ones which didn't have jets. We got almost identical results. And we're, in fact, exploring the sensitivity of the spectrum to the strength of the jets. Because what we're suggesting here is perhaps that Sagittarius A star is not a jetless source, as you might think, because of the absence of an obvious jet. Perhaps it has a weak jet, because it's a really messy system. So maybe one is hiding there, and this flat radio spectrum is telling us that it's the jet. So I would say a standard ADAF would have this feature to some degree, and we're exploring how strong this feature of flat radio spectrum is in those non-radiative flows. Now, another question you asked, what makes electrons hot? Right. Well, this is complicated collisionless physics that has to do with the cascade of collisionless Kelvin waves down to small scales. And so it turns out that if you have either hot electrons already, or if you have strong magnetic fields, then this cascading Kelvin waves tend to heat electrons preferentially. I wouldn't go into details right now, but that's what comes out from the observations of the solar wind and then the modeling of that process. So we think that we understand this process pretty well, but what really is important in order to reproduce this spectrum is the sensitivity to the magnetization of the flow. If high magnetization means hot electrons, as we expect, then that's all that's needed in order to reproduce the spectrum.
So the hot electrons on the sheath of the jet are producing radio emission, but presumably the total radio emission that you have is just whatever you have in your domain. But won't the electrons continue to cool for a very long time as the jet propagates a long distance away from the black hole?
That's exactly right. So those electrons contribute to the emission at low frequencies. Okay. So it's kind of an inverted disk. So you have the highest frequency. The highest frequency is produced by the base of the jet, and then as you move out further and further out, the photosphere. So at lower frequencies, the photosphere is further out. So you're seeing further and further out away from the black hole. So this is closest to the black hole, further and further out, and then in fact our domain ends somewhere here, so we don't show it. But if we were to run it with the larger domain and for a longer time, we would presumably reproduce the entire spectrum. Good question.
Yeah, the ratio between the electron and proton temperatures effectively is a free parameter in your theory, but you just said that you have this information on how this actually is constrained. So how well constrained is that ratio?
Oh, the ratio is not a free parameter. It comes out in our simulations. Usually people set it to be a free parameter. But in this case, what we do is the only freedom that we have is we set initial electron temperature to be 0.1 MEC squared of electron. And then actually, since the electrons get a lot of heat as they go in, it is not really relevant. So in a sense, I mean, not in a sense, but in our modeling, we get in first principles, or as first principle as we can, given that we have the subgrid model that we implemented. So within that subgrid model of electron heating, we make a unique prediction. Yeah, there is no free parameter there.
So what is this ratio that comes out then?
So the ratio in the middle of the disk, the electrons are about 5% of the protons in temperature. And then as you move in towards the edge of the jet, you get an electron temperature of about 20 MEC squared, something like this, 2030.
Okay.
Does it answer your question?
I think it's time to go to coffee break. Are there any more questions? You can grab Alexander at coffee break. Let's thank him again. And thanks to all the speakers in a really interesting session today.
offside or like. Right laser. And is it like you can click to change it? Yeah, yeah. So forward, backwards. Oh, cool. You can adjust it.
Okay, so folks, we're ready to start the last session of the day and the symposium. I'll be sharing this session on Pat's lane, or at least that's what my name said before I lost it. I'm a member of the CXC staff. I had the team of mission planners who schedule your observations for those of you who propose to Chandra. And often when I tell people that, they're just nice to me all the time. In addition, for research, I work on supernova remnants, particularly, at least in recent times, cosmic ray acceleration by non-relativistic shocks, and on pulsar ring nebulae. So I will be chairing a session of talks, several of which I don't very little about. And so we'll start here with Blakesley Burkhart, who is here at CFA and got her PhD, like your session chair, at the University of Wisconsin-Madison. And she's going to tell us about the origins and implications of turbulence in galaxies.
All right, thanks, Pat.
Yep.
I'd like to also thank Paul and Carol for putting together this great symposium every year. It's always a lot of fun to see all the fellows year after year. So that's fantastic. This is my second year. And this year I'll be talking a little bit about some preliminary work that I've been doing with the illustrious simulation in comparison with observations. So I think this is a great forum to present something slightly preliminary, and I'd be happy to have your ideas and feedback on that. So I'm particularly interested in turbulence, and the title of my talk is The Origins and Implications of Turbulence. And so the implications I'll start with. That's actually sort of the easy thing, because throughout this 2 days, a lot of you have been talking about turbulence, whether it's in the context of simulations or observations in a variety of astrophysical settings. So these are just a few of the many implications of MHD turbulence, particularly in galaxy-type settings. We already heard a lot about turbulence in clusters earlier today, so I haven't included clustered turbulence on here. But you can see there's many, many, many astrophysical examples of where one needs to consider the effects of magnetic fields in turbulence. They just simply cannot be ignored. So things like magnetic reconnection, so the reconnection of field lines, cosmic ray propagation, pressure support in the ISM, the process of star formation, feedback, ISM structures, all of these things, these areas of study in astrophysics and galaxies, you just simply cannot ignore the effects of turbulence in magnetic fields. And so for my talk, I'd like to kind of back up and discuss what do we actually mean when we talk about turbulence, like what is turbulence as a physical process? And then where does this turbulence come from in galaxies? What drives turbulence? What's the origin of turbulence? And so I'd like to discuss that particular problem on the largest scale, so kiloparsec scales of galaxies, and I'll give it from a perspective of simulations, in particular the illustrious simulation, which is a cosmological simulation, and then also observation. So the question of how do we measure turbulence in observations. I'll address that as well. So what is turbulence? This is actually a $1 million question. I was at a conference a few months ago on turbulence, a room full of experts on turbulence from the perspective of laboratory all the way to astrophysical experts. And the very last question of the conference, after a week-long discussion about turbulence, was what is turbulence? And then these experts argued for like an hour about their definition of turbulence. So it's actually a non-trivial thing. My definition, which I think is a good one, is that turbulence is an energy transfer process. So you inject energy on some scale, and energy cascades along the turbulent cascade from large scales to small scales generally. You can have an inverse cascade, but the general cascade is energy that transfers from large to small scales. There's three main scales of interest in the turbulent cascade. The first one being the injection scale. So this is what I would call the origin of turbulence. Where is energy injected? Where does the energy come from? That energy cascades through a series of eddies down what's known as the inertial range. The inertial range is a particularly important range of scales because this is where we have theoretical predictions for how the scaling should behave. And as it was mentioned many times yesterday in astrophysics, everything's a power law. So we have some power law type scaling in the inertial range. The actual power law is still a subject of a lot of research. Probably most of you are familiar with the very famous 1941 Kolmogorov scaling in the inertial range. This is where this minus 5/3 power law of turbulence is derived from simple arguments that the energy transfer per unit time is constant throughout the cascade. And from very simple dimensional analysis type arguments, from there you're able to derive this minus 5/3 scaling law. Now, the Kolmogorov scaling is an incompressible scaling and unmagnetized. So we know in the ISM we have shocks, so we have a compressible medium, we have magnetic fields. So things get a little more complicated, and that's why this sort of minus 5/3 scaling isn't necessarily what we expect in astrophysical environments. Furthermore, when you introduce a magnetic field, eddies are no longer isotropic, they become anisotropic, and there's a scale-dependent anisotropy, which was first predicted by a very famous paper by Goldrick and Sridhar in 1995, and then subsequently tested by numerical simulations. So the point is, turbulence in itself is extremely complicated, so we want to somehow study it astrophysically, and then we need diagnostic tools to do that. The power spectrum is generally the most common diagnostic tool for studies of turbulence, but I've been working very interestedly on many other diagnostic tools for astrophysical turbulence that enabled us to not just measure the energy injection rate, which I've called E of k here, but also other parameters of interest in astrophysical turbulence, such as the Alfvén Mach number, which depends on the magnetic field strength, and the sonic Mach number, which gives you an idea of how strong the turbulence is and how compressible the media is. And there's a mess of references. If you're at all interested in turbulence, I'd be really happy to talk to you about diagnosing turbulence in your simulations or observations afterwards. But for this talk, I really want to focus on the origin of turbulence. And so, again, it's really probing these largest scales in the turbulence cascade. Where does turbulence come from? What are the origins of turbulence? And also what's happening in this inertial range. And towards the inertial range from observations, we actually have a lot of measurements in the ISM. So clouds that are nearby, and I've listed in this table here a number of observations tracing different phases in the ISM. So H1, the 21 centimeter line, which primarily traces the warm and cold neutral medium, CO observations, and C18O, which of course are tracing molecular clouds, the sites of star formation. And a variety of different authors have tried to measure the velocity power spectrum of turbulence, which is non-trivial to do because, of course, you have line of sight information only, and the density power spectrum from column density maps. And in the cases where these different authors and different studies were successful, one sees that you get slightly steeper velocity power spectrums relative to the Kolmogorov scaling of minus 5/3, and slightly shallower slopes relative to Kolmogorov for the density spectrum. This is actually exactly what we see in MHD simulations of turbulence with high sonic Mach number, so highly compressible turbulence. The velocity spectrum slightly steepens from the Kolmogorov scaling, and the density spectrum slightly is shallower. And so this, I think, is very nice evidence that we actually have a supersonic ISM from the observations. So what about the driving scale? Where does this supersonic turbulence come from? Again, this is observational evidence. So I'm going to show you a couple different pieces of observational evidence that suggest we have driving that's at least larger than parsec scale. So usually when you give a talk on turbulence, you always have to show this so-called big electron density fluctuation power law. First shown in Armstrong, Rickett, and Spangler in 1995. It was later modified to include H alpha data. But the point is that you see this beautiful power law that has a roughly minus 5/3 slope from parsec scales down to AU scales. And so this was one of the more early pieces of evidence that turbulence is in the ISM, and it's driven on scales that are at least larger than parsec scales because we don't really see any sort of turnover here. There's other pieces of evidence for large-scale turbulent driving. So a more recent study by Chapurnev et al. Looking at high-latitude H1 clouds, again showed from the velocity power spectrum an injection scale that's at least greater than or equal to 140 parsecs in these clouds. And then finally, very famous Larson relationships for the size of clouds as compared to their line width. So you again see this very nice power law that's interpreted as being due to a turbulent cascade. And you see this power law not really turning over, or giving any indication of turnover, at least out to about 100 parsecs or so. So this is all observational evidence that we have some kind of large-scale turbulent driving. Now I should point out that we don't expect in the ISM to just have one driving scale. We actually can expect many driving scales, and it's really more about a competition between where the most energy is injected as a function of scale. And so I've listed a number of very likely possibilities for driving scales. So at kiloparsec scales, you can have galaxy-wide processes like mergers, gravitational instability. I'll discuss some results in this talk about that. At hundreds of parsec scales, of course, supernova can be driving turbulence. It's a very likely driver of turbulence in the ISM. You can also have things like MRI and cloud collisions, expanding shells. And then even into the cloud scales, especially where you have active star formation, you can have winds and feedback from those stars. So that's sort of driving a turbulent cascade around tens of parsecs. So it's not really the question of so much what is driving turbulence, but more what is the dominant driver. And of course, if you go through the literature, one of the most common drivers of turbulence that's discussed is supernova. And that's because if you compare sort of a fiducial value for the turbulent energy dissipation rate, supernova are generally matching this kind of order of magnitude estimate for the turbulent dissipation rate. And so supernova can certainly provide this kind of driving. If you look at global observations of galaxies, so this is now H-alpha measurements of a variety of different galaxies from several of different studies. Resolution in all these cases is roughly kiloparsec scales. So you can correlate the H-alpha luminosity in galaxies with the star formation rate, and then compare that to the velocity dispersion in the H-alpha observations. And you see, lo and behold, you get this extremely nice correlation between star formation, or H-alpha luminosity in galaxies, and the local velocity dispersion on kiloparsec scales. So many of these studies interpreted this type of correlation as the usual supernova paradigm for driving turbulence. You have more star formation, you get more turbulence, this will increase the velocity dispersion, and you have this very nice picture. So we can ask the question, does this kind of feedback actually drive the dispersions or not? And we can ask this question from the perspective of simulations. In particular, at kiloparsec scales, cosmological simulations such as the Illustris simulation actually resolve down to these sort of scales. And so we can compare the galaxies as shown in Illustris to these type of observations. Illustris is particularly nice to use because, of course, we can change the feedback prescription for the star formation and how the star formation injects momentum into the ISM. So we can change this parameter and see, indeed, how does the star formation rate relate to the gas physics. So this is the same plot again with the observational data here, the star formation rate and the velocity dispersion here. And the Illustris spiral galaxies, so these are 48 perfectly beautiful spiral galaxies in the Illustris simulation shown as these blue diamonds. And they follow extremely well the same relationship that's tracked by the observations. I've also put on here elliptical galaxies. They're very devoid of gas. They sort of depart from this relationship, and then lower mass galaxies down here. So it seems that the Illustris galaxies track very nicely the observational galaxies in H-alpha. Now again, we can play the game of turning off the feedback. These are just with a normal sort of feedback run, but I can say, well, what happens if I turn off feedback entirely? And lo and behold, when I change the feedback model in the simulations, in particular, even with no feedback, you still see this very nice correlation between the star formation rate and the gas dispersion in the galaxies. And so it seems that you can get this correlation without any feedback at all. And so what could be driving these extremely high velocity dispersions in the galaxies? Well, there's other explanations. In particular, gravitational instability. So if you consider just a Toomre type analysis, you can relate the gas dispersion to the gas surface density, which of course from a Kennecott-Schmidt type relationship is related to the star formation rate. And then you can get very nice correlation between the star formation rate naturally and the sigma of the gas just simply by considering a gravitational stability type analysis. So gravitational instabilities can also drive turbulence, especially at these large scales. What about other processes, like mergers, for example? Mergers could also particularly drive turbulence. So this is a movie from the Illustrious collaboration. You can find this beautiful movie on the web. The left panel shows the stellar light. The right panel shows the gas density. And you see when you have a merger event, all the gas is spewed out of these halos, an extremely violent and turbulent-looking event. I can track one of the galaxies in Illustrious as a function of redshift. So the star formation rate is shown here. The gas dispersion is shown here. The total mass is in green. You see in the total mass a blip here when a merging event occurs for this particular galaxy. This is its snapshot at redshift of 0. And you get corresponding jumps in the velocity dispersion for this particular galaxy. So this suggests also mergers can play a significant role in increasing the local velocity dispersion. Observationally, we also have evidence. In particular, if I apply the VCS, which is a technique that's used to get the velocity power spectrum of turbulence. We've done this recently in the SMC. I briefly talked about this last year during my symposium talk. We applied the velocity coordinate spectrum to the SMC in order to get the velocity power spectrum and hopefully the driving scale information from this galaxy. Long story short, we found in the SMC, in the H1 data, a driving scale of about 2.3 kiloparsecs. So this is a very large-scale driving, larger than any particular clouds that we've studied with this technique so far in the Milky Way galaxy. And then we have to speculate what could be driving such a large velocity dispersion, a large turbulent injection rate in the SMC. Of course, two likely candidates, probably the most likely, I think, is the merger between the SMC and the LMC. So this suggests that mergers can indeed drive turbulence, especially in smaller dwarf galaxies like the SMC, which are lower mass. Models by Besla et al. From 2012 suggest that the SMC and LMC have already merged. Of course, there's also the possibility of supershells, so remnants of supernova that could be injecting momentum as well. So I'll conclude, and particularly I'd like to again stress if you're interested in diagnosing turbulence, either from a simulation perspective or observational perspective, then I'd be very happy to discuss possibilities for measuring turbulence in simulations. Thank you.
If the large-scale driving by mergers and the gas accretion is depositing stuff at sort of the outside of a disk galaxy, is there an angular momentum barrier preventing the turbulence from propagating all the way to the inner parts of the galaxy?
I think the propagation will be more set by the dissipation rate of the turbulence. It could be, I'm not sure how it would necessarily be related to the angular momentum of the galaxy. The SMC LMC system is sort of special because you still observe regular motions, and so that might be a nice, I don't know how to go back here. That might be a very nice question to address with simulations. I know her initial conditions, she starts off with regular rotation and then the galaxies collide, and so one could kind of separate out regular motions from more like turbulent velocity dispersive type motions after the simulations have run. It's really difficult to actually get that from the observations, though.
Your mention of the supershells just put me in mind of the Fermi bubbles in our own galaxy. Are those on the right size scale? I think they're in the kiloparsec range. And can you actually cross-correlate the turbulence one sees with that structure to see if there's any tracing there?
Yeah, I think that's a very good point. I mean, our galaxy has only been studied in on a cloud-to-cloud basis. It's very difficult because, of course, we're inside of it. But it would be really nice to compare the velocity dispersions of different tracers around the Fermi bubbles. And, yeah, that would be very interesting. It hasn't been done yet, as far as I know.
Other questions? Okay, well, let's thank folks for the attendance. Next, we have Philippe Mosta, who's from Berkeley, and he's going to tell us about MHD-driven supernovae in 3 dimensions.
I will let you know after 10 minutes that you have 5 minutes left to get to your 5 minutes of questions.
Which one is the laser pointer?
One
Oh,
right
the
above
right one.
the,
Okay, yes, I'm Philip Muster. I'm a first-year fellow at UC Berkeley, and I'd like to take the opportunity today to talk to you a little bit about work that I've done in the past couple of years while at Caltech on modeling MHD-driven or engine-driven core collapse supernova with 3D simulations. And just to recap a little bit, Kazumi in the previous session has already given us a quick introduction of what kind of different evolutionary paths massive stars at the end of their lifetime can take, and he had focused a bit on black hole formation. I'm going to just recap that the core collapse supernova are the explosion of massive stars at the end of their lifetime. I'm just showing 87A here. And just to recap the details of the physical situation that we're encountering here. So we have the collapse of an iron core to a protoneutron star. This sends out an initial shock wave, and that shock wave initially was, when this mechanism was first proposed, was thought to actually be successful in exploding the star and launching the supernova, but this doesn't really quite work out. So this shock wave, that's what you see here on the bottom, actually stalls very rapidly at a radius of about a few hundred or 100 kilometers. And then you have the situation where you have a standing accretion shock surrounding the protoneutron star in the center, which cools and releasing neutrinos in this cooling. And that is the scenario that we face, where we need to find a mechanism to revive this shock wave that is stalled there to launch an explosion. And then in the next talk, Luke is actually going to focus on the mechanism that is believed to drive the majority of supernova explosions, in where you revive this by the extra deposition of heat by neutrinos behind the shock wave. But I'm actually going to be focusing on a specific subclass of supernova, hyperenergetic or superluminous supernova, where you need rapid rotation and probably magnetic fields to launch an explosion. These explosions are on the order of a factor of 10, maybe sometimes a factor of 100 more energetic than typical supernova. They often have Doppler broadened lines, so what I'm focusing on here is basically these type 1c broadline explosions where you have relativistic outflows, and some of these explosions are also connected to long gamma ray bursts, making this kind of an interesting scenario to study this connection and how this connection actually happens. So basically what I'm interested in, and this goes back to what Kazumi had been shown, have core collapse, and then we need to find some kind of mechanism or engine, and you have either this outcome in normal supernova, or you have this extreme kind of sub-branch where you either have a hyperenergetic or superluminous supernova, an unnova, black hole formation. And what I'm really interested in is the hyperenergetic supernova or superluminous supernova and how they're connected to long gamma ray bursts. And this connection is basically that we have at the moment about 11 cases where this is actually confirmed, and all of these confirmed GRB supernova of type 1c broadline, so we have no hydrogen or helium in these observed spectra. Relativistic velocities indicate outflows that are probably at relativistic speeds, and all of these are hyperenergetic supernova. But to make this more complicated, not all type 1c broadline supernova come with long gamma ray bursts. And then there's also type 1cs, type 1bs, so we need to figure out how this actually works and how this actually makes this connection to the long gamma ray burst. So what I'm interested in is what is the mechanism or the engine driving these extreme explosions, and what determines in which cases we get an additional long gamma ray burst or an X-ray flash, and how does all of this depend on progenitor parameters and the details of the engine operating. And then if you want to do this, you can only do this with actually doing consistent simulations where you put in all the physics and model all the details. And the mechanism that is typically proposed for these kind of explosions is the magnetorotational mechanism, where you have rapid rotation on the progenitor star, leading to a millisecond protoneutron star that has a strong differential rotation profile. And then with the addition of magnetic fields, you actually have a way of tapping into this reservoir of rotational energy and extract this and power it into the explosion. This has been studied pretty extensively with 2D simulations, and we get beautiful energetic bipolar explosions out that are symmetrically launching jets along the rotation axis of the star. But But the caveats are that you need very high core spin, and probably this is realized only in a few of the progenitor stars. We don't quite know since we don't have good constraints on this from observations. From stellar evolution, it's also very simplified, so especially rotation is something that's hard to figure out in stellar evolution codes right now. Also, we need to figure out how we get the actually super strong magnetic fields on the order of like 10 to the 15 Gauss or stronger after core bounds realized in our progenitor model, since that's what we need to extract this. Computationally, this is actually a pretty complicated thing to model. You need magnetohydrodynamics for the fluid. You need GR for handling the collapse of the iron core to the protoneutron star. But you also need nuclear neutrino physics to deal with the matter at neutron star densities. And on top of that, you need basically a full Boltzmann theory for transport of the neutrinos. So we need to make some kind of approximations when we put this on the computer. On top of that, we actually have to do this in 3D, since we have to deal with specific fluids and MHD instabilities that only happen in 3D, and we can't really employ symmetries. And then just to give you an idea of the scales here, so we typically need to resolve turbulence on scales of like 10 meters roughly, but then the relevant interior of the star that we need to model is like 10 to the 7 meters. The simulation time step is constrained to 10 to the minus 6 seconds, but we really need to cover 10 seconds of the cooling time of this protoneutron star to figure out what's happening to our supernova. So this is a very complex problem that needs to be dealt with simulations. What I'm showing here is a simulation where on the left you see a 2D simulation, on the right you see the same simulation in 3D. We had this initial shockwave being launched. We're looking at entropy here. The shockwave stalls, and then in 2D you get one of these beautiful jet explosions out. So I'm showing entropy here, and basically material in red is high entropy, so higher, hotter material. Blue is colder one, and then basically in 2D you have a beautiful jet explosion. This is a model that has been run by a Japanese group before, and we reproduce those results. In our full 3D simulation, which was one of the first consistent full 3D simulations, you can see that this didn't quite work out in a pretty extreme way. And so we went in and figured out that there must be something wrong in our code. I mean, this looks pretty drastically different. And what we actually found is that you have instability developing where if you look at the barycenter of the jet, so you do basically cuts in the XY planes through the jet emission at different heights, then you see that the barycenter of the jet actually gets displaced from the rotation axis in the full 3D simulation. And this is happening, and this is basically the tracks of this barycenter in the XY plane. It's happening in a spiraling pattern away from the rotation axis. And this is typical of a m equals 1 spiral instability. And when we looked at this, we pretty quickly figured out this looks like a kink instability, which Sasha had just mentioned in his talk in the last session, which is a common instability that jets actually experience. And looking at a toy model, theoretically, this seemed to work out pretty well in terms of like what we would predict from the rough conditions that we observe in our simulations to the instability of this outflow. So the kink instability is nothing terribly new. This is actually something that commonly happens, for example, also in very different fields, like in fusion reactors. Tokamak reactors typically experience this quite violently, and this is one of the problems there. One of the key things for the kink instability to happen is that you have a much stronger toroidal over colloidal field strengths. And so basically one thing we did to check that we're actually not seeing something that's numerically triggered here is bump up the colloidal field strengths artificially to get out what we see here on the left, where basically you still have a kinked kind of outflow, but it's not any more completely disrupted as in the simulation that I had showed you before. This is not, I don't consider this necessarily a more realistic model. It was just more a sanity check that we did. So now looking at the 3D simulation in the 3D volume rendering, so we're again looking at volume, at entropy here. We had this initial shockwave stall, and then basically material is sloshing around a little bit, and you see basically material rotating in and out of the screen. But not much is happening for like about 50 to 100 milliseconds after core bounds, where the 2D model had already launched this jet explosion. So we were kind of a bit disappointed, but we kept it running. Luckily we did, since later on you do actually see that there's outflows along the rotation axis of that core, but they don't really look like clean jets. They're more like basically bubbles pushing out along the rotation axis and have a much more complicated structure than what you see in 2D. And this is basically what, in the end, then leads to this kind of bipolar bubble structure that we're seeing here in this simulation. And then basically looking at what is actually driving those outflows, we want to look at the plasma beta parameter, and this is what I'm going to show in the next movie. So here, the color map has chosen that anything in blue and red is actually dominated by the fluid or by the gas. Anything in yellow is magnetically dominated material. And initially, you don't see much since there's not much happening in terms of magnetic field driving any of the dynamics. But if you wait a little bit in this, you're going to see that there's like material being expelled from the protoneutron star that's sitting in the center where this is basically black here. And that this is actually what is driving the outflow. So this is happening now where you basically see this kind of narrow funnels of yellow material pushing out, and then actually all the material behind these kind of expanding bubbles is actually mostly yellow, so dominated by magnetic field. So the analogy that I often use here is that it's basically like a loose garden hose expelling water, where it kind of like it's not really confined to the rotation axis here in this 3D case, and this is kind of pushing the shock outwards, but not in a relativistic jet-like fashion, but rather these kind of complicated geometry. And then, so this was at the end of where we stopped these simulations at about 180 milliseconds after core bounds. Since then, we actually have continued the simulation, since one of the issues was that this didn't quite look like an explosion. So it was expanding, but not like in a runaway fashion, so we could conclude that this is actually a successful explosion. Since then, basically, if you look at the shock radius versus time, we actually, if we run this longer, we do get runaway behavior, where basically this is accelerating, and then as it is facing lower and lower density material accreting as the outer layers of the star accrete onto the core, this is most likely going to turn into a successful explosion. And then looking at the geometry of this now, at the end of where we have the simulation right now, it's still in this geometry where you have these basically two bipolar bubbles pushing out material. One thing that I want to highlight here is that if you pay attention, there's a bit of a kind of transition going on here and here. So we actually have this tilted accretion torus still present. And this is one of the things that is actually crucially different with respect to 2D simulations, that even though we have a successful explosion driving along the rotation axis of the star, we have still accretion going on. And this comes back to what Kazumi had been pointing out. So in 2D simulations, what had been shown in these kind of scenarios, that accretion was completely shut off so that you would have a neutron star ultimately being left behind by the supernova. Here we actually have the scenario where we could be driving an explosion and still have black hole formation later on, which is very, very interesting for the possible connection to long gamma ray bursts, since here it's really unclear which kind of engine we have driving this gamma ray burst. So you could have the scenario where you have the neutron star or the magnetar, the highly magnetized neutron star, drive this supernova explosion, making your type 1c broadline explosion. But then it could be either this neutron star or a black hole that is later formed, driving your long gamma ray bursts later on. And this is something that is interesting, where here now basically with 3D simulations, it looks like there's many more opportunities of which kind of different scenarios can be realized. And that's something we have to figure out in the future by doing longer simulations, if we indeed have black hole formation later on. And then also how this depends on different progenitor parameters, where this could be a very specific scenario that's happening for the rotation and magnetization profile that we've chosen. And that's something that I'm planning to do while having my fellowship in the next couple of years. And with that, let me summarize. So I hope I've convinced you that MHD-driven supernova really have to be modeled in 3D if we want to do this right. On top of that, it really looks pretty cool as well. The developing jet becomes kink unstable, and basically we have this dual lobe structure that determines what the geometry of the explosion ultimately will be. One of the key things that I highlighted is that we still have continued accretion even though we have an explosion taking off in our simulations. And this is very, very interesting for the possible connection to long gamma ray bursts, where it allows both for the magnetar and the collapsar model. And this is something we have to figure out with our continued simulations. And basically all of this will also have implications for the R process in these jet-driven outflows, which is one of the mechanisms where supernova may still contribute to the R process abundances that we observe in our universe. And with that, let me thank you for your attention.
So you still have accretion at rate time in this model.
Yeah.
So how long would you have to accrete to make a black hole in the center?
So we've done this simulation in kind of a simplified 1.5D code without magnetic fields, and that takes about 2 to 3 seconds for black hole formation. So this would be slightly different in a 3D simulation, but we're still far, far away from black hole formation.
Other questions?
Yeah, so binary first, and there's one model that says that these long GRBs comes, the rotation comes from replenishing from binary mass transfer, something like that.
Right.
And so I'm just wondering, how sensitive are these conclusions to the initial conditions of your initial rotation?
Well, so I mean, they're pretty sensitive since you need rapid rotation to have any of this happening. So you really need an order of millisecond magnetar spinning in the center of this to even have like any successive launching explosion. If that threshold is at like 4 or 5 milliseconds, it's a different question for the spin period. But if you don't have that to begin with, you won't see any of that, since you just don't have the right kind of energy in rotation to even be able to drive the supernova, let alone the GRB. For the GRB, it's kind of a question. I guess if you want the magnetar driving the GRB, then you definitely need rapid rotation as well. If you rely on black hole formation, it's a different question, since I guess there you can get up to energies much easier with like slower rotating black holes as well. For that, it's a hard question to answer, but generally that's all pretty sensitive to those initial conditions.
So would you say that there are requirements on the ratio of the foil to toroidal magnetic field to give an explosion?
Well, in the sense of that this affects how the outflow propagates. So it's really more like, do you get something like what I show here out, which really looks like a jet explosion. It's actually expanding pretty quickly, pretty rapidly at like 10-20% of the speed of light. You still see a kink instability, but it's not completely disrupted as in this 3D model that I've shown you that has a lower colloidal seed field. So in principle, yes, by affecting the outflow. How much that will matter if you look at it on the scale of the star later on is a question that has to be answered with like full star simulations, just because this is happening in the very interior of the collapsed iron core. So you could very well see that this kind of configuration that I'm showing here, kind of from looking at it from like the kind of length scale of like propagation into the full star until shock breakout, may very much look like a jet in the end. So yes and no, I guess, would be my answer.
There's two things that I was wondering about. One, maybe from what you said here, you can't answer, but you started saying that you're looking at cases that are very energetic explosions. I guess maybe since you don't know absolutely that explosion, it looks like it's taking off. But I'm curious as to what the hope is that this will produce 10 to the 52 ergs in kinetic energy.
Yeah, so it's hard to measure the kind of explosion energy reliably in this kind of state where it's really just transitioning into explosion. So that's a typical problem with supernova simulations of these kind of consistently driven explosions. Generally, it's more in the way that the neutrinos cannot explain those explosion energies. If you look at the energy in rotational energies in these systems, you have 10 to the 52 ergs in there. So basically, if you can extract all of this, then you can get up to that energy. But if this actually happens, it's something that we have to figure out by basically running this simulation longer and then determining the explosion energy from our simulations. Yeah. And this is basically just referring to the kinetic energy. Then the luminosity is a different question, since that depends on what kind of material you synthesize and stuff like that. So that's a different question again.
Right. Yeah. The other is, you mentioned a magnetar-like core, highly magnetic, rapidly spinning core, which you and others have also referred to as magnetar-like things, and these are rare,
right?
And so they presumably don't connect to the observed population of magnetars in the galaxy, which are not that rare.
No, that's absolutely right, and it's also a question of like how these magnetars actually get their fields. So basically, there would be a way of like getting this immediately in the supernova, but then there's also a question of like how does this happen with recycling of magnetars? Since most of these that we observe are not super young, right? So they don't show a strong magnetic field if they're young. So then that's actually a more complicated question. But you're right that basically the observed magnetar population cannot be explained by just being produced by type 1c broadline explosions, since those are way too rare to like explain all of this. So just having a magnetar doesn't seem to be the full story of like being connected to type 1c broadlines. But then here rotation plays a crucial role, where if you have a way of creating your magnetic fields independent of rotation, then basically rotation would here be the kind of defining parameter where you actually have an explosion being driven out of these magnetars or not. But that is a complicated question, since you would need to actually do the full evolution from basically core collapse until very long times to figure out if you actually get a proper magnetar out of this. Since here you have the field, but it's not necessarily settled onto the neutron star yet, which is again a different question.
Okay. Okay. Well, let's thank Philip. And as you already described, next we have Bruce Roberts, who's from Caltech. And he's going to talk about multi-group radiation, hydrodynamic simulations of core collapse supernovae.
Yes.
So after 10 minutes, I'll tell you that there's 5 minutes before your 5-minute talk.
Okay. Excellent. Oh, this thing goes here. Let's see. So can you guys, okay, is that coming through? Excellent. Oh, how do we switch over? Okay, yeah. So Philip just gave a very nice introduction to this topic. So I'm going to talk about sort of more garden variety supernovae today. But before I go on, I'd first like to say thanks to, this is my last year in the Einstein Fellowship. I'd like to say thanks to all the people who facilitated it. It's been great. It's been a good time to come to these meetings as well. So this is sort of the last talk I'm going to give. And I'm going to talk about three-dimensional radiation hydrodynamic simulations of core collapse supernovae. This is something we've been pushing forward actually for a while, but these simulations take a long time. So this is still actually fairly preliminary work. So, but I'm going to tell you something about our models. Or I'm going to tell you something about the sort of standard core collapse supernova problem when you want the neutrino mechanisms to work. I'm going to talk about our radiation hydrodynamics methods that we're using here, our general relativistic radiation hydrodynamics methods. And then I'm going to present some preliminary results that we're finding for our simulations of full 3D post-bounce evolution. And so I don't have anyone's names up here, but there are quite a number of other people who are involved in this, and mainly that would be Christian Ott, someone I work with at Caltech mainly. But there are also other people who have developed hydrodynamics code that the radiation transport stuff that has been built on top of that I have done. And so Philip is also one of those people. So I think we've had a couple of reviews of core collapse supernova stuff, but just a quick slide here to describe all the potential ways that these things are multi-messenger objects. So the most obvious thing is that you have some electromagnetic signal from these things, and you might have type 2Ps, type 1Bs, type 1Cs, depending on the shape of the light curve, what sort of lines are found in those light curves. You also, from the innermost regions, you observe neutrinos. And maybe a couple years ago, I would have told you that these were the only neutrinos from outside of our solar system we'd observed. That's, of course, probably not true now with ice cube observations. There's obviously another, at least for galactic supernovae, there may be another source of information that we can extract from the innermost cores. So these things might emit a significant amount of gravitational waves. Not enough to be detected for a supernova outside our galaxy, but at least for some within our galaxy, advanced LIGO and stuff may be able to detect them. And then, of course, these things also contribute a lot of elements to interstellar medium and are very important to nucleosynthesis. So these are interesting objects, interesting events to study. But there's this sort of problem, right? Is that you somehow go from this massive star to an explosion that drives some light curve both through the shock propagating outward and also from some decay of nickel and cobalt in its tail. But if I start out with this core or this massive star and it eventually stops burning iron in its core, or burns the iron in its core and stops burning in its core and builds up this hydrostatic, somewhat cooling core, how do I get from this thing that eventually collapses to an explosion? And so the basic picture, as Philip took you through this, right, is that you build up this core, it gets more massive and hits something like the Chandrasekhar limit. And once it hits that Chandrasekhar limit, it starts to collapse inward somewhat. And then electrons capture on nuclei in this material, and that removes more and more pressure support from this thing. And it collapses more and more rapidly, and at least outside of some radius, you get supersonic collapse. And then inside, you get some homologous collapse. And I'll show you this in more detail in the movie here in a second. And then eventually, you get this bounce shock. But the idea is basically you've taken a white dwarf and you've turned it into a neutron star. And this is a very old argument from Bodian's Wiki. And this is something like you release like 3 times 10 to the 53 erg going from this white dwarf to this protoneutron star. And the binding energy of the stellar envelope is only like something like 10 to the 51 ergs. And for standard supernovae, that's sort of also the scale of the kinetic energy you'd like in this thing. So really, you have a huge amount of energy relative to the amount of energy you need to put out. But the problem is that most of this energy comes out in the form of neutrinos, and that's very hard to couple back. And so in a little bit more detail, I guess, we can look at how at least in a 1D model, all of these quantities evolve. So this is the density is a function of radius here. The electron fraction is a function of radius. The neutrino luminosities for all 3 neutrino flavors. And then the velocity is this black line. And the entropy is this red line here. And so it's not very exciting right now, but you'll see it pretty rapidly evolve if this works. So you can see the density in the core goes up. And like I talked about, it eventually gets up to something like quite close to nuclear saturation density. You have a shock form. That thing propagates out. But then eventually neutrinos break out. And that saps a lot of energy from this shock. And also this dissociates a lot of iron and all this sort of stuff. And eventually the shock reaches a maximum radius and starts to propagate back in. And you can see a few features here that you have some region where you're emitting a lot. So here's the neutrino luminosity as a function of radius. So where these are increasing, you're basically adding neutrino luminosity to the fluxes. And in these small regions where they're decreasing, you're actually depositing neutrino energy. The decrease out here is actually due to gravitational redshift, so just ignore that. But the point is that you're taking energy from this innermost region, and you're coupling some amount of it to this small region here, and that's increasing the entropy in this section here. And so you're heating behind the shock with these neutrinos, but the question is, how efficient is this? And so if you, like I just showed you in this movie, in 1D, this neutrino mechanism for core collapse supernovae is not efficient enough to blow up the star. So, and that's true for almost every progenitor mass. There are some low mass progenitors for which this can work, but for most it doesn't work. So the question here is, okay, is the whole story this 1D model, or is there more going on? And of course, I think probably everyone's aware that there is significantly more going on. So I've left behind this entropy gradient that's a negative entropy gradient here. So this should be convectively unstable material. That should enhance energy transport in this region. And maybe that's going to change the dynamics of how this shock evolves, and then whether or not I can get an explosion. So there's these hydrodynamic instabilities, and this is a plot of entropy in some models I'm going to show you in a few minutes. And so you can see that this is very far from spherical symmetry. And people realized, so this is something that people realized around the beginning of the 2000s. If you do have accurate models of the neutrino physics and everything in there, you can't get these explosions. But if you go to axial symmetry, you in fact can get shock runaways. So here, if you're in axial symmetry, the red lines are the model I'm going to show you later on in this talk. And you can see that they start to get shock runaway after about 200 milliseconds. And so they get to shock radii that are much larger than what we saw before. But of course, okay, it's clear that you're going to get this convection, you're going to get turbulence behind the shock. And so axial symmetry is very different from our 3-dimensional reality. And so really only in the past few years have people been able to push into being able to model the neutrino mechanism in 3 dimensions. And so I'm going to tell you about some of our modeling, but also other groups in the last year. So the Oak Ridge group and the Garshin group have also started to look at this, although using a different method for radiative transport. But so the question becomes, okay, how does this depend on input physics and numerics? It turns out it's quite sensitive. At least these are some of the Garshin models. So if you look at how the shock radius proceeds and you change the neutrino interaction rates by maybe 20%, so include some strangeness correction, and you get shock runaway. If you don't include that, then you don't get shock runaway. So, but this is only for one particular resolution for their models, and so we'd like to look at this in a little bit more detail. So to do this, we implemented this 2-moment neutrino transport scheme. Basically, I think everyone probably understands how this works. You just take the Boltzmann equation, take some angular moments of the neutrino distribution function, doing this all in general relativity here, You get some conservation equations for the projection of the neutrino energy density, the spectral neutrino energy density, and fluxes in the laboratory frame. And so you get some spatial fluxes here, and you get some fluxes in momentum space here, and then you have some source terms. This turns out to be quite amenable to finite volume techniques, so you can use a framework that's very similar to like our hydrodynamics code. Of course, you still have this problem that you need to specify the stress tensor, so you have this infinite hierarchy of moments. And so here we use sort of the standard M1 closure. This was talked about earlier on today. This is a big advantage because it speeds things up a lot, but it does have some problems because essentially this makes radiative transport, which is a linear problem, into a nonlinear problem because the pressure tensor depends back on E and F, and you can get things like caustics and radiation shocks that are clearly unphysical. Okay, I'm going a little bit slow. So these are some of the neutrino interactions we include in here. I'm just going to skip this. And so this is just an overview of what simulations we're doing. So we're using a 27 solar mass progenitor from Woosley and Hager, and it's sort of this is a parameter that tells you something about whether or not this progenitor model is likely to explode, and we're sort of in a regime where this thing is probably likely to explode. And so we're using these general relativistic radiation hydrodynamic simulations with 12 logarithmically spaced neutrino energy groups. So this is something like 48 variables plus all the hydrodynamics variables we're evolving. This is on a Cartesian grid with some sort of adaptive mesh refinement. And this has taken about 30 million hours of CPU time. But the important thing is it picks about 3,000 hours of wall clock time. And so that's like 120 days. And so that's why it's taken so long for me to tell you about these simulations. And so I'm going to show you the results from about 4 simulations, one including the full domain in 1.5 kilometer resolution behind the shock, one with the same resolution but in a single octant of the grid, and then reflecting symmetries on the interfaces of that octant, another one that's half the resolution but on the full domain, and another one that has this reflecting octant symmetry again but at the lower resolution. And so you can just watch how the entropy evolves. And so outside of this, well, this is an approximate thing, but outside of this gain radius, you're depositing neutrino energy. And so this is the entropy. Not much is happening for the first maybe 50 milliseconds. It looks more or less like it would in 1D. But then you can see some hot plumes start to rise up buoyantly. You get some sort of convection behind this shock. And this changes how energy transport proceeds. This goes on for a little while. It starts to look nicer pretty soon. But you start to get higher and higher entropies. But there's not much going on inside the region where all the neutrinos are emitted here.
Is this uniform grade everywhere, or is it mesh refinement?
So there's mesh refinement starting down here, and then I think the outer mesh boundary is somewhere out here. So all the stuff that's going on behind the shock is on the same grid. And the neutrinos are on the same grid as the hydrodynamics and stuff. So you eventually, this thing evolves and convects and sits there, and you can see, okay, this is just showing you where I'm getting neutrino heating. I think I'm running low on time. You can look at some of the global properties between these things. So here's the neutrino luminosity that we predict as a function of time. And all the same colored lines are for different neutrino species, and the dashed lines and the thin lines and the solid lines are for the different resolutions and symmetries. And the takeaway from this is that you see very little variation in the neutrino luminosities and the neutrino average energies as you choose different symmetries. And this actually, and resolutions. And this actually looks very similar to what you would get in 1D. So there's not much difference there. There's also not much difference in how much heating you get from these neutrinos. So if you sum over the region that's getting net neutrino heating, you can calculate, which is this convective region, you can see that you're getting about maybe 10 to the 52 ergs per second input in all these models, and there's not too much variation between the full symmetry, the full models, and the lower resolution models. You can also use this quantity to look at how efficiently you're depositing this energy, and you can find that maybe you're depositing 5% of the neutrino energy that's emitted, and maybe 10% once you get through this point where you go through the silicon oxygen shell and the accretion rate shuts off. So this is the accretion rate as a function of time. And it's basically the same for all models. And so you see that you get some increased heating efficiency after here, but you don't really see much difference between different symmetries and different resolutions. But if you look at how the shock evolves as a function of time in the high resolution simulation, you see that once you go through this silicon oxygen shell around 220 milliseconds, you see that the accretion rate falls off, the tamping down on the shock stops. In the high resolution model, you see that the shock starts to run away here. But if I go to the lower resolution model, I get shock run away much more rapidly and at a little bit earlier times, still associated with this change in the accretion flow. If I look at the octant simulation at high resolution, I get something that looks, at least at early times, fairly similar to the high resolution model, but it doesn't in fact explode. So the shock is moving inward. And if I look at the octant low resolution simulation, it looks very similar to the other low resolution simulation, except for it doesn't run away quite as rapidly. And so if I remove all, so these were the bounds of the shock radius, so the maximum minimum shock radius, and here are just the average shock radii. So you see this evolution here. And we think this is probably, so this is consistent with what people have seen in models with much more simplified treatments of the neutrino luminosities. So what we think is happening here is that this is really due to the difference between how turbulence behaves at different resolutions. So we have a numerical Reynolds number that's relatively low compared to the physical Reynolds number we should see. And so in these models with lower resolution, we're trapping more energy at larger scales. And so that seems to be advantageous for shock expansion. And that would also be consistent with the difference between these octant and these full simulations, because there you're suppressing a bunch of modes that, you're suppressing a bunch of large-scale modes in the octant simulations. So I think I'm at the end of what I wanted to say here. I told you about our M1 model, or our two-moment model for radiative transfer, and it provides a reasonable solution to this in the close to spherically symmetric situation you find in core collapse supernovae. We've done long-term evolution of post-bounce core collapse supernovae without imposed symmetries. We're starting to see that shock runaway occurs in these models, but we're not far enough along to really quantify what the explosion energy should be here. But there is significant dependence on resolution and assumed symmetries, and more detailed analysis of the post-shock flow should follow. So thanks.
Thanks. Do you have questions? Yeah.
Do you see any trend towards convergence in your resolution studies that you've done?
No, I mean, I think you have to, so David Radice has looked at this in more simplified models and smaller domains, and I think you need at least a factor of a few more resolution. So this is a significant problem for moving forward with these 3D models. I mean, this is something that people really started to be able to do in the last year or two. So hopefully in 5 years, we'll have enough computational power to do this at somewhat higher resolution, maybe some better techniques to capture the cascade.
Can you say again in a bit more detail what are the multi-groups?
So we have, this is just the neutrino energies, right? So we're integrating over some region of neutrino energy and evolving, let's say, from 0 to 1 MeV, 1 to, well, it's not actually 1 to 10 MeV, but 1 to 10 MeV, 10 to 20 MeV. You need to have this very high, you need to have at least some spectral resolution here, because the neutrino interaction rates depend, they go as an energy squared, right? So you need to have some spectral resolution to get the neutrino spectrum right.
Do they interact with each other?
Yeah, so there's redshifting terms in there, and we just do those via advection, explicit advection. The only implicit piece in this is the source terms, and I didn't say it, but we don't include inelastic scattering, so the groups don't have to be implicitly coupled.
Can you say a bit more about the difference between the octant simulation, high res, and the full simulation? So I'm kind of surprised that you're seeing such a drastic difference.
Well, I mean, I think they're right on the line. I mean, if you look at, the shock is not running away rapidly, and if you look at there's not a great, I didn't really choose this so well, But I mean, if you look at what the minimum shock radius is doing in the high resolution case, it's sort of sitting along down at the bottom here. So it's not like, I would this seems positive for explosion, but it's definitely not definitively exploding. So, that's about as much insight as I have.
Going back to what Blakeslee was asking, or perhaps telling us in her talk, that you're discussing the turbulence in the final throws here, and I don't know much about this, but my understanding is that the introduction of turbulence in these 3D models is essentially providing the capability of the materials staying in the neutrino gain region longer and making the explosion happen. But is that not what you're seeing, or not?
Well, I mean, so that's a reason that's been invoked, so that you have material sits in the gain region, has longer time to be heated by neutrinos, and that makes things more efficient. That doesn't, but that's a story that people tell. I'm not sure that there's so much analysis that went into that stuff. I think that there's starting to be more quantitative results. People have showed that the turbulence actually provides maybe a significant amount of pressure. So the Reynolds stress provides a significant amount of pressure, and that can be important. Those other things, how it transports energy through the gain layer.
Any other questions? Okay, thank you. And our final talk of the afternoon and the symposium is by Francois Focard, my French is terrible, from Lawrence Berkeley National Lab. He's going to tell us about the evolution of accretion disks using extended MHD models.
All right, thanks. So I'm François Foucard from Lawrence Berkeley Lab. Most of what I do usually is merging neutron stars and gravitational wave sources, but that's not what I want to talk about today. Instead, I'll give a talk which is mostly a complement to what Sasha was talking about, which is looking at the effect of a very low collision rate in the plasma forming accretion disk around supermassive black holes, around many supermassive black holes at least. And I should say that a lot of the work that I'm going to present is also done by Mani Chandra, who is a graduate student at the University of Illinois, and in collaboration with Mani's advisor, Charles Gami, and Elliot Cattard at UC Berkeley. So Sasha already gave us a good introduction on accretion flow around supermassive black holes. So let me just mention a few key points for this talk. Most disks around supermassive black holes are thought to accrete at a rate which is much lower than the Eddington rate. And in particular, this is the case for the two black holes which are the easiest to resolve from Earth, which is Sagittarius A star at the center of our own galaxy, and the supermassive black hole at the center of the M87 galaxy. In that regime, we expect that the accretion disk is very ineffective at radiative cooling, and so the disk will be geometrically thick, optically thin, and most importantly, from the point of view of this talk, mainly collisionless. The Coulomb collision rate between charged particles is very low. We are interested in studying those disks for multiple reasons. One of them is, as we have heard a lot during this conference, that all flow from accretion disks are critical probably to the evolution of galaxies. Another one is that the Event Horizon telescope is coming online. The Event Horizon telescope is an array of millimeter wave telescopes, which is going to use as baseline basically the entire Earth. And by doing that, you can actually start resolving the accretion flow around Sagittarius A star and M87 with subhorizon resolution. And in order to understand those observations, we would like to have a good model of those accretion disks. Now, why is this a problem? We have had simulations in 3D of accretion disk in ideal MHD for some time now. The problem with those accretion disks is a question of scale. We expect that the magnetic field in the disk is relatively strong, so the Larmor radius of particles in the disk is expected to be very small compared to the size of the disk. So charged particles are well confined in the direction perpendicular to the magnetic field. But because the plasma is nearly collisionless, Coulomb interactions are rare, you expect that the Coulomb mean free path of particle along the direction of the magnetic field is extremely large. And in that regime, in theory, you cannot model this as a fluid. your mean free path, your Coulomb mean free path is much larger than the size of the disk, this breaks your assumptions that you have actually an ideal fluid here. So if that was the whole story, we would be in a lot of trouble because we would have to evolve the distribution function of electrons and ions in the plasma. And in global 3D simulations, this is extremely expensive. We don't have the computational power to do this at this point. Thankfully, there is an effective coupling between particles, which is due to wave-particle interaction, which has been found in local simulations of plasma, and which effectively means that the effective collision rate of particles within the plasma is much larger than what you would expect from Coulomb interactions. And that gives us hope that first, ideal MHD simulations are at least order of magnitude correct, which is good because that's what we are basing most of our understanding of our disk on. And on top of that, that we can go further and get a better understanding of those disks by modeling the plasma as a perturbation of an ideal fluid. And Sasha presented one aspect of this, which is concerning two ideal fluids in which you decouple the electrons and the protons and the ions. And here, in this case, I am going to focus instead on what happens when the ions themselves are a non-ideal fluid, so when there is low collision rate, weakly collisional plasma for the ions. And in the slowly accreting disk that we are considering here, we expect the ions to dominate the dynamics of the disk, while the electrons, as Sasha explained, are critically important to understand the radiative properties of the disk, but they mostly act on a fixed, on what is for them is the background of protons on which they don't back react. So here I'm going to be interested in the dynamics of the disk without looking at the electrons. So in order to do this, we had to develop a new model to evolve a weakly collisional plasma in general relativity. And the idea behind the model is to develop a model which is first consistent with general relativity, so covariant, causal, and stable, and also a model which is in agreement with the second law of thermodynamics, and which, in the limits of a non-relativistic plasma, asymptote to a known theory for a plasma with strong magnetic fields, which is Braginsky's theory. And what it comes to in practice is that on top of the usual fluid variables and magnetic field that we are evolving in those simulations, we have to evolve two additional fields. One is a heat flux along magnetic field lines, which effectively transport energy along magnetic field lines, which is also the heat flux that Sasha was using in his electron simulations. And the second is the pressure anisotropy, so a difference in the pressure parallel to the magnetic field line and the pressure perpendicular to the magnetic field line. And this pressure anisotropy effectively acts as a shear onto the plasma. And in non-relativistic theory, you can just set the heat flux and the pressure anisotropy to, for the heat flux, something proportional to the temperature gradient along magnetic field lines, and for the pressure anisotropy, something proportional to the projection of the shear tensor onto the magnetic field. In general relativity, this is not correct because this is not causal. So in general relativity, you have to go a little bit further and actually evolve the heat flux and the pressure anisotropy and damp them towards those target value on some time scale, relaxation time scale tau. So effectively, this model has three free parameters that we have to figure out that are not fixed by the general relativistic model. This is the damping time scale tau and the proportionality constant, which are effectively the viscosity and conductivity. So how do we choose this? Well, for the viscosity and diffusivity, we are informing our choice from local simulations, which tells us that they are proportional roughly to the collision timescale within the plasma and the sound speed square with some dimensionless parameter for the unity, which actually end up not mattering too much in our simulations. So that leaves us with just the timescale, the collision timescale. And the first rough guess for the collision timescale is that it's of the order of the orbital timescale of the disk. But there are important limits on how big the non-ideal effects of the pressure anisotropy and the heat flux can be. We know that if the pressure anisotropy grows to be of the order of the magnetic pressure, roughly, instabilities kick in the plasma, and effectively the effective collision rate between particles increase, or equivalently, the pressure anisotropy saturates at a value which is of the order of the magnetic pressure. And this is observed in simulations. This is known theoretically. And this is also observed, for example, in the solar wind, which you can see here, the ratio of the perpendicular to parallel temperature or pressure as a function of the plasma beta parameter. And these dotted and dashed dotted lines shows you the theoretical limit for the two most important instabilities in this plasma, which are at the top the mirror instability and at the bottom the fire hose instability. And they very effectively constrain the available parameter for the solar wind. So we are going to use this in our model. And the way we do this is that we actually use the free parameter in our model, which is the collision time scale. And when we reach those instability, we decrease the collision time scale. We make effectively the fluid less, more ideal. And this effectively saturates the pressure anisotropy to that value. And there's also an equivalent saturation limit for the heat flux, but it happens, as it happens, it doesn't matter in our simulations. So this is the model that we are going to use. Now, we want to actually start testing how these non-ideal effects affect the evolution of accretion disks. And for that, we had to develop a new code for evolving that system of equation. The reason we had to use a code different from what is generally used for the evolution of accretion disks in general relativity is that, first, there are very stiff source terms in the evolution equations for the non-ideal terms. The collision timescale can become very small in some regions. In that regime, the source terms are driving towards the Braginski heat flux and pressure anisotropy becomes very fast and very stiff. The other reason is that there is a strong coupling between the evolution of the velocity and the non-ideal terms, which involves time derivatives of the non-ideal terms in the evolution of the velocity and vice versa. And so to evolve this system of equation, we need to use an implicit time stepper, and that's what we have been using here. And details of the code is freely available on this website, and details are coming up in the coming paper. So now let's look at the actual evolution of an accretion disk. And this is a 2D simulation. This is the first time we actually evolved those disks, and so we have started with a very simple configuration. I'm going to show here the logarithm of the density, here the heat flux normalized by the saturation factor, the saturation limit, which is roughly where it becomes important, and here the pressure anisotropy normalized by the magnetic energy, which is roughly where the pressure anisotropy saturates. And so regions which are bright red saturate at the mirror instability, regions which are bright blue saturate at the fire hose instability, and everything that is pink is not saturated. And the evolution of the disk proceeds. So we developed temporarily, because it's a 2D simulation, turbulence. And in most of the disk, the heat flux, as you can see, is extremely low, of order of at most 10%, but in most regions, 1% or in 0.1% of the saturation limit. And effectively, it doesn't affect the evolution. On the other hand, the pressure anisotropy in most of the disk is very strongly saturated. Most of the disk, the pressure anisotropy is very close to the saturation limit. So that's effectively what is the main result of the simulation, is that the pressure anisotropy grows to whatever saturation limit we have used as a subgrid model in our model, but a subgrid model which is actually fairly well understood from local simulations, and then it just stays there. What that means is that the shear tensor due to that pressure anisotropy is of the same order as the Maxwell shear tensor, because the pressure anisotropy is of the same order as the magnetic pressure. And so you get an order 1 effect on the evolution of the fluid in terms of angular momentum transport, heating, and so on. This is another way to see the same thing, is that it's the same plot I showed before for the solar wind, but no for our simulation. And you can see that most of the matter is very close to the mirror instability here. And a significant amount of matter also is at the fire hose instability threshold, and a lot less matter in the regions in between, which are not saturated. So what really determines the evolution of the system here is those saturation limits. Now I can have a quick look at what happens to the heat flux. So I said the heat flux is very low in our simulations. And this is a little bit surprising in some ways, that if you were just looking at the temperature gradients, you would predict that the heat flux would be very close to the saturation limit. So the normalized heat flux, normalized the saturation limit, would be more than 20-30% of the saturation limit everywhere, and saturated in all the white region here. But at least in 2D, the gradient of the temperature is nearly orthogonal to the magnetic field. And so because you only transport energy along magnetic field lines, the actual heat flux that you obtain is a lot lower than that. And on top of that, because the pressure anisotropy saturates, and this causes an increased collision rate, effective collision rate within the plasma, this is another effect which actually reduces the heat flux, reduces the non-ideal effects. So you both saturate the pressure anisotropy and also causes the heat flux to be much lower than the saturation limit. So effectively, conduction plays no role in your simulations, but viscosity has other one effect. You can see this, for example, in the temperature of that plasma. And this is the ideal MHD result. You can see that, there is a hot coronal region, but in the full extended MHD results with viscosity and conduction, the temperature in those outflow regions is a lot hotter. And this could significantly affect the radiative properties of the disk. This is also where, in Sasha's simulations, the electrons were particularly hot, and how the two parts of the model, which have both to be incorporated together to get a full story, are going to play together, that's an open question at this moment. It's something that we have to figure out. But there's definitely an important effect of the viscosity of the protons on the evolution of the accretion disk. So that's where we are right now. We have developed a model to actually incorporate those weakly collisional effects in accretion disks, and we find that roughly we expect of order 1 effect, and we robustly find that the pressure anisotropy grows to the saturation limit, which is of the order of the magnetic pressure. So far in 2D, conduction plays nearly no role, but this could be different in 3D, where you could expect part of the temperature gradient to be along the magnetic field line instead of everything being orthogonal. And finally, we need to go now to 3D simulations and also to incorporate all the different parts of the non-ideal models that we have been working on. So the part that Sasha has been working on with electron thermodynamics, as well as this, which includes the non-ideal effects in the ion sector. And thank you for listening.
Your calculations are 2D.
Yes.
But in 3D, you expect the turbulence to be a little bit different on the boundary between the edge of the outflow and the rest of the...
Yeah, so at this point, in 2D, the turbulence grow and then just dissipates, and we don't actually sustain the MRI. So it's a very different setup. So currently, we see that the pressure anisotropy grows to be at the saturation limit everywhere in the disk during most of the evolution. So that's a fairly reliable result. But the fact that we see more heating in the outflow region, the fact that we see more outflows also in the presence of non-ideal effects, that has to be confirmed by 3D simulations, because you wouldn't really trust the 2D simulations for that.
But I guess my point just was that you have reduced conduction perpendicular to the field lines, but in 3D, if you have a turbulent boundary between those two regions, then it should be similar to the large-scale jet calculations that we were seeing yesterday, where you have sort of 1/3 the heat flux.
Yeah.
I didn't actually know
So in the coronal region, the heat flux is not necessarily negligible there, because there you actually do get temperature gradients along the magnetic field lines. It's in the whole core of the disk, which is actually the more reliable part here, that there is no heat conduction. The temperature becoming so large in the coronal region means that there you actually have nearly saturated heat flux there. But I don't trust that in 2D at this point.
If I remember right, in solar wind, you actually see increased heating in those regions along the instability boundaries for the mirror and fire hose. Do you get any, in your simulation, you're just essentially equilibrating the parallel and perpendicular temperatures, that's all that's happening?
So they are not equilibrating. They are they are basically staying at the instability limit. So the pressure are off by roughly the magnetic pressure. And there is definitely extra heating in the non-ideal simulations, effectively comparable to the heating due to the dissipation of the magnetic rotational instability. But again, in 2D, magnetic rotational instability doesn't behave as in 3D. So, but it's roughly it's another one effect because the pressure is the magnetic pressure, and the pressure isotropy is at the same level, right? So that's.
So you mentioned that you use the parameters, I think, for the solar wind, right? But what's the motivation for that? Because you're really interested in the conditions around a black hole.
The only thing that we use there is the fact that those instabilities are observed in the solar wind, and those instabilities are also seen in local simulations and can be obtained theoretically. So it's not where we use the solar wind actually is that there are other instabilities, for example, the ion cyclotron instability, which in theory could exist but are not observed in the solar wind. And so currently we have not included them in our simulations. But that is exactly how to close the model and how to include those instabilities is an open question that we are using the instabilities that have been observed, and because those seem to be reliable, but there could be more to it.
Okay, let's thank Francois again.
We have our final word here.
So I guess we can clap silently for a couple of people who aren't in the room that I want to thank. Ray Heeman, who did all the setup for the computers and everything. Lauren Deknis-Bortolami, who set up all the food and lots of other details. But Katie Wyman is in the room, so let's give her a hand. Collected all your presentations, put together the abstract handbook and the web pages and a lot of other things. So I don't really have any other announcements except again to remind you that Sunday is the deadline for reports, annual reports, and final reports. And I think it's been an excellent couple of days, so why don't you give yourselves a hand?
Let's give a hand to Paul and Rita.
Yeah, so a lot of that, all the agency stuff is in very recent and then all the stuff oh yeah.